테스팅 하나, 둘, 셋. 마이크를 테스트 중입니다. 하나, 둘, 셋. 테스팅 하나, 둘, 셋. 하나, 둘, 셋. 지금 현재 2주먹 정도 멀리 떨어져서 얘기하고 있습니다. 하나, 둘, 셋. 테스팅 셋, 셋. 셋. 테스팅 하나, 둘, 셋. 둘. 테스팅 하나, 둘, 셋. 마이크를 테스트 중입니다. 하나, 둘, 셋. 테스팅 하나, 둘, 셋. 지금 현재 마이크를 테스트하고 있습니다. 하나, 둘, 셋. 지금 현재 마이크 테스트 중입니다. 하나, 둘, 셋. 테스팅 하나, 둘, 셋. 마이크와 거리는 2주먹 정도 됩니다. 하나, 둘, 셋. 마이크 테스트 하나, 둘, 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 셋, 셋, 셋. 테스팅 하나, 둘, 셋. 마이크를 테스트하고 있습니다. 하나, 둘, 셋, 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 셋. 테스팅 하나, 둘, 셋. 마이크 테스트 하나, 둘, 셋, 셋.
PC 연결했는데 혹시 띄워주시나요? 네, 여기엔 나와요. 아, it's okay.
Oh, it works. Okay. Awesome. Thank you. Oh, okay. Oh, it shows up there.
It's okay.
I'll take it out.
Yeah, sorry, let me just restart the computer. Yeah, we just wanted to test to see if the presentation works. Okay. I see. Also, will this reflect what's going to go up there? Extend display. Cool. Okay. Good. Thanks. Sorry, give me a second. Okay.
there's a screen here, and then this device will tell you. Hello, everyone. Good morning. If you are here for the oral presentations and you are a presenter, if you could please come to the front and test your computer, that'd be fantastic. Otherwise, if you're here to attend and participate, you're in the right place and you can continue sitting in your seats. So it should be pretty straightforward. It should just be
Okay, good morning, everyone. So this is Yunzhu Li. I'm a faculty at Columbia University. So I will be the session chair for this oral sessions on manipulations. We're going to start with our first speaker, Wu Chong, for his presentation on ImMimic. Please.
Hi, I'm Mucho, a master's student at Georgia Tech, and today I'll be presenting our work, ImMimic, embodiment agnostic co-training from human videos via cross-domain interpolation. When training robot policy, teleoperation, where humans control robots through devices like VR, is costly and time-intensive. To address this, many have begun exploring co-training robot policy from both robot data and large-scale human videos. Co-training means training robot policy jointly on human and robot data. But co-training is still challenging because of the visual and action gaps between humans and robots. Visually, they simply don't look alike. In actions, humans and robots have very different morphologies, so they don't move the same way. In the videos, the wrist motions show how differently humans and robots move for the same task. Here, we started with a simple question. Can we easily bridge these gaps just by using more human mimetic embodiments? If we compare human hand, parallel jaw grippers, and dexterous hands not only visually look more similar to human hand, but they also have higher degree of freedom, allowing them to better mimic human actions. Our initial expectation, therefore, was that more human mimetic embodiments will perform tasks better in co-training. But does more human mimetic embodiment actually perform tasks better? We conducted simple co-training experiments. We first collected teleoperated robot data using online retargeting, which maps human motions to the robot in real time. Then we collected human videos, extracted wrist and finger poses, and applied offline retargeting, where recorded human motions are translated into robot trajectories. Next, we co-trained the model and evaluated it through rollout. The results show that more human mimetic embodiment doesn't necessarily perform tasks better. In tool-use tasks like hammer and flip, dexterous hands performed worse than parallel jaw grippers. These results were counterintuitive and against our initial expectations. To analyze further, we calculated the action gap between human and robot actions using action distance. We calculated the action gap between retargeted human action and teleoperated robot action. For action distance, we used a weighted distance metric using dynamic time warping to compare it to action vectors. Dynamic time warping is an algorithm that finds the optimal alignment between two time-dependent sequences that differ in speed or timing. From this analysis, we found that more human mimetic embodiment exhibit larger action distances than less human mimetic embodiments. This means we cannot bridge the action gap just by simply using more human mimetic embodiments. But during teleoperation, we observed that the larger distance may be caused by a behavior difference. Behavior difference occurs when humans adapt to robot system. To quantify this, we calculated the action distance between human behavior in teleoperation and in videos. Here we designed a 120-degree wrist mount that better aligns wrist motion with that in human videos. You can see in these videos that with the 120 degrees mount, humans behave similarly to the human videos during teleoperation, while with the 90 degrees mount, humans have to bend their wrists unnaturally to adapt to the robot system. The results show that an aligned wrist mount can mitigate the behavior difference. We calculated the action distances across two mounts and two tasks and found that the distance between human behaviors decreased with the 120-degree mount. The decreased behavior difference also led to a drop in overall action gap. In particular, the drop in action gap for wrist was significant with the aligned wrist mount. To summarize, we observed that the behavior difference causes action gap. In offline retargeting from human videos, robots imitate human actions. In teleoperation, human adapts to the robot embodiment. Thus, mixing in teleoperation data collected with misaligned mounts and interfaces may introduce a behavior difference. However, addressing action gaps by customizing wrist mounts and interfaces for each robot and task is costly and often requires abandoning pre-collected data set. Thus, we propose ImMimic to bridge the gaps at the policy level. ImMimic leverages large-scale human videos with a small amount of teleoperated robot data. A key challenge of vanilla code training, as we discussed, lies in the visual and action gaps between humans and robots. The core insight of ImMimic is to interpolate between human and robot data through mapping. Specifically, ImMimic establishes selective DTW mapping between human and robot demos, aligning only the representation that should correspond. It then applies mix-up interpolation to create intermediate domains between human and robot data. Mix-up is a data augmentation technique that creates intermediate domains by blending pairs of inputs and labels using linear interpolation. In this way, ImMimic can effectively bridge the domain gaps and enable more robust policy learning. After co-training with robot data and interpolated human data, we validate ImMimic on 4 diverse real-world manipulation tasks spanning 4 robotic embodiments. So here, instead of vanilla co-training we tried earlier, ImMimic first maps corresponding time steps between teleoperated robot actions and retargeted human actions using DTW. The same DTW mapping can also be applied to visual latents instead of actions. If we map based on action, we call it ImMimic action. If based on visual latents, we call it ImMimic visual. Either mapping strategy can be used. After mapping human and robot data, we interpolated the mapped data using mix-up to create interpolated human data. Finally, we co-trained a robot policy with both interpolated human data and teleoperated robot data. Here's the architecture of ImMimic. First, we collect robot and human data. Second, we retarget from human videos. Since human videos lack wrist cameras, we zero-pad the wrist image. Also, we use retargeted human hand trajectories and as informative action labels, serving both as proprioception and ground truth action labels. Third, we encode visual latents from the videos. Fourth, we map human data to robot data with DTW using either visual latents, ImMimic visual, or actions, ImMimic action, resulting in mapped robot data. Fifth, we interpolate this mapped robot data with human data to create interpolated human data. Finally, we co-train a diffusion policy with both interpolated human data and robot data. ImMimic uses linear mix-up scheduling during teleoperation to create a smoother domain flow from human data to robot data. We visualize TSNE of observation condition to illustrate domain adaptation. At the beginning, training starts with human data and robot data. As epochs increase, the human data becomes progressively interpolated with mapped robot data. By the end, the model is trained solely on robot data. We evaluated ImMimic action on 4 tasks across 4 different embodiments. The results show that ImMimic significantly and consistently improves the task performance. ImMimic outperforms baseline methods on most tasks, from basic object manipulation like pick and place and push to tool-use tasks like hammer and flip. We also found that action-based mapping yields greater improvements than visual-based or random mapping, suggesting that the rich action information in human hand trajectories is equally, if not more, beneficial for code training. Thank you for listening.
Do we have any questions from the audience? There are in total 6 microphones, so if you have questions, please come to the microphone. Okay, I can ask a question. So it seems, for the next speaker, please start to do the setup. So it seems that this kind of interpolation and the latent space mostly are doing some kind of interpolations over the position space. So what happens if some of the tasks require like a more force level information for it to be successful?
Could you repeat the last part, please?
Oh, okay. So what if the tasks require force level informations? Like how well does your pipeline work in those kind of scenarios?
Oh, you mean forced information?
Yeah, force informations.
Oh, force information. Okay, that's a great question. We haven't tried with the force data yet, but I think the force misalignment between human data and robot data still exists, and we can try to apply the interpolation strategy on the force data. We can try that in the future works, yes.
Okay, sounds good.
I have a
yeah,
question.
please.
Hey, good talk. I'm curious, when collecting the human data, do you have to change anything about how the humans are behaving to make it easier to get this method to work?
Yeah, I couldn't find you, sorry.
Hey, I'm over here.
Oh, okay, thank you. So the question is, do we have to Like,
Do you need to like instruct the humans to behave more robotically first?
Oh, no. When we collected human video, we just, the operator, like the operator just acted normally as what humans would do when performing the task.
Okay, so there's no like major dynamic shift between if like you're interacting with a deformable object versus very slow teleoperation.
Yeah, no major dynamics, difference, yes. Thank you.
Okay, thank you again.
Yeah, thank you.
Our next speaker will be speaking about his work on KineSoft, please.
Yeah. Hello, everyone. My name is Uk Sung. I'm a PhD student at Carnegie Mellon University, and I'll be sharing our work on learning policies for soft robot hands. Now, just for some context, we know from prior work, and in this case, our prior work, that we can do a lot of robust in-hand manipulation with soft robot hands by leveraging its unique morphology and softness. We also know from a lot of prior works, and also ours, that we can do safe physical human-robot interaction and delicate object manipulation using these soft robots because they're compliant and deform to be safer. Now, despite all these unique advantages, the challenge in the community has been trying to teach these robot hand policies for soft robots where the degrees of freedom are a lot higher than human hands, jointed degrees of freedoms, and where there's not a clear mapping between human hand poses and the soft robot hand poses. And this is in the context of the broader manipulation field where we've seen remarkable advancements in policy learning frameworks that can generalize to different domains and tasks that are largely built on thinking about mapping between the human hand poses and the robot hand poses using some similarity. Now, this is crucially kind of a limiting factor for translating those methods into soft robots where this mapping between the hand poses may not exist. And so the key problem in this paper that we're trying to look at is thinking about how can we leverage the benefits of the soft hands morphology and softness while also trying to bring in all these methods and frameworks that are developed for largely rigid robots into doing policy learning for soft robot hands. And so given this, we're looking at the core problem of how do we teach soft robot hands to be dexterous in manipulation skills. And the key idea in this paper is pretty intuitive, which is that because the fingers are soft in these soft robot hands, we can deform them kinesthetically to get the demonstrations for imitation policy. And the key component in this is doing mesh shape estimation of the fingers real time with high fidelity, which we can then use to train the high level imitation policy and also use as a shape feedback for the low level controller that we can use to track the desired shapes outputted by the imitation policy. So to start, we're going to discuss the mesh shape estimation, which again is a central piece of this. In our work, we embedded these strain sensors along the length of the soft fingers. And so what they look like, if you cut the fingers open in the cross-section, you'll see these 4 tendons that actuate the fingers, and then these 4 strain sensors that will measure how the fingers are deforming. And so these sensor signals, as you deform the finger or as the robot actuates itself, gives us a pretty clear signal for how the soft robot state is at that given moment. And to actually train a model that can predict the shape of the robot and to track the shape in the real world, we use FVM-based simulator to generate a large data set of soft robot configurations, both with contact and actuation. And using this simulated data set and getting the strain measurements through the finite elements, we can simulate the sensor signals at the strain sensor's length, and then use that to map to the deformation of the soft finger. And the actual model we use is a folding net-based architecture where we take the mesh encoder, where we do the vertex level encoding, and conditioned on the signals of the strain sensors, we try to decode the displacement of the vertices. So these models are right now only trained on simulation data, so we have to do some sort of sim-to-real domain alignment. And so to do this, we take the real-world sensor signals, we bring them into the shape estimation model, predict some shape of the soft robots, and take the real-world observation of the soft robot fingers using RGBD cameras, and then match using some shape alignment function. Now, this actual domain alignment function is derived from a physical model of the sensor, where we're trying to go looking at the resistance values of the sensors and looking at the simulated strain lengths, and then trying to optimize this kappa values to align the 2 distributions. And we can update these alignment scaling terms using sample-based optimization, where we try to iteratively update the values to minimize the error in the shape estimation. And so we show that we can improve on all the baselines, both in domain alignment problem and the model learning problem here. Okay, so now we can use these shape demonstrations to train the high-level imitation policy, and to do this, we kinesthetically deform the soft robot fingers to perform manipulation tasks. Using this, we can track the shape estimations, which give us the proprioceptive states, also the point cloud data that are filtered to get the fingers out, and then also the robot and effector poses. We can also use the shape estimations for the low-level feedback to actually track the outputs of the imitation policy. And for this, we project the hyper-underactuated soft robots states to the actuation directions of the servos and use a proportional controller to track the precise desired shapes of the fingers. Now, we demonstrate our pipeline through multiple different tasks. For some of the tasks, these are tasks that are known to be advantageous for soft robots to perform, so delicate object manipulation like fabric pickup, or doing berry picking by looking at these suspended berries and trying to pick them without crushing them. Or trying to do flat object grasping, where you're trying to pick up a piece of paper from tabletops. Right? We also show these performances on tasks where soft robots have a lot of hard time doing. Conventionally, they usually involve finger coordination, either single finger or multi-finger coordination to do in-hand object reorientation, like unscrewing a bottle cap, or trying to do in-hand articulated object manipulation, like this bottle that we're trying to unlid using its one hand. And so we show that compared to the baseline, only using the strain measurements directly, KineSoft, by using the shape intermediate representation, can actually execute the skills better across all the tasks. So to summarize, in this work, we present KineSoft. We use a proprioceptive pipeline using embedded sensors to measure the shape estimation, to use as both high-level imitation policy demonstration and the low-level execution for feedback controllers. We show that the shape estimation-based imitation learning kind of bridges the gap between the demonstrated shapes and the executed manipulation shapes. And then we also show that we can demonstrate success across tasks that are conventionally easy for soft robots to do, as well as tasks where soft robots struggle with, where you have to do multi-finger coordination. So I look forward to any of the questions you may have right now or later in today's poster session. Thank you so much.
Do we have any questions, please?
Yeah, great work, Ukshan. You said that in the simulate experiments you're also having contact. Did you have to do anything specific to deal with contacts and transfer it to the real world?
Yeah, in the actual policy, like the controller, we don't actually reason about contact conditions too much. It's a purely kinematic kind of policy. But the primary motivation in trying to deal with the contact in simulation is to try to also capture the shapes that the soft robot can get into when you kinesthetically deform them, which is obviously involving contact. But yeah, we're also interested in how we can incorporate tactile signals when we actually do the policy learning in the future works.
Great, thank you.
Any more questions?
Hi here. Really impressive work, and I'm curious about the hardware consistency. So, for example, if the hardware is using as time goes, and maybe you build like 3 or 4 more hardwares, how does the estimation results varies as time goes?
Yeah, so I think the part about the sim-to-real domain alignment pipeline that we propose is to account for these kind of variability in the manufacturing. The sensors itself is pretty robust, so we didn't see that much hysteresis. And actually in the paper you can see results on how the performance degrades over dozens of iterations or dozens of policy rollouts. And we haven't seen like significant degradation of performance through that.
Oh, cool, thank you.
Yeah, I think that would be all for this session. Let's thank the speaker again. Next, we'll have Suri and Laura presenting PIO5. Please.
Great. Hey, I'm Suraj.
I'm Laura.
And we're going to be talking about PIO5, a vision language action model with open world generalization. Now, in the last year, we've seen some tremendous progress in robot capabilities, doing some really dexterous tasks across a lot of different embodiments, right? Things like folding laundry, assembling boxes, or even lighting candles on pies. But often these skills are restricted to lab-like settings, making them a far cry from what we need to make robots really useful in our everyday lives. So what does it take to actually bring these capabilities into the real world? Well, it's actually quite difficult, right? Taking dexterous skills and making them work in any home you could drop a robot into has been a long-standing challenge for a reason. The real world is highly diverse, where no new home will look exactly like one you've previously seen. So that means whether it's Laura's home with its relatively clean bedroom and kitchen, or mine with its bedroom full of clothes all over the floor and a random bicycle in the kitchen, the model needs to be able to handle the unknown. So motivated by this challenge, we set our sights on a concrete goal. Get a robot to clean a kitchen or bedroom in a totally new home, 0 shot. So achieving this level of generalization is hard for a number of reasons, right? Imagining a robot that's just been dropped into a totally new kitchen. First, even at the level of one very narrow primitive action, like say opening a cabinet, doing this in a new environment may require a fundamentally different level of low-level control based on the context. For example, these are all videos of opening a cabinet, but in each case using a different level of dexterity and a different low-level strategy based on the specific cabinet in that scene. The same goes for something seemingly as simple as putting a pillow at the head of the bed. The size, shape, and surface of the pillow and the layout of the bedroom fundamentally alter the low-level control needed to complete the task. Second, stepping back from low-level control, the model also needs to be capable of high-level reasoning of what objects are and where they need to go, even if they're unseen. Right? For example, understanding what it means to navigate to the sink, even though the layout of a new kitchen might be totally different and the visual appearance of the sink in that kitchen might be totally different. This high-level reasoning then needs to be combined with the low-level control I just talked about to complete these full long-horizon tasks. So motivated by these challenges, what type of data do we need to collect? So first, towards capturing this relationship between low-level action and diverse objects and scenes, the most natural choice is going to be to collect expert teleoperation data of dexterous skills across a large variety of environments. So we're going to do exactly that, focusing on mobile robot collection, right? Because mobile robots can most effectively cover the space of tasks that all sorts of different homes can afford. At the same time, we have these nice clip-on robot arms, so we can bring them along with us whenever we go into a new environment and collect some static data in these new scenes as well. So both of these types of data are going to be that type of data that's showing us, what is the low-level control I need to open any new drawer or cabinet. Second, towards tackling the challenge of high-level understanding of objects and their affordances, we can leverage web data. Right? So this has internet-scale knowledge of objects, how they look, how they can be interacted with. So this is that data that's going to show us this is what a sink looks like in a totally new kitchen and where is it relative to other things in the scene. And finally, we still have this very large-scale in-lab data of many embodiments doing many tasks. Right? So this is a strong foundation of lots of tasks, lots of objects, and we're going to train on this as well. So concretely, about a year ago at the time of Pi 0, we had collected about 10,000 hours of this in-lab cross-embodiment data, and so this was on the order of tens of scenes and maybe 100 tasks. By PIO5, we'd grown to significantly more data, well over 10,000 hours total, and we collected 400 hours of data of this diverse mobile data across many environments. So note that this mobile data is actually less focused on quantity, but much more focused on environment diversity. So overall, we're covering over 100 environments and many hundreds of tasks.
Now, how do we train a model that can absorb all of this data effectively? We first combine all of these data sources in our pre-training phase, where we start with a VLM and co-train on multimodal web data, as well as our robot data with discretized actions. Then during post-training, we fine-tune the model to infer its own goals, or subtasks, from a high-level prompt, and then produce continuous actions for dexterous control. Now at test time, the model takes as input observations like these and a high-level prompt like clean the bedroom. Then it'll verbalize its own short-term goal, like I'm gonna pick up this pillow, and then with these as context, produce an action and repeat. Now let's really see this in action. Here we took a robot to a completely new home and only told it to clean the bedroom. First, we see that it identifies some clothes strewn on the floor and puts them away in the hamper. It then spots some trash that missed the trash can behind it and turns around and throws them away. Finally, we see that it decided that the bed also could use some tidying, so it goes and puts the pillow at the top of the head of the bed and straightens up the blanket. So what actually matters for making this work? To dig into this, we did some controlled experiments with 4 kitchen bedroom cleanup tasks in 10 unseen mock home environments. And first, we're going to look at how zero-shot performance scales with the diversity of environments we collect training data in. As a kind of upper bound, this green bar shows the performance we get if we train on data directly collected in the test environment. Now we see that as we increase the number of training environments, zero-shot performance improves. And finally, at just about 100 locations, zero-shot generalizations actually just as performant as the in-domain specialist. This was pretty interesting to us because going into this project, the number of training environments we needed to get the sort of generalization we were looking for was a big unknown. It could have been anywhere from 10 environments to maybe 10,000 environments, right? So what we did see, though, is that our diverse pre-training was a key enabler here. Without it, trying to generalize from those same 100 training environments got near zero success. Now, what about the other data sources that we trained on? We can see that both static data with environment diversity, which we refer to here as multi-env, and lab data with task and embodiment diversity, cross-emb, are both really important. To us, this is also a remarkable finding, specifically that leveraging the more than 10,000 hours of in-lab cross-embodiment data was actually important for getting the most out of our diverse mobile data. Now, in our standard suite of tasks, we only saw a modest lift from training on web data. But we find that when handling out-of-distribution objects, web co-training indeed clearly helps. For example, while we don't have data of the robot interacting with a pair of goggles or a guitar-shaped spoon, the model that's co-trained on relevant tasks with web data exhibits the ability to identify and manipulate those objects. So why does that matter? More robust language following is useful in allowing a user to steer the model. So in this video, we're seeing Chelsea walk the robot through how she wants it to clean this unseen kitchen. We see that the robot clearly understands and does the tasks as prompted, turning toward the dishes and sink and putting them all away, and also reacting to the new dishes that Chelsea added. Now, after putting all the dirty dishes in the sink, when asked to clean the spill, the robot locates a sponge and the ketchup spill that she's referring to and wipes it all until the counter is clean. Now, we didn't test this in just one home, but several kitchens and bedrooms, letting the robot run continuously for up to even half an hour at a time without any physical intervention. So in summary, we demonstrated that PIO5 allows mobile robots to tackle challenging long horizon tasks over the course of tens of minutes in entirely unseen homes. We're really excited about this result because it's a sign that real-world generalization can emerge by scaling diverse data with dexterous VLAs, and a step towards really useful generalist robots. But we don't want you to just take our word for it. We encourage you to try PIO5 out using our open source code. Now, does this mean that we're going to have robots in our house cleaning our rooms tomorrow? Not quite. Of course, there's still some limitations, especially around reliability, safety, speed, and handling even longer horizon and more open-ended tasks. And we're, of course, excited to continue making progress on these. Thank you.
Thank you. I will take the chance to ask the first question because you guys are going towards generalist robots. And significant claims require significant evidence. So I'm just curious, the protocols you put in place for doing the evaluation that you can know you are making concrete progress. I'm referring to papers like large behavior models. They are having some kind of protocols to making sure they know whether a model are making progress or not. I'm curious about the protocol you take to evaluate your models.
Yeah. So I think actually one interesting point here is, for a while when we were running our experiments for this paper, we were just evaluating in a couple environments, like 1 or 2 environments that were held out, right? And we were seeing that after a while, like some of the things we were trying weren't helping. We were a little bit confused. And actually, it was only after we were running our evals in more like 10 different unseen environments that we saw like some of these interesting results. So I guess one takeaway is that really scaling actually your evaluating a lot of different settings, a lot of different unseen environments is actually key to even, seeing these results and establishing some of these takeaways.
Yep. Ken.
Oh, thanks. So really interesting, and I'm curious about the 80% progress. Can you say a little more about, what does that mean? In other words, does it just stop at a certain point, and then what's the 20% left over? Is it just the bed has a few wrinkles and a few things are still in the kitchen, or what's left? And can you say a little more about how you might address those?
Yeah. So like the task progress, like usually these are pretty long horizon tasks, like involving putting multiple items into the sink or like making the whole bed. And so the criteria changes for each task, but for the dishes and sink example, the task progress is measured in like how many objects were successfully put into the sink. So in that case, maybe 80% could mean that it just wasn't able to maybe pick up one of the harder items like a cutting board that's like flat on the countertop and put it into the sink. I think in terms of, or hopefully that answers your first question. And then in terms of how to maybe address the remaining 20%, I think one maybe unsatisfying answer or maybe satisfying answer is that with more data, we've seen that like these numbers go up pretty significantly. But also like there's always gonna be some gap, especially when we're trying to do zero-shot generalization. And I think like things that incorporate on-policy experience, whether that's like with human help or just autonomously, can maybe in the future address that gap.
Yeah, due to the time limit, we have to end it here, but you are welcome to check out with the authors during the poster session. Let's thank the speaker again. Next, we're gonna be hearing from the speakers on their work, Tactile Beyond Pixels. Please take it away.
Hi, this is Akash, I'm Carolina, and today we'll talk about Tactile Beyond Pixels and how can we use multisensory touch to improve robot manipulation. This is a collaboration between University of Washington, CMU, and Meta. So touch is a rich sense, and it's key for human dexterity. For us, touch means skin deformation, vibrations, motion, pressure, and more. With it, we're able to tell objects apart. We can feel patterns, do blind insertions, and handle delicate objects with precision. But in robotics, multisensory touch is still under use. Most methods focus on single type of signal, for example, tactile images from vision-based tactile sensors or forces for magnetic skins. Now, new sensors like the Digi360 make multisensory touch possible for robotics. They give us high-resolution images, vibrations, motion, and pressure at the same time. This gives much richer information about contact and forces that describe object manipulation, but it also makes the system more complex. So what we need is a method that is unified, scalable, and easy to fuse all these sensing modalities, and that we can easily incorporate for policy learning. Representation learning is a good way to bring together different sensory modalities. We introduced SpargeX, the first self-supervised backbone for multisensory touch. It learns from 4 tactile modalities: images, audio, motion, and pressure from the Digi360 sensor. SpargeX can be used in robot policies, and it improves real-world performance compared to using tactile images alone. It also learns embeddings that capture many physical properties, like material, mass, and dynamic actions. SpargeX is a multisensory touch transformer for general-purpose representations. Each signal, images, audio, IMU, and pressure are processed independently using temporal self-attention. This lets the model pick up the most important information from each modality first. Then, we fuse the signals, allowing cross-modal information to flow through attention bottlenecks. This is where the tactile embedding becomes richer. Some modalities are very good at geometric features, for example, while some others are really good at picking up high-frequency changes like sleep. The bottleneck tokens act as a multimodal summarizer, distilling and exchanging information between the modalities in each transformer block. We train the SparseX with self-supervised learning, in particular a teacher-student self-distillation paradigm. Our data comes from an Allegro hand with D360 sensors doing random motions, for example, rummaging a tray full of objects. We also use a manual picker for doing simple actions like picking, sliding, tapping, placing, and dropping objects on surfaces with different textures and, in general, tactile properties. We design supervised tasks to test what the SparseX captures from play data. We keep the model frozen and train small classifiers via attentive proving. We find that the SparseX can identify materials, surfaces, and motion patterns. In general, using all modalities gives us a boost over tactile images alone. With the SparseX, we're also able to tell solids from liquids. We roughly estimate mass from checking motions. Even with limited data, pre-trained SparseX outperforms end-to-end models.
Touch representations can also help enable tactile manipulation policies to sense properties like friction, mass, and forces. We test SparseX on a plug insertion task using teleoperated demonstrations to train a visuotactile policy. Here, we compare performance between using different touch modalities and using vision alone. Using all modalities with SparseX gives a 90% success rate, which is significantly better than using tactile images alone. In fact, multisensory touch helps catch subtle cues. For instance, audio detects initial contact or collisions, while tactile images and pressure shows forces needed for alignment and insertion. Now, for more dexterous tasks, such as in-hand rotation, robot demonstrations are quite hard to obtain for behavior cloning. A common approach, then, is to train policies using RL in simulation. In-hand rotation specifically is trained through a two-stage approach. First, an oracle policy is trained in simulation using privileged state information such as object position, mass, friction, and the like. Then, the encoder from the oracle policy is distilled into a deployable model using proprioception inputs only. So the idea here is that the adaptation module is going to learn to match the latent state containing object properties using proprioception history alone. This is good at capturing finger contact patterns, but some other properties of the object itself, like friction, are quite hard to recover. It's also unclear why the contact patterns might change. Is it because of mass or is it because of slip? So the question we ask here is, can we use SparseX representations to better approximate the tactile object properties, resulting in better in-hand rotation policies? With tactile adaptation through ControlNet, we can add touch via SparseX to the base policy without retraining it. A zero initialized convolution ensures performance never drops below the original HORA policy, allowing a gradual integration of touch. To train this module, we simply roll out the proprioception policy and collect tactile signatures. Additionally, we perform rejection sampling and save trajectories where the object experiences minor vertical drift and rotates for longer than 30 seconds. Then, we supervise the tactile adaptation module using control error, the gap between the action executed and the policy output. Specifically, we backpropagate the control error through the policy to update only the tactile adaptation module. For example, you can imagine HORA might predict the same finger motion for two cups with different friction. This mismatch reflects in the tactile properties that proprioception alone can't capture. We compare the robustness of the original HORA policy with HORA plus tactile adaptation under reduced object friction. With SparseX, combining all tactile modalities, the adapted policy adjusts its finger motion to compensate for the lower friction. This keeps the object stable and prevents it from slipping for longer. Finally, we note that HORA is usually trained only with the hand pointing upwards in simulation. To stress test tactile adaptation, we flipped the setup and rotated the object against gravity with the hand facing down. With SPERSHX, you can see that tactile adaptation shows much greater robustness to these post-perturbations compared to the original policy. To wrap up, here are the key takeaways. SPERSHX is a self-supervised backbone for general multisensory touch. We trained it on Digit 360 data, but the approach can extend to other sensors and modalities. SPERSHX captures physical properties, letting us identify objects, actions, surfaces, and even estimate intrinsic properties and forces. Finally, SPERSHX enables stronger policies. In imitation learning, it improves performance by 63%, and with tactile adaptation, it improves robustness by 90%. Check out our papers on our website. Thank you, and we're happy to take questions.
Do we have questions from the audience? Okay, I have a question. So it seems for the design of the model, the key assumption is that the multisensory data is sufficient for you to recover all the privileged information for you to actually do the policy learning. So I'm just curious, have you ever quantified the contributions of different modalities? Like which one is more important, which one is less important? If you have to remove one, one might be the least important ones.
Yeah, I think that's a great question. So in the paper, we have ablations where we're looking at different modalities separately, and we quantify the performance where we're essentially saying that if you add, say, audio and like pressure signals, like that would give you like slightly worse performance compared to having all the modalities together.
Okay, sounds great.
Thank you.
Yeah, thank you. Let's thank the speaker again. The next presentation will be from William for his work on training strategies for efficient embodied reasoning. Please take it away.
All right. Hi, everyone. My name is Will. I'm a PhD student at UC Berkeley. And today, I'll be presenting training strategies for efficient embodied reasoning. One long-standing goal of robotics is to develop generalist robot systems, ones that can perform a wide variety of tasks in a wide variety of unstructured environments. To that end, a popular recent approach has been to train vision language action models, or VLAs. These are policies that take a powerful pre-trained vision language model and fine-tunes it on a vast amount of robot demonstration data. Now, this approach has been pretty successful as of late, but it does have some downsides. Namely, unlike in vision and language, high-quality robot demonstration data is quite scarce and expensive. Because of this, last CORL, my co-authors and I presented an orthogonal method for improving VLAs. Rather than scaling the demonstration data, we instead proposed to train on embodied reasoning data. Specifically, we trained a policy to auto-regressively reason before choosing an action. This so-called embodied chain of thought contains high-level plans, low-level motions, and grounded visuosemantic features such as bounding boxes. Because all these features are helpful for choosing actions, the overall policy ends up performing better than the equivalent standard VLAs. Now, this is glossing over something. While embodied chain of thought does improve policy success rates, it does so at the cost of needing to generate around 300 or so text tokens per time step. This naturally has a negative impact on the overall inference rate of the policy. Comparing to past popular VLAs like OpenVLA and RT2, they both have inference rates of around 4 actions per second, all right? And then we have embodied chain of thought. It has an inference rate of 4 seconds per action. That's like really slow, right? Like running the evals through this paper was like really, really painful. And like big shout out to my co-author for putting up with that. So needless to say, the robot learning tasks of today require a lot more dexterity and therefore higher action throughputs, making embodied chain of thought sort of performant but kind of impractical. This leads us to the question of how can we benefit from robot reasoning without the inference time costs? In this paper, we present embodied chain of thought light as an answer for this. These are simple methods for training on embodied reasoning data, but not generating them at test time, thereby seeing a performance boost, but without the slowdown. In order to design these methods, though, we needed to answer the question of why does embodied reasoning help robot policies in the first place? After all, the answer to this question basically tells us how we should be making use of this data. We put forth 3 simple hypotheses for this. First off, in learning to reason, the policy's representations are improved since they're shaped to contain important features like the locations of objects or robot plans. If this is the main important factor contributing to the performance boost of reasoning, then what's important is simply learning to generate reasonings, not necessarily generating them at test time, since by then they've already helped improve the policy's representations. Next up, reasoning acts as a sort of learning curriculum, in that it contains the important features for choosing actions which the policy otherwise must learn from scratch. We can test this out by using reasoning as a sort of scaffold for learning, that is, providing them in context during training and then removing them during inference time. This is different from representation learning in that the policy never learns to actually predict reasonings. Instead, it's more akin to teacher-student learning, wherein the policy receives privileged information in order to guide its learning, but must learn to act without it during deployment. Our last hypothesis is that reasonings improve policy expressivity. A transformer that has a bunch of in-context tokens can actually learn a more complex mapping from input to output. It's sort of like widening the layers of your neural network. So this is actually a pretty common reason given for why reasoning benefits LLMs, with some authors even showing that if you just give the LLM a bunch of meaningless thinking tokens, it can actually improve on some tasks. We thus adopt the exact same approach. Basically, we replace our reasoning with an equivalent number of thinking tokens, thereby improving policy expressivity without actually teaching it anything semantically new from reasoning data. In order to test all of these approaches, we devise simple variants of the core embodied chain of thought recipe, which isolate each one. We then test all of them in the Libero 90 simulated manipulation environment, as well as both a standard VLA and embodied chain of thought VLA as baselines. I want to stress, for all of these approaches, we were sure to control for as many factors as possible. They're all trained on the same data, the same compute, from the same base models, they even use the same task seeds during evaluation. Thus, we could be sure that any performance differences we observe come from our 3 hypothesized mechanisms. After running over 100,000 evaluations in Libero, we found that the representation learning approaches were by far the best. They universally outperformed the standard VLA and almost matched the performance of full embodied chain of thought, despite being a ton faster. In particular, the approaches that worked best were reasoning pre-training and reasoning dropout. These are what we're calling our new embodied chain of thought light methods. So let's go over them now. Also, I'm very proud of these animations. Okay, so first off is reasoning pre-training. In this one, we take the policy and train it just on reasonings first. Then, we transfer that checkpoint and train it just on actions. Next up is reasoning dropout. In this one, it predicts the reasonings and actions in sequence, but we sometimes drop out the reasoning during training. This means that the policy learns to predict actions whether or not it reasoned beforehand. In order to validate that these approaches were practical, we replicate them in the real-world Bridge WidowX setup. And sure enough, we find that our 2 new methods similarly outperform the equivalent standard VLA while being 16 times faster than full embodied chain of thought. I want to end off on some high-level prescriptions for when you want to use each of these methods. So, first off, embodied chain of thought is still the best performance, but of course it has to generate a bunch of stuff at every time step. While you can speed it up with techniques such as VLA compilation, it's still by default going to be the slowest one. Next up is reasoning pre-training. This is a pretty safe and flexible option since it can actually consume arbitrary embodied reasoning data, including ones that aren't paired with actions. The downside here is that you have to wait for more total training gradient steps, since you have to train first on reasonings and then on actions consecutively. The last one is reasoning dropout. This one provides the unique option to toggle the reasonings off and on during test time, meaning if you want to use it as a standard reasoning policy at the cost of inference speed, you totally could. The downside here is that it requires the same amount of training compute as a full embodied chain of thought, because for each data point, you have to include both the reasoning and the action in context at once. To summarize, these two approaches comprise embodied chain of thought light. They share the commonality of basically learning better representations from embodied reasoning data, but not generating them at test time. This means that they are more performant than a standard VLA while having the exact same inference speed. We hope that these methods will be simple, effective, and practical ways to adopt embodied reasoning into robot learning. I want to give a quick shout out to all of my co-authors at Berkeley, Stanford, and Physical Intelligence, and for all of you guys for watching. And if you're interested in learning more, that's the poster section and the website. Thank you.
Do we have any questions from the audience?
Also, if you do have a question, can you raise your hand so I can see you?
Okay,
Hello.
there is one, yep.
Yeah. Thanks for the talk. I was wondering, so you proposed sort of two training methods for this. Do you propose doing one or the other, or do you do both at the same time? Like, is there any difference?
Yeah, so basically from that last slide, right, it entirely depends on which set of options sound attractive to you, right? So if you have a lot of unpaired embodied reasoning data, maybe from like just videos of robots or something like that, then you should be using reasoning pre-training. Whereas if you instead want the option to be able to generate reasonings or not generate reasonings, then you should be using the other one. Sort of think of it like a flow chart based off of what you want, what your compute situation is, stuff like that.
Okay, thank you.
Let's thank the speaker again. Next, we will have Amber presenting us their work, Data Retrieval with Importance Weights for Few Shot Imitation Learning. Please take it away.
Hi, I'm Amber Z, and I'm here to present our work, Data Retrieval with Importance Weights for Few-Shot Imitation Learning. This is joint work done with collaborators at Stanford, Rahul, Dorsa, and Joey. How do we teach a robot a simple task like move the carrot to the dish rack? A popular approach has been imitation learning, where we optimize the objective, on the left, the behavior cloning loss. This loss here is to imitate the expert actions under the distribution of our collected target data, p-target. However, to generalize for a simple task, we still may need to collect dozens or even hundreds of demonstrations, which is extremely time-consuming. Instead of collecting a new dataset for every single task, can we use the existing data out there? More and more, we're seeing the aggregation and collection of such large, diverse datasets. For example, for this carrot to dish rack task, we notice that there's an existing prior dataset, Bridge v2. And in fact, some of this data may actually be quite helpful. We notice that the carrot is present in a lot of this prior data, and learning to grasp and move the carrot could be useful for the task we want to accomplish. This allows us to reduce the number of demonstrations we need to collect. Then, with this retrieved data, we can co-train on a mix of our target task and the useful diverse prior data. To do so, we optimize a weighted behavior cloning objective. First, we optimize the behavior cloning objective for the target data and also for the retrieved data. We weight this with alpha, which is typically just held at 0.5. However, what exactly is p-retrieved? The way retrieval methods typically retrieve data is first, they perform representation learning over the large prior data set. This allows us to learn a latent space, which we then embed target and prior data. In order to select the prior data which is useful for our task, we look at the nearest neighbors of our target data. For example, in this instance, Z1 is retrieved and Z2 is not. More concretely, this can be represented as such, where for each prior point, we find the nearest target point and retrieve it if the L2 distance is less than a certain threshold. Let's revisit the weighted BC objective. Here we're optimizing both the BC loss for the target distribution and the retrieved distribution. But what we really want is to optimize it for this top one, which is the expert actions under the target distribution. What we notice is if we look at an importance sampling equation, we can instead sample from p-prior, our large prior data set, and weight the samples with this important weight. Our key insight is using these importance weights as a threshold for retrieval instead of L2 distance. This requires us to model the probability density function of both the target and the prior data. Let's take a look at a toy example to see how this works. This is the L2 retrieval rule. And here's an example of some target data in orange and some prior data in gray. In this case, we may hope to retrieve X because it bridges this gap between the target data on the left and W, whereas Y might be less optimal to retrieve. L2 distance will calculate the distance between each prior data point and its nearest neighbor. Here, Y will be retrieved because it's closer to the target data point. However, in our paper we discussed this more, but this can also be interpreted as modeling the target distribution, the distribution of orange points, with very peaky Gaussians. In this case, we would retrieve the gray data point on the right because it has higher density under this distribution, although it is very peaky and noisy. If we look at our importance weighted retrieval rule, we are instead looking at the ratio of the probability of our prior point under p-target over p-prior. Here, let's assume our prior data point is distributed uniformly, so let's look at the numerator. What we do is we use Gaussian KDEs to model the distribution of target points. This might look something like this, and here for each prior point, we'll calculate the probability under that distribution, and here X will be retrieved, which might be more optimal. Why does importance weighted retrieval work? First, we perform a smoother type of retrieval because we're modeling p-target with a smoother distribution instead of the peakier L2 retrieval. Second, we're hoping to reduce bias by using the importance sampling equation, which helps us optimize the objective that we actually care about, which is imitating expert actions under the target distribution. Once again, this is what our retrieval recipe looks like. The representation learning is held constant. Once again, we embed our data into the latent space. And instead of looking at L2 distance, we will model the distribution of target and prior data and calculate the importance weights and retrieve based on the value of the importance weights. In this general retrieval recipe, there's typically 3 steps: representation learning, the actual retrieval process, and co-training on the retrieved and target data. Importance weighted retrieval only modifies this middle step, making it a very simple but effective fix. How does IWR perform empirically? We evaluate on a suite of simulated tasks and real-world tasks. Again, prior retrieval baselines focus on how to learn this latent space, making IWR amenable for each of these baselines. For example, behavior retrieval learns a latent space based on embedding the state and the action. As you see, the dotted line represents the BC performance, which doesn't use any retrieved data. Behavior retrieval is able to outperform this baseline, but when we instead use IWR for retrieval, we see a jump of 21% across all tasks. Second, flow retrieval is another baseline which learns a latent space by embedding optical flow. Once again, averaged across all tasks, we see an improvement when retrieving with IWR. Cellular retrieval learns a skill-based embedding space, and again, we see an improvement of 9%. Here's an example of a real-world task we do. This is a long horizon task which first requires moving the eggplant to the bowl and then the bowl to the dish rack. We see that IWR is able to accomplish this task, whereas the other 2 baselines are unable to. For this task, there's a huge jump in success rate of an improvement of 40%. Does IWR retrieve better data? In this simulated experiment, we categorize prior data into 3 categories: harmful, miscellaneous, and relevant. IWR is able to retrieve more relevant data and less miscellaneous and harmful data. Some limitations of our work include smooth latent spaces. All the prior baselines use VAEs to learn this embedding space. Second, the tasks are still relatively simple. which makes future directions exciting to focus on larger, more complex, more dexterous robot datasets and tasks. And also, because we're modeling the distribution with Gaussian KDEs, learning a way to better estimate the importance weights. As a summary, importance weighted retrieval makes a simple modification at the retrieval step. We estimate importance weights, and this leads to smoother retrieval estimates. Thank you.
Any questions from the audience? I can ask one question. For example, currently we see that the performance of the model still has significant gap towards 100%. Do you see that's an issue of the quality of the retrieved data, or maybe some actually useful data hasn't been retrieved?
So could you repeat the last part of your question?
Okay, so the question is like, given the performance gap, is the reason mainly because the data quality itself is bad, or because there might be some good data, but just this procedure hasn't really been able to identify those data yet?
I think it depends on the type of prior data set you have. For the bridge data set, I think it could just be not retrieving enough of the useful data. Yeah.
Okay, sounds great. Thank you so much.
Thank you.
Next, we'll have Samantha presenting their work on core sensor touch generations. Please take it away.
Good morning, everyone. I'm Samantha. This work is a joint work with Jimin Du, my co-author, Michael Oler, Andrew Owens, and Nima Faseli. In this project, we investigate if it's possible to transfer tactile manipulation skills across significantly different visual tactile sensors. This is important because of three main reasons. The first one is that tactile sensing is critical for manipulation tasks, especially when the object of interest is highly occluded. The second reason is the lack of standardization across visual tactile sensors. There exists a lot of visual tactile sensors, and all of them have different shapes, size, and compliance. Finally, due to this lack of standardization, there is the need to create methods that are specifically designed for each tactile sensor, even when the task is the same. Previous work have investigated generalizing manipulation tasks across visual tactile sensors. However, most of them focus on using latent representations. There has also been work on generating tactile images, but these images are mostly generated conditioned on vision. Finally, recently there has been some work on generating tactile images from conditioning on other visual tactile sensors. However, in this case, their ability to transfer manipulation tasks is still underexplored. What we propose is to use cross-sensor tactile image generation to transfer manipulation task skills across visual tactile sensors. First, to do this, we focus on data collection. For data collection, we choose two main sensors. The first one is GelSlim 3.0, and the second one is the bubbles. These two sensors are significantly different, as you can see. What we do is that for the data collection, we create a paired data set where we collect data that keeps the key geometric features of both sensors and pairs each of them. What we do is that we use a latent diffusion model to produce the target sensor image conditioned on the source sensor image. How we evaluate it is by transferring manipulation tasks. In this case, is cup stacking task. It consists of first picking up a cup, then we use the bubble post estimation algorithm and to help reorient the cup, and finally we stack the cup. Our goal is to transfer this task that was designed for bubbles to GelSlim sensors using tactile image generation. Overall, the evaluation consists of grasping the cup with a GelSlim sensor, using our model to generate the corresponding the corresponding tactile image of how it will look like if the bubble sensor was the one touching it. Once we generate this image, we are able to zero-shot implement our bubble pose estimation algorithm and then finalize the stacking task. Besides the task, we also tested our generation in insertion tasks on unseen tools during training, and we can see that overall our method outperforms the baseline, and in average it has an increase of 20% compared to the baseline across tasks. But what happens if we don't have paired data? Since paired data is really expensive to collect, we also offer another approach, and this approach uses synthetic depth as an intermediate representation. Here you can see the tactile signals and their corresponding depth maps. What we do is that we transform the synthetic depth to 3D space to relate the source sensor to the target sensor without the need of paired data. We call this approach T2D2, touch to depth to touch. This approach is modular and consists of three main parts. The first one is touch to depth, where we have a depth estimator module that is used to estimate the depth map from the source sensor. Then we have the depth adaptation step to go from the source sensor depth map to the target sensor depth map. And finally, we have the depth to touch model, where we have a latent diffusion model that is used to generate the target sensor image condition on the depth map. How we evaluate this transfer is in a marble rolling task, where we wanna the way this task works is that we train a behavior cloning policy where the initial state of the marble is placed randomly, and the goal is for the marble to get at the center of the image. This policy is trained on the jostling sensor, and we want to transfer it to the digit sensor. Here you can see we have the digit sensor. We get the tactile signal from this sensor. It goes through our method, and we generate how it will look like if it was the jostling sensor, and we zero-shot our jostling policy without any fine-tuning, and we are able to perform the task. This task achieves success 15 out of 20 times. Now we can compare these approaches. We can see that both are capable of generating the target sensor image condition on the source sensor image. However, direct touch-to-touch using paired data achieves higher results on qualitative and quantitative image generation metrics. Now, when should we use T2T versus T2D2? T2T should be used when you have access to paired data and when the downstream task does not require high-fidelity tactile generation. However, T2D2, you can use it when paired data is not available and a slightly lower tactile generation quality does not affect the task performance. Thank you, and please come to the poster.
Do we have any questions from the audience? So I can ask one question. So when you do this touch-to-touch transfer, do you implicitly have to make the assumption that they contain the similar set of information, which might not be true? For them, the gel sites, when you have the dot patterns, it measures the shear force. But for the soft bubble, where you don't have the patterns, the shear is not as obvious. So can you maybe talk a bit more about the assumptions behind this touch-to-touch transfer?
Yes, so one assumption is that what we are looking to transfer is the key geometric features. So in this case, the data collection, how we define what alignment is, what is pair, is what allows us to generate the images good enough for quasi-static manipulation tasks. Thank you.
Thank you. Any other questions? I think maybe I can ask another one. So for the later ones, you are essentially using this geometric information to do this kind of coarse model or coarse sensor, like as this unified representations. So I'm curious, for example, in this case, like how how much information does it actually capture? For example, for the gel side, it covers the shear, but the geometry doesn't really measure those kind of shear informations. Like, can you talk about, for example, are there any information that is missed by only using geometric information as these intermediate representations?
Yes, by only using the geometric information, we are missing information about how the contact is generated. So in this case, we limit our method just to quasi-static because of that. In the future, something we would like to explore is to generation of shear map, and also like force estimation to see if in this way we can generalize more tasks.
Sounds great. Let's thank the speaker again. Next, we will have Chen Yang presenting to us their work on latent theory of mind. Please take it away.
Okay, thank you. So, hi everyone. My name is Chen Yang He. I'm very excited to have this opportunity to present our work here entitled Latent Theory of Mind, Decentralized Differential Architecture for Cooperative Manipulation. Before I begin, I'd like to once again thank Professor Schreger, Professor Sadoretti, and all our collaborators for their help. So first, I'd like to highlight the practical importance of decentralized multi-robot systems. So on the left, the examples show centralized systems, a warehouse logistics setup, and a BMW car production line. In such factory-level tasks, centralized coordination is efficient and precise, enabling multiple robots to collaborate reliably. However, on the right, you can see the centralized methods face challenges. Remote city-scale autonomous driving cannot rely on a single controller. Similarly, the recent Figure AI and BMW demo showcased human noise. Oh, okay. So, working in a decentralized fashion across factory floor. So these cases illustrate why decentralized approaches are crucial scientific direction. So yet, current decentralized methods remain limited in cooperation, as most of them follow independent learning paradigms, which, where robots can finish their own job, but lack the true collaboration ability, actually. So here are 4 methods for multi-robot systems cooperation. The first one is independent learning. Each robot just learns its own, task and treats the other agents as part of the environment. It is simple, but usually leads to really weak cooperation. The second one is centralized critic. This gives a strong cooperative signal and usually improves the coordination level, but it depends on the centralized training, which is not always realistic. And the third one is credit assignment. This directly tackles the problem of splitting the team reward across individual agents. It is very powerful, but methods like QMX and VDN don't scale well, since they often need to be retrained if the team scale changes. And the last one is communication learning. So the cost is, in a lot of methods, you need to use the bitwise to make sure they can communicate with each other. Based on the background we just discussed, let me introduce our method, Latent Theory of Mind, or Latent TOM. It is a decentralized different policy architecture for cooperative robot manipulation. The idea is that each manipulator has its own perception and computation, yet they can still coordinate toward a shared goal, with or without direct communication. You can think of it as combining the strengths of independent learning, centralized critic, and communication learning. The benefits are clear. So potential better scalability, real-time decision-making, and an explicit cooperation mechanism. But due to the hardware constraints, in this paper, we focused on the case of 2 manipulators. That's the reason I put the potential scalability here, not just our good scalability. So, yeah. Here is the Latent TOM's architecture. Our key innovation lies in allowing each agent to maintain 2 latent representations, an ego embedding specific to the robot and a consensus embedding trained to be common for both robots. Despite their different sensor streams and poses. To make this work, we use consensus laws to align the shared embeddings and add extra constraints inspired by the theory of mind plus a directional consensus mechanism to make them expressive enough. So, and most importantly, when we run the model, it works in a fully decentralized way. The manipulators don't need to explicitly communicate with each other. They can, I mean, this is an option, but not compulsory. So to make the robots reach a common understanding, we first use a consensus loss, which is actually a first-order cohomology loss to align their consensus embedding in the numerical aspect. But if we only rely on this stuff, the consensus might collapse into something that's meaningless. For example, instead of focusing on the factory tasks, the robots might just agree on going for burgers tonight. I mean, this is just an example. So clearly, it is not helpful for the collaboration. So we added 2 extra constraints. The first one is this one, the theory of mind constraint, which where each robot use its shared embedding to guess the other's private embedding. This focuses on the shared representation to stay informative and avoids the trivial solutions. And the next one is an directional consensus mechanism where we are expecting that the more confident robot will guide the embedding learning of the less confident robot. So to make the system more stable, we use one-round communication which is also known as shift Laplaceing. You can think of it as a post-processing fine-tune method to make sure they align with each other. But the downside is that this method requires the arms to talk with each other once before they make the decision. So this adds some communication overhead. Next, we have 2 types of tasks, the in-distribution and out-of-distribution. This is the out-of-distribution task because we changed the friction coefficient of this T-shaped block. So here are some results. So the first one is CDP, the centralized different policy. The second one is the naive decentralized different policy. And this one is naive consensus decentralized different policy, which means we only use the consensus learning without any constraints. And here are our methods. And this is the final one is the method with shift Laplaceing. And here are the quantitative results. So, and this is our in-distribution task, which requires 2 manipulators to collaborate to transfer coffee beans from one container to another. So this shows the same trend as our previous OOD results. You can see Latent Tom and Latent Tom with communication can perform much better than the NDDP and NCDTP. So here are some quantitative results of the in-distribution task. And finally, this is our data collection pipeline, which is a motion capture-based system. We designed this to minimize costs, and in the end, we are able to collect data without any additional costs. Thank you for your attention.
Do we have any questions from the audience? So I have one question about the scalability of your method. Okay. Because at the very beginning, you use examples where there's like hundreds of robots that are working together. But in your experiments, there are just 2 robot arms. Oh, yeah. So I'm just curious about, for your framework, how scalable it is to maybe like a larger scale environments or larger scale like robotic systems.
Okay, thank you for your question. This is, so at the beginning, our problem is the hardware constraint because we only have 2 arms. But so ideally, what we are expecting is if all the robots do the similar task, for example, they pass something, in that case, we can use the same data. So for example, you train on only 2 arms, and then based on this kind of data, you can deploy all this kind of arbitrary policy in all the robot arms. In that case, we are expecting it can perform better in the scalability aspect. But we actually need to try this in the future.
Sounds great. Let's thank the speaker again.
Yeah, thank you.
Next, we'll have the presentations of RoboArena. Please take it away.
Hi, everyone. I'm Pranav. Excited to be talking to you guys today about RoboArena, our new benchmark for generalist robot policies. So the problem that our work tackles is that of generalist policy evaluation. So generalist policy evaluation is particularly challenging because in the limit, a generalist policy can be commanded to do arguably anything in any scene. So to accurately assess a policy's capabilities as a generalist, you kind of have to take the robot to a very wide array of locations and a large set of scenes, and basically cover the set of tasks that an end user might ask of said generalist policy. So the way policy evaluation typically proceeds in most papers today is that the paper authors will pit their policy against the baseline and the baselines against a set of M evaluation tasks that they've curated, exhaustively evaluating all policies against all tasks. And they take care to exactly match the initial conditions for each task across evals. Now, some problem points with such an approach is hard to enable reproducibility across time and locations. So say 5 months from now, a new paper wants to exactly replicate the evaluation setup of one of the baselines. That's going to be very difficult to do. Authors also typically both decide the set of tasks and evaluate their own policies, which isn't the most ideal setup. And perhaps most critically, for generalist policy evaluations, you really need to scale M, the number of tasks that you evaluate on. And this is something we show and I'll discuss later in the presentation. And it's very hard for one institution to pull together the resources to really scale diversity to this level. Now, taking a look outside at broader ML, one thing we'll notice is that evaluations are shared. And this is actually unlike evaluations typically in robotics, where evaluation setups are usually bespoke. And such evals, like the ones shown here, are shared because they define a shared problem statement. And arguably, several shared problem statements exist in robotics too, one such being that of generalist policy development. But arguably, one potential reason for why we haven't had a similar sort of shared benchmark for this statement has been that generalist policies until recently have been kind of nascent. In that it's very rare, again, until recently, to be able to train a policy in one lab and take that policy, deploy it on another robot, and have it do non-trivial things, zero shot, when commanded with language. So with the increased generality of modern generalist policies, we asked the question, is there an opportunity for a new type of benchmark? So I'll outline some of the design decisions of RoboArena now. The first is to not standardize tasks at all. Instead, letting evaluators freely choose the task for each and every single evaluation. And this is actually, again, permitted only by the generality of these new generalist policies. To actually obtain some sort of signal about whether one policy is better than another, we do evals in A/B fashion and ask the evaluator to mark their preference over which policy they preferred. We crowdsource, so we scale this up to as many number and as much diversity as possible across a distributed network of institutions. And we make evaluations double-blind to ensure fairness. So I'll walk you guys through what one A/B eval looks like. So an evaluator will take the robot setup and park it in some location that they want to and command some language task. And the evaluator will be given two policies sampled at random from the policy pool, and critically they won't know which policies they're evaluating. So they'll basically roll out policy A on this task, and in this case the policy didn't do super well, so the evaluator marked a partial success score of 50%. Then they'll replicate the initial conditions of the scene to exactly what it was for policy A, and they'll run the they'll run policy B now on this task. So as you guys can see here, the policy is actually decent at wiping the table. So the evaluator marked a partial success of 100%. And now in addition to this, they'll also mark their preference for which policy they liked better. And critical here is that the preference may not always match what these partial success scores have mentioned. In that it's very possible, for example, for two policies to both solve the task, but the evaluator to still decide to mark a preference. Maybe because one policy was safer or it was more smooth. And the last step is we ask the evaluator to provide long-form textual feedback about why they liked policy A or policy B. And when we replicate this at scale across our entire distributed pool of evaluators, we end up with something that looks like this. Basically a data set of preferences that we now need to use to obtain a ranking over all the policies. So to actually do this, we start with the standard Bradley-Terry model, which models the probability that a policy is better than another policy by the sigmoid of the difference of their log ability parameters. Now, in robotics, we're not actually pitting two policies against each other directly, but rather we're pitting each policy against the same task. So we'll take this into account by doing basically exactly that, introducing task-specific parameters, and we say that policy A is better than policy B if policy A solves the task and policy B does not solve the task. And finally, we add one extra set of parameters here, psi, which basically account for the situation where on certain subsets of tasks, a policy may be better than another policy, but another subset it may be worse. So with the previous model, it's basically impossible to obtain a total ordering, but with this addition of a new set of parameters here, we actually can. And finally, we just fit the model with standard MLE. And these theta parameters are what we use for the final ranking. So some implications of the design in RoboArena. A lot of evaluation criteria beyond success rate can actually be captured by this preference data. Like the preferences could include safety, smoothness, etc., which is very useful to record. Factors that used to plague reproducibility of setups pretty much go away, because reproducibility now is only required across policies A and policies B, which are basically co-located in time. So it's very easy to maintain reproducibility here. The benchmark evolves with the policy capabilities. So something we found when we ran this experiment is that as we introduced more competitive policies, evaluators started to command more difficult things for the policies to do. And also RoboArena is robust to organizational challenges. So if like one student graduates, the benchmark will still live because there is a distributed evaluation network. And one other implication is that the community decides what a generous policy should be able to do. And arguably, this is how it should be. Like if I were to write down the list of all things I would want a generalist to do, you guys would maybe not agree with that. But as generalist policies evolve, it definitely does seem the case that the community should decide what a generalist policy is and how it should be evaluated, and that's exactly what happens with RoboArena. So now we instantiate this idea on Droid, and we choose Droid because there's an existing dataset, the Droid dataset, that enables policies to work out of the box zero shot. So across 7 partner institutions, we collected over 4K evals in just a couple of weeks, and we measured the diversity, and we found that actually the diversity scales really well. Because we have this distributed evaluation setup, we collected, for example, here over 80 unique task verbs, like pouring, wiping, and 570 unique objects in just this 2-week period. And finally, we also get better rankings. So let me expand on this a little bit more. So here, regular is what the standard evaluation approach might look like, and is the evaluation approach used primarily in prior by most papers, wherein one institution tries to set up a set of tasks, and they evaluate their approach and the baselines on all tasks. And blue here is RoboArena. And we find that within a couple hundred evaluation episodes, RoboArena rankings converge pretty closely to the Oracle. And the Oracle here is basically uses our entire distributed evaluation network and exhaustively runs all policies and all tasks. And it's actually K times more expensive than RoboArena, where K is the number of policies. So if we have like hundreds of policies, it's a really good idea not to do this Oracle type of evaluation. So if you guys remember, we also asked evaluators to give long-form textual feedback. So we explored whether we can use like current state-of-the-art AI models to basically aggregate this preference feedback into AI-generated automatic policy-specific weakness and strength reports. And we were successful in doing this. This is an example of some of the reports, and you can take a look on our website. And they also have video references to specific trajectories that you can take a look at. And to end things, I wanted to highlight one of the things that I thought was most interesting about this project, which is the diversity in the tasks commanded. So I often found it very useful to look at the evaluations that were done by our entire pool of evaluators and just see the types of tasks they were commanding. For example, on the left here, make a bowl of watermelon slices for dessert is the task, and on the right is hide the red ball. And I think looking at these evals gives you a lot of insight into what people ask of generalist policies, but also what policies can't do today. For example, for hiding the red ball, the policy needs to do some sort of reasoning of maybe like the best place to hide the ball is underneath the cup, but the current policy is not able to do that. And yeah, the benchmark is still open, so if you guys are working on generalist policies, I would encourage you guys to fine-tune it on Droid and submit and get your policies evaluated. And we have evaluations pretty much going every day, thanks to a very generous pool of evaluators. And I'll also be at poster number 77, and I'm happy to take any questions. Thank you.
Apologize if I have missed any audience question, because it's very hard to see from the stage. If you have questions, it's better if you can raise your hands. That'll be easier to see from the stage. Any questions from the audience? Please, Jeanette.
Thank you. Okay, I have a bunch of questions. So first of all, I really like that this is not task related, the evaluations that you do. But it seems like it's still very hard to reproduce exactly the conditions per trial or rollout that you do. How do you help the evaluators to be good at this, right? Like especially with the example you showed, it was a deformable object. I mean, that's really hard to reproduce exactly. What did you find there, and like how you can make that easier? How close do you have to be in all of this?
Yeah. So yeah, conditions only need to be reproduced within just 2 evaluations. So the convenience script that we give for the evaluators shows them an image of what the state of the world looked like further at the beginning of policy A, and sort of ask them to exactly adjust the objects to match that.
Okay, and so did you find you have to filter out some of these results when you look at the images and they don't really match well enough, or how do you make that call?
Yeah, I don't know, maybe we were blessed with a great set of evaluators, but we didn't have to really do anything like that. Yeah.
And so I'm wondering, now that you've done this for a while, how many evaluators do you think you need to really make that viable for maybe the entire CORL community, for example?
Mm-hmm. Yeah, so we explored how many evaluations it would take for us to be reasonably confident about the ranking that we end up getting. And what we sort of experimentally found out was that on the order of 100. So actually, with the current set of evaluators, it's reasonable. We are able to get to the number, but of course, the more the better. I think if we can get to for example, a few thousand evaluations, I think we can be reasonably confident about the final ranking of our policies.
Yeah. What if we, instead of having places that do large-scale data collection, also do large-scale evaluation?
I think that's a good idea. I think data collection and evaluation are very similar problems and require very similar resources.
Yeah, might be great if you had that.
Okay, let's thank the speaker again. This concludes the oral sessions for this morning. Next will be the spotlights. Please stay around.
Okay, it's time to start a spotlight session, and then speakers, please line up the front rep. As you know, the coffee break is coming, right? So let's start spotlight session as soon as possible. So let's welcome the first speaker. Woo.
For years, the spotlight has been on control policy, but what if the hardware itself can be learned? We show how soft-grade and control policies can be co-optimized from data. We derive a uniform tendon routing model so that the finger can deform to any geometry. We sample a wide range of policies and design parameters in simulation, generating ATK data over a wide range of objects. Then a neurophysics model is trained to predict grasp outcomes, and with this differentiable model, both design and policies are tuned automatically. Our optimized design is more adaptable than the rigid ones, and it can be compliant yet strong enough to bear high loads. And interestingly, our final design is symmetrical. One finger differs like a thumb, and the rigid tips that work like human nails. Thank you.
today. So Opal is a framework for large-scale localization that bridges LiDAR, sensing, and OpenStreetMap data. Existing methods for localization often rely on expensive or heavy resources like dense point cloud maps, which are hard to build and maintain. OpenStreetMap offers compact and free alternative, but aligning with LiDAR is challenging due to modality differences and occlusions. Opal solves this with visibility-aware and radio fusion design, allowing reliable single-frame LiDAR localization in complex environments. And then we present a demo of the localization results on the Kitty dataset. Predictions with localization errors within 5 meters are marked in green, while those exceeding 5 meters are shown in red. In conclusion, Opal makes cross-model single-frame localization feasible, fast, and accurate. Thank you.
Hi all, my name is Hui Zhang, and I'm glad to be here to share our work RobustX Grasp. It can robustly grasp more than 500 real-world objects and perform continuous grasping without a single failure. And it can generalize well across various object properties like the challenges small and thin objects, large and heavy objects, deformable objects, and transparent objects. And it shows great robustness even under the disturbances like external forces, random object poses, unexpected object rotations, and the random lighting conditions. It further supports different applications like grasping under cluttered environments and playing chess games with human, and grasping moving objects or cleaning up a table. Please come to our poster for more information. Thank you.
Hi, my name is Han-Jung Kim. I represent our work, Uniscale. Uniscale introduces a universal scale representation learned from large-scale videos dataset. This embodiment agnostic representation enables robots to imitate human videos directly. Uniscale has 2 components, an inverse scale dynamics model that encodes cross-embodiment scale representation, and a forward scale dynamics model predicts future frame based on that scale. Our scale representation lets robot to follow the task in a video prompt. Even when a video prompt is human, Uniscale executes the task across embodiment. Moreover, based on our scale representation, Uniscale predicts multiple plausible futures from the same state. Also, given the same task from different embodiment, Uniscale predicts multiple futures. Thank you. Please visit our poster number 26.
Everyone, Casper is a robot sidekick that shadows your day, decodes your intent, and lends a hand while you stay in control. Now, given a human teleoperation input, Casper will predict your intent on the fly. Upon user confirmation, it will fulfill the task autonomously. Now, the human can relax in the meantime while the robot completes the task. Upon completion, the control will be passed back to the human. Now, sometimes the human's intent might be unclear. In those cases, Casper will hold off the prediction until it is more confident. Using such a system, Casper enables humans to achieve long horizon and diverse tasks with ease. Thank you. Please visit our poster session 45. This was a great work led by Hui Han from our lab. Thank you.
Hello everyone, I'm Lee from the University of Hong Kong, and I'm here to present our work Hypertester. Robotic manipulation demands flexible perception, yet most methods treating extracting a representation part like a uniform part. However, inspired by some findings in human cognition, we present Hypertester, a hypernetwork-driven framework that modulates scene representation based on task objective and task progression. Specifically, we employ a hypernetwork and an autoencoder for representation transformation. Experiments in both simulation and real world demonstrate performance improvement. And through some attention visualization, we demonstrate that our approach selectively prioritizes the task-relevant scene information. Yeah, please visit our poster 65. Thanks.
Hello everyone, I want to introduce our work FastUMI. FastUMI is redesigned based on the UMI with hardware decoupling for broad, robust adaptability and software-driven efficiency and robust ecosystem to get the high data quality. And this guy use our device to pick up to collect the data in the task of pick up the cup. Next, we will show up. We also open resourced 10,000 data for different scenarios. So in this task is open the container. Maybe okay. I think. I don't know why it stopped.
It's okay. You can explain more.
Okay.
The video is going.
Oh, I don't know why.
But we believe we can enjoy in post-session.
Yeah, the FastUMI data will bring some challenges for algorithms. So in this work, we designed lots of algorithm adaptation, and we build on the FastUMI device. We also set up a new setup and sell our device. It is a professional tools and have the world-leading precision. Thanks for watching.
Thank you.
Hi everyone, I'm Yitang Li. I'm very happy to be here to introduce our work, Hold My Beer. Nowadays, humanoid can dance, can box, but can it simply handle a plate of chips without spilling them? Actually, it's very hard for humanoid to do robust locomotion and effector stabilization at the same time. So Hold My Beer. We propose a slow, fast to agent RL framework to tackle this problem. You can see with our method, the red bottle is much more stable than the baseline, the yellow one. And also, our humanoid can serve as a camera stabilizer. It can shoot a long, smooth, and less shaky videos compared to the baseline. Also, under fierce disturbance, our right hand with our method can still hold the bottle in hand without spilling out the water, but the baseline has a large acceleration and also the shakes case. If you are interested in our work, please come to our poster section, number 8. Thank you.
Hi everyone, I'm Devidatta. I'll be talking about our framework, Gen2 Act. So the problem setting we are interested in is generalist policies. So the scene can be unseen and the text that is given to the robot can also be a new one. So at that point of time, how do we get these policies to behave in a proper way? So to do this, we are relying on pre-trained human video generation models that can take a current frame as input and generate what the success of a task looks like. So you can take the current frame and it tells you what would be successful if a human did the task, and then we train a policy that takes the human video and outputs actions on the robot. And by being able to do that, we can also chain a bunch of videos one after the other to do long horizon tasks in new scenes. And how we are able to do that will be explained at our poster, so please come by poster 27. Thank you.
Yep, so good morning everyone, I'm Minu from SNU. Today I will introduce ImLPR. This work is in collaboration with ORI. And yep, so in recent days, the Vision Foundation model shows a powerful performance for various downstream tasks. And building on this, 3D foundation models are also advancing. These foundation models have been applied to place recognition. For instance, Dino, as you know, serves as a feature extractor for visual place recognition. Inspired by this, we investigated their potential for LiDAR place recognition. However, applying a 3D foundation model to LiDAR data is really challenging due to their reliance on RGB data and limited training data set compared to Vision Foundation model. Instead, by effectively converting point cloud to image with some mapping technique, the Vision Foundation model can be a promising solution. So that's the reason why we designed IMLPR using Vision Foundation model. Please visit our poster 79 to find more detail. Thank you.
Hi, my name is Xinga Jiang from Karlsruhe Institute of Technology. We are going to present our work named IRIS. IRIS is an extended reality framework for robot learning. So users don't need to know anything about the extended reality development, and they can use XR headset with Python code. So here's some demo video. So we can try to use some data collection for the Libro, and for analysis such as meta word for robot Casa, which is a really big thing. And you can try even any other robot in Mojoko, iSexing, Copiloting, and Genesis. You can also try bimanual robot manipulation and humanoid robots such as Unitree H1. By the way, this is all the virtual robot, and you can even try soft object manipulation from iSexing and collaborative data collection, so you can play it with your friends, and then you can even interact with, play with the table tennis with the IR agent. And we also support for rendering point cloud, so you can collect data from the robot. Please find more information from the post session, and our number is 82. Thanks.
Animals display remarkable adaptability in natural and complex environments, particularly when facing joint wear, limb injuries, and losses. Redundant leg joints can exhibit remarkable fault tolerance. We propose a novel contrastive forward prediction reinforcement learning framework. Privileged observations are provided to the critic to refine the gradient updates for the actor. The policy network, as shown in the video, we compare a method with the DreamLac method using random joint mask. We conducted a TSNE analysis of the embedding distribution in the latent space. The next video demonstrates our method applied to a quadruped robot with different joint damages. In addition, enter joint damage conditions. Our method also demonstrates strong generalization across different terrains. The bar chart compares the velocity tracking accuracy between our method and adapt its gait and locomotion strategy, demonstrating the fault tolerance capabilities of our method. Its walking posture on grassy surfaces, and it can also navigate downstairs smoothly.
Hello everyone, my name is Shivam and I'll be presenting our work on sub-goal transitioning in goal condition policy learning. Consider the problem of imitation learning from expert demonstrations using behavior cloning. As the task horizon increases, errors accumulate over time, resulting in distribution shifts. This problem is usually addressed by decomposing the overall task into sub-goals and then learning goal condition policies. However, a key challenge with goal condition policies is that at inference time, the agent must decide when the current sub-goal is considered achieved and when to transition to the next sub-goal. To address this challenge, we introduce SGPT, a new policy architecture that leverages cross-attention over sub-goals and learn continuous and smooth sub-goal transition signals along with joint space actions. Policies learned through SGPT can reliably execute very long horizon tasks and handle more complex manipulation. To learn more about our work, please visit our poster session, poster 53. Thank you.
Hi everybody, I'm Michael Mungy from UT Austin, here to present Composable Nav on behalf of Xiao Hu. So developing robots to follow instructions allow humans to customize how they want their robots to navigate in everyday situations. The problem is that instructions often contain multiple specifications. Popular methods such as reinforcement learning and imitation learning struggle with this, because if you change the order or combination, then suddenly you need to retrain your model. To tackle this, we propose Composable Nav, a diffusion-based planner that works by composition. Rather than training one large model to handle every possible combination, we train multiple diffusion models to learn low-level motion primitives. During deployment, we use primitive diffusion models that correspond to the specifications and then compose them on the fly to generate trajectories that satisfy the instructions. For more info, please see me at the poster session, and I actually have one more spotlight too, if you'll bear with me. Okay, so this is Social Nav Sub. This is a VLM benchmark for social navigation. So recently, we've seen plenty of works that have leveraged VLMs in robotics, and in particular for robot social navigation. Despite signs of promising results, VLMs can still show a lot of mistakes in scene understanding for social navigation. To help evaluate VLM capabilities, we contribute a benchmark for scene understanding for social navigation. Our benchmark, SocialNav Sub, features diverse social navigation scenarios, grounded representations for VLMs, multiple ways to assess scene understanding, and robust evaluation against human answers. Even the best performing VLMs can still underperform compared to rule-based and human consensus baselines, showing that there's still room for improvement before VLMs can be used reliably in practice for social navigation. For more info, please see me, or if you see me around, please feel free to approach me. Thank you.
Okay, so this work is about policy generalization through functional correspondences. Now we all agree that imitation learning is great. Here we are simply trying to sort trash and recycling. However, when we show the policy in new trash, it sort of struggles. I mean, if you see a tissue, would you compost it or would you recycle it? Our observation is that while we can keep collecting more demonstrations to sort of fix this, the robot already knows the behavior, it just doesn't understand the mapping. So the key insight is that ID behaviors can be transferred to OOD conditions that are functionally overlapping. Based on this insight, we present adapting by analogy, our test time adaptation approach. ABA first runs a very fast OOD detector. On encountering an OOD situation, ABA will retrieve functionally corresponding in-distribution samples. You will shortly see it in action. So on the right, you can see it's retrieving these observations from the training set and using that to steer the policy through OD conditions. With this, we can generalize to novel object configurations and novel backgrounds. Thank you. Please visit our poster.
Hey everyone, we present ARC, Hierarchical Hybrid Learning for Long Horizon Contact-Rich Robotic Assembly. In our task setup, we have a third-person view camera captures RGBD images. A robot arm performs manipulation tasks, and objects randomly placed within the grasp region on the table. We propose a hierarchical learning framework. The high-level policy can be learned from a handful of demonstrations. It takes object pose and robot pose as input, and predicts a categorical distribution to select the best low-level primitives. Our low-level action primitive library consists of both motion planning and IL policies. We first validate our framework on 2 complex simulated tasks. We then evaluate on real-world tasks. Our system can generalize this well to unseen objects without any fine-tuning. Further details can be found in poster 42. Thank you.
Our paper is called DIVA, Diffusion Policy Adaptation with World Models. The human ability to sleep on a problem and wake up with clarity inspires this work. We fine-tune diffusion policies with RL by exploring entirely inside a world model. The robot policies are fine-tuned without touching the real world. First, we train the world model on a large play data. Then we use small expert data to train the policies and a simple reward classifier. Then we roll out policies inside our Dream Diffusion MDP and reinforce the whole chain with PPO updates. You can see the base policies fail to do the task, and they get to practice in the Dream, and the fine-tuned policies then do the task a lot better. This is the power of our approach, where we combine diffusion policy, world model, and policy gradients. To see more results in simulation, you can visit our poster 10.
Hello, so in this paper we present the first framework for using mechanistic interpretability techniques to identify and exploit semantically interpretable representations within vision language action models for the purposes of interpretation and also for steering and control. So as a brief overview of our framework, we first extract these representation vectors from the feed-forward network, and then we try to project these vectors into the VLA token space to get a semantic meaning for each vector. We can then cluster these vectors to get a set that all represents a similar semantic concept, and then at inference time actually change the activation weights for this specific semantic concept to modify the behavior of the robot. And we're able to show this both on real hardware with the Pi0 model working on a UR5 arm, as well as in the Libero simulation with the OpenVLA model. And I just want to finish up with a quick side-by-side comparison showing that we can modify the behavior of the robot in different ways while it is still able to successfully complete the task. And for more details, please check us out at poster number 49. Thank you.
Hello, my name is Zach. I'll be presenting distilling on-device language models for robot planning with minimal human intervention. Language models provide robots with contextual reasoning and a natural human interface. However, LLM-enabled robots typically rely on cloud-hosted models and reliable network infrastructure. And while this works in structured environments, it prevents operations in environments where internet is unreliable or unavailable. We address these limitations via PRISM, a framework for distilling on-device language models for robot planning. The distilled models rival the performance of their LLM counterparts, and training requires only synthesized data, so no curated datasets or simulators. We evaluate our method on 3 distinct simulated and real-world domains, and we find that it boosts the performance of a base model from under 20% to over 90% on unseen tasks and environments. To learn more, please check out my poster at booth 42. Thank you.
Okay. So, hi everyone, I'm Hojin from Quest. We made a fast and accurate collision checker. So we are tackling a core bottleneck in motion planning, swap volume collision detection. Discrete checkers can miss between waypoint collisions, known as tunneling, while classical SPCD trades speed for accuracy. Our method, Neural SPCD, is an encoder-decoder based method that outputs penetration depth from mesh of objects and trajectory. It is efficient and GPU-friendly, generalized well with high accuracy. So why does it generalize? We exploit 2 localities: shape locality. Contact depend on local geometry. Temporal locality. Most severe collisions occur on short trajectory snippets. We tested our SPCD in domains including narrow passage like dish insertion, bimanual paginal, and mobile navigation. Testing in diverse domains, we matched our bit success while cutting planning time, up to 6 times faster than curable at similar success rate. So our poster number is 22, so please come us. Thank you.
Hi all. We present HAT, learning humanoid navigation, locomotion, and reaching. Given a 2D point on an image as a goal, our system can autonomously deliver itself based on its own ego-centric vision to navigate the scene and finally reach the picked target. We propose a modular design to achieve this with the 3-point tracking as the interface. The high-level policy includes a navigation module and a reaching module. They send 3-point tracking to the lower-level Hobart controller, which keeps running at 30 Hz to track the target while maintaining the balance and the smooth transition. Finally, we show our robot can deliver itself to different targets in different environments. For more details, please come to see our poster number 2 in this afternoon. Thank you.
This work focuses on developing a quadruped controller that extends factoring animal motions to achieve not only the local motion, but also the local navigation across diverse terrains. And by using RL with reference data, complex motions can be acquired with minimal reward shaping. However, since such controllers are often trained to simply replay these motions, and it could be hard to generalize to the new environments. And to extend its adaptability beyond simply mimicking these motions, we propose a hierarchical RL framework to tap the flattering skills learned from the animal data to diverse terrains with the joint residuals. And as a result, our pipeline transfers the flattering skills from the animals to diverse terrains while preserving the motion style in the dataset. And furthermore, our controller can also achieve an efficient obstacle avoidance with only a single goal specification by incorporating the lidar pattern scan into the observation space. And if you're interested in our work, please come to poster number 6. Thank you.
Hello, I'm Dong-Young Gang from KineSoft. I'll present our work on learning impact-rich rotational maneuvers. We validated our approach on a one-legged hopper, which is modeled after a single leg of a humanoid leg. How can we achieve impact-rich rotational maneuvers in this robot? We observed that executing a front flip requires respecting actuation limits at takeoff, generating sufficient angular momentum, and modulating inertia midair, and managing high impact forces and landing to avoid hardware damage. To address these challenges, we proposed a motor operating region to enforce actuator limits, centroidal velocity reverse for whole body rotation, and transmission load regularization to reduce impulsive torque loads. With these techniques, we successfully transferred the learned flip motion to hardware and completed front flip across multiple hardware trials. To see more details, please visit our poster.
We introduce Object React, learning object relative control for visual navigation. Images are a gold standard sub-goal representation for navigation. Here, an image from the map is used as a sub-goal to predict control. One limitation of this approach is that images are tied to the agent's embodiment and pose. Our approach, Object React, instead uses an object-level topological map to plan over. Sub-goals are represented in the current view of the agent using an object-level cost map. This has several advantages, including enabling robustness to embodiment changes between mapping and execution. Object React enables landmark-based human-style navigation. It also enables cross-embodiment deployment. Here we demonstrate using a phone camera to generate a map, and then deploying Object React using this map on a quadruped robot. We hope to see you at poster 55. Thank you.
As you know, just before, one also had video problem, so let's welcome him again.
So good luck to me. I want to introduce my work, FastUMI. FastUMI is where we designed the UMI with the hardware decoupling for broad adaptability and the software-driven plug-and-play efficiency and the robust ecosystem to ensure the data quality and algorithm capability. This is our device. The guys use our device to collect the data in the task of pick and cup. And we also open resource to 10,000 trajectories for the whole community.
Oh. It's okay, we have post-session and he prepared demonstration video, right?
Oh, could you jump to the last page? I want to show our professional device. We set up a new company and we sell the upgraded device. And if you are interested in our device, you can come to our poster session. Thanks.
Thank you for your brave second trial. It's I'd like to close the spotlight session and please enjoy coffee.
腾讯 Robotics X 和福田实验室基于过往多年在机器人领域积累的技术能力，广泛结合产业端需求，发布了规划大模型、多模态感知模型、感知行动联合大模型。各个模型之间通过多模态感知、规划、记忆等模块的协同工作，转化为机器人的具体行动。规划大模型作为机器人的大脑，具备自我认知能力，通过与人类自由沟通、拆解任务、调用工具、查询知识库和在执行中的自我反思，最终完成长程复杂任务，并可为特定领域提供角色问答服务。欢迎参观腾讯机器人实验室。
来，我们握个手吧。
当然，很高兴认识你。多模态感知模型可实时整合环境感知数据，构建语义丰富、空间关系精确的3维层级地图。
你们俩去站在前面2个企鹅雕塑中间，我给你们拍个合影。
支持自然语言输入输出，实现多场景下的高效信息检索，助力机器人精准完成任务规划与环境交互。感知行动联合大模型结合快慢系统思考与时空物理感知，有效赋能灵巧手、夹爪等多种末端执行器，在复杂场景下对多样物体的操作能力。同时，针对人形机器人训练得到的模型，可实时感知机器人本体信息、环境地形信息，并作出及时响应，控制各关节协调运动，进而控制机器人灵活移动、灵敏运动。目前 Hyros 已经适配过双足、轮式人形、4足、机械臂等多构型本体，操作支持夹爪、灵巧手等多种末端执行器，与多家机器人企业在工业、汽车、家电等多行业进行场景落地实践。未来期待与更多机器人企业联手，共同推动机器人行业发展，共建人机共存、共创共赢的未来。
I see. Okay, over there. Great.
If you need presentation mode, you have to change the display.
Okay, but this is good. Yeah,
okay.
This is good for me. Thank you. And
Omron Cynic X quickly captures signs of change in the world and the social issues that arise from them, designs the near future, and aims to create innovative technology.
줌 테스트합니다. 하나, 둘, 셋, 테스팅.
Okay, Professor Yuan, can you hear me?
Well, now. So can you guys hear me?
Yes, and also can you see us?
Yes.
Okay, great.
I can see the screen and the hall.
Okay, great. We will turn to the other promotional video again. Thank
Okay,
you.
so do you mind if I log off for a few minutes and check back like 5 minutes before the session starts?
If you want.
Okay, thank you.
Oops, I forgot my password. Sorry. 여기 있는 건가? 여기에 물려야 돼요. Should we try? Yeah, it's playing this. Yeah. Oh, in my own settings. 아니면 얘를 바로 PC에 sound. USB audio. Okay, let's try that again. Yeah. Should we try the other option? There's another HDMI. Maybe we can. Yeah, I think we can try it. I think so. That's an HDMI port, but I can focus on that. Anyway, that's what we have for there. Try direct connection. USB-C. Yeah. Yeah. Sorry. Yeah, this is not a USB-C. 저기서 안 켜져 있던 그런 거 같아요. Please play. Yeah.
This is coming from your laptop.
Yeah, that's coming from my laptop.
그 오디오 세팅이 지금 코덱으로 돼 있어요?
Can you? Yeah. Okay. Let's try again.
Please check this one, okay?
And then should we try?
Yeah, you can try.
Let's see. So you went. Where was the option? You went
Option? Option here. Sound. USB audio.
So up here and USB.
Yeah.
Yeah, I also want to know.
So you go up here.
Head
You can
up.
try your laptop inside.
Yeah, I will do.
This is where you need to go. And then go USB on.
Yeah, okay.
And then
I would like to try.
okay.
For the audio, how do I play from audio from the computer?
I think it's sound setting.
This.
And is USB audio code
Okay.
option.
Okay. I try to play something just to make sure it's. Okay, it's off. Okay, perfect. Yeah. All right. Thanks so much.
네, 지금 컨셉 빠지고 계시는
갈색 끝까지 주시죠.
I should be sitting now.
I don't know. That's what someone said. No. Like after you're done with this, yeah.
That I understand. Yeah.
Okay. I was confused.
I think that makes sense. Okay, hello everyone. Please find a seat to sit down. We'll start our next session very soon. Great. So, hello everyone. I'm Shuran. I'm the session chair for this very exciting session. So this is actually one of my favorite sessions in every CORL. This is our early career keynotes. So every year in CORL, we will invite those rising stars in the field to talk about their most exciting work. That's probably you're going to be excited about it as well. So today we have three amazing speakers lining up. And then our first speaker I will introduce is Wenzhen Yuan. Wenzhen is assistant professor at UIUC. And she directs the lab called a Robot Touch Lab. And her work has been really pushing the boundary for high-resolution tactile sensing for robots with much wider contributions and applications in multimodal robot perception, soft robotics, manipulation, and haptics. And then, unfortunately, she will not be here in person, but she will give the talk online. And let's welcome Wenzhen.
Thank you. Thanks very much for the introduction. It's really a great honor to have this chance to be here and introduce our work. It's very unfortunate I cannot join you in person because of health-related issue. So here is where I started my journey in robotics research since 13 years ago. So we try to address this question: how can we make a robot able to understand the world through touch? So definitely the first step, we need to have a good sensor. So together with my advisors and lab mates, we introduced the vision-based tactile sensor GelSight to robotics. So it uses some optical design to turn the high-resolution contact geometry into a format of RGB image, so the robots can precisely measure the fine details of any arbitrary surface. So this kind of rich information turns out to be very helpful for many robotics tasks and introduce many new possibilities to robot perception and manipulation. But at the same time, the rich and high-dimensional information also introduces new challenge in data processing and machine learning. So I would like to, among those efforts we did, I would like to mention this work where I collaborated with Roberto, Andrew, and Dinesh back in 2017. So we try to predict the result of robot grasping based on the output of GelSight data and external vision using data-driven methods. So here is how our machine learning structure works. And everything works well. It turns out it generalize very well to different objects. But the biggest challenge here is data collection. So what behind the paper is that like we have some grad students sitting in the lab for several days, just watching the robot doing grasping, and we broke multiple sensors, and we need to remake the sensors in the lab, which was really a painful process. So this also reveals the truth about like any robotic research and data-driven methods with tactile sensing, that the data is expensive. So let me ask a question. Can we do things in simulations, since it turns out to be a very effective way to scaling up the data collection process? So based on this motivation, so together with my students, Lin, so we introduced a new simulation model for gel site called Taxon. So it's an example-based simulation model, which means like it's data-driven, but we only use a very small set of data and very simple model to simulate the sensor, so that the model itself is very easy to calibrate and it's very fast in computation. So the core part is only a simple polynomial models, and we only need to characterize a few parameters based on like 15 samples that can easily collected by human. But the result is pretty good. So here shows examples about like the comparison of the real sensor reading and simulations when we use a sensor to contacting different object surface. And also, like even our CPU machine is able to achieve like almost online performance as a speed side. So it also generalized pretty well to different kind of gel site sensors after simple calibration process. So this inspired us to revisit this like data-driven grasping problems. This time, instead of making a grad student sitting in the lab watching the robot doing grasping, we moved all the data collection process into simulation. And based on simulation models, we trained the simulation data, we trained the model, and try to predict whether the grasp is successful or not. And you transfer to the real model, and then transfer to the real robot in a zero-shot manners. And the result is actually pretty good, as shown here that like we can achieve a successful rate of 91%. And this inspires us to ask the question. So with these good tools for simulations, have we solved the data challenge for robotic tactile sensing? Or we can also pose this question in another way. Can those big tactile data sets and models be broadly shared and used across the community? So obviously, I guess you sit here, you know that the answer is no, because there are multiple challenges. And the biggest challenge here is the domain shift caused by sensor hardware. So in other words, the same context may cause very different readings for each individual sensors, even if they may be of very similar design or exactly the same design. So that currently, the tactile data is very hard to share, and models trained on data from one sensor generally cannot be applied to another sensor. And this challenge becomes more serious if we consider the wider range of tactile sensors that has been used on different applications, different robots, or have been played a very important role at different time of the history. So those tactile sensors, they vary greatly in sensing modalities, spatial resolution, precision, and noise models. So, but how can we address this big challenge in the sensor-to-sensor gap? Are there any potential solutions? So since last years, researchers have tried to train models with large tactile data sets collected by different sensors to facilitate transferability between sensors. So they show to be very helpful initial trials towards this challenge. But however, the shown generalizability is still kind of limited. So that is because although the training data set size is pretty large, but the training data is only from a small number of sensors, so that as a result, the zero-shot transfer to new sensors is almost impossible. So, but we still have this need of having a solutions to bridge the sensor-to-sensor domain gap. So we hope the methods to be easily applied to new sensors and can cover a wide range of tactile sensors. So this poses a bigger challenge on the data collection side. So especially in the real world, it's really difficult to cover like a large variance of different tactile sensors and collecting data on a very similar domain. So what could be a good solution? So this inspired us to look into the old solution again, like Simulation. Can we use simulation to do this? But this poses a very different simulation and data collection problem than the traditional ones. So traditionally, when we talk about collecting robotic data in simulations, our focus is collecting the variance of the response of a single sensors under different cases. But now, since our focus is to bridge the sensor-to-sensor domain gap, so this data collection process should have a well coverage of the variance in the sensor design itself, so that the traditional way of simulation doesn't work. And particularly, we believe we need to use a physical-based simulation method. So how does this work? So we come back to the job site sensors. As we introduced at the beginning of the talk, the job site sensor uses optical design to turn the contact geometries into the readings of the camera's image. So the core sensing part here is this optical system. So we try to use physical-based rendering to model this optical system and on the physical level how things work. So here briefly shows how the method works. So given this optical system, there's lots of light rays flying around in these things. So we try to sample a lot of them and track how they works, how they travels from the light emitters, hitting different surfaces, got reflected, refracted, and finally a small portion of it will hit the photonic sensor in the camera plane and contributes to the brightness of a single pixel on the image. And we repeat the process and tracking lots of rays, and finally that can form the image in the camera. And that exactly gave us the output from the tactile sensor. So once we have this method, we try to simulate the sensors by disassemble the sensors into its original optical components, getting the precise models of optical models of each optical components, and reassemble them into simulation and see and track how the light travels in the things and how they form an image as a final output of the camera's image. And the result is pretty reasonable. So here shows our comparison of two slightly different sensor designs of our simulated results with the real sensors. You can see that the simulated results is very close to the real ones. So obviously, it's not a perfect method. So we didn't like it since that it's not very fast and not very realistic to apply it for the robotic simulation scenarios where real online response or real-time response is needed. But we also like it because it's built based on the physical principle. So in other words, we can play with the sensor design in simulation by rearranging all the optical components and changing the geometries, by playing with them like toy blocks. So that exactly means we can build new sensors in simulations, which may happen just in a few seconds. And in comparison, making a new real sensors in the real world, so that may take several weeks' time. And also this process can be fully automated. So we can define a range of choice of optical components and geometrical design factors. Our simulator can automatically sample a bunch of designs in the range and renders the sensor's reading under the control conditions when contacting different objects. So going back to our initial motivations, that we want to build a data set of many tactile sensors, and this provides exactly our solutions. So we actually ended up collecting a data set of 100 variants of job site sensors with a definition of the design space shown in the right. And we also built an object data set containing 50 different objects and a bunch of different random contact locations, which resulted in 10K contact geometries. And by combining the two, we can get a data set of 1 million tactile images, which contains the variance as a combination of different sensors as well as different contact geometry. So in addition, you can see that this data collection pipeline is fully scalable. We can easily extend its distributions by enlarging the sensor design space definitions and the object set regarding the contact geometry. So then let's go to the algorithm side. So a recap of our previous discussion of what makes an ideal solutions for bridging sensor-to-sensor domain gaps. So we want this method to be easily applied to new sensors and can cover a wide range of sensor varieties. So we want to address both requirements. So on the easy application side, we want to make sure our models can apply to a new sensor after some very easy to get calibration process. And it should also be able to transfer to out of distribution sensors. And based on this, here is the machine learning models we proposed. So we try to get the input through a backbone of transformer encoders and generate this sensor invariant tactile representations, which we hope that it contains all the tactile relevant information, but not the sensor-specific domain information. And we hope this representation can be used as the input of different downstream task machine learning models instead of the raw data. So the input comes from two sources. So one is the current tactile images, and the other part is a set of calibration images that conveys sensor-specific info. And this calibration images is very easy to collect. So you only need 18 different images that can be manually collected in a few minutes. And this network is supervised with two sources. One is contrastive learning structures, which is defined as cluttering the representation if the contact geometry is the same, regardless of which sensor source it is from. The other supervision comes from the shape reconstruction, and this supervision forces the representation to maintain all the details about the contact geometry. And here shows our results on testing the system. So we try to test it on 3 downstream tasks in a totally zero-shot manners. So that means like our neural network is purely trained with those simulated sensors, simulated data, but most of our tests is conducted with real sensors, which whose optical designs is pretty much different from the ones we have in the simulations. But you can see that in this first task for 3D reconstructions, so we can get a very reasonable reconstruction results of the shape of the objects when it is in contact. For the other tasks, we try to work on an object classification task and contact localization task. And in both cases, although our transfer happens between sensor A and sensor B, both are sensors not in our training sets. So you can see that the transfer results is pretty good. So, but still, we believe like although we show some progress towards this challenge, but we are not solving things. So specifically, our focus has been mostly on Galaxia family of sensors and focus on the tactile sensing relevant to the geometrical information. But if we look at the broader challenge of the entire communities, so there are new challenges regarding to like other sensing modalities such as force, pressure distributions, and also we need to consider the transferability between different types of sensors, even the sensors that is not really existing now. And we believe that this remains an open question for the entire community, and we should join force on this. Okay, so that summarizes my talks. I would like to thank all my students who worked very hard behind the scene and make all those good results. And I would like to thank you for listening.
Great, thank you. And any questions from the audience?
Yes, quick questions. Thanks, Wenjen, for the talk. I appreciate your effort to make the tactile sensor more useful for this whole area. And I think you use the image or video as a conveyor of the tactile sensor information, which is useful to transfer the knowledge between different type of visual tactile sensors. I wonder if it's possible to add another layer of encoded feature layer such that you can expand this transferability not just beyond this visual tactile. You can essentially transfer it among, like, say, magnet or capacitive or resistive, all different type of tactiles. I think you kind of mentioned a little bit at the end of your talk, but just want to hear your thoughts on this.
Yes, that's a great question. So I think this is something we must do as a community for the future. Like we cannot constrain to gel side or vision-based tactile sensors. There are also other sensors, like you said, like magnetic sensors, and there are sensors that does not exist now, but I'm sure they will exist in the future. So I don't think like it's very easy to bridge these domain gaps in this setting, especially considering this difference in spatial resolution and representations. So that means like we probably need like new formats of like neural network design and new format of data collections. So I don't think we have a good solution now, but I look forward to exploring this in the future.
Cool. Thank you.
One more question.
One more question. Okay, thank you. Hi, Wenjin. Very nice talk. Thank you. I was wondering if you could turn the process also around that you have right now and actually use that simulation to optimize sensor parameters too for a particular task, or if you thought about that.
Oh, that's great. Thanks for asking this. Yeah, we actually have some recent progress this, and we have 2 papers published recently about like turning the sensor design process fully automated and can optimize the design factors in simulation. So it's unfortunate I won't have time to introduce them in details, but like I encourage you to check our recent publication.
Thank you.
Great. Let's thank the speaker one more time.
Thank you.
Okay, so next is my great pleasure to introduce Nima. Nima is assistant professor at University of Michigan, where he leads manipulation and the machine intelligence lab. His research is focused on intelligent and dexterous robot manipulation, ranging from sensing, learning, and control the whole stack. And Nima told me that he's going to have a completely new talk today, so I'm really excited and looking forward to it.
Thank you so much for the very kind introduction. As Sharon said, I'm sorry, I'm pulling the rug out from under your feet. It's an entirely different talk from the abstract and whatnot, but I think it'll be fun. So we're really going to talk about why manipulation is so hard, why it's so interesting, and we're going to talk about dexterity through vision and touch. But before getting there, I think I want to share with you the dream for dexterous manipulation, and that's this video. This is Wally. Perhaps you know Wally. And I think what makes Wally uniquely interesting is that he's such a curious robot, right? He's walking around. He's exploring the world, he's making contact, he's manipulating objects, he's learning from proprioception, vision, touch, building internal representations that then he will use downstream for useful work. This is super cool, this is what we aspire to have in robotics. Okay, so what is happening here? What is the beating heart of dexterous manipulation? And I think it's worth mentioning that manipulation is essentially contact. If you want to get a little bit more specific, manipulation is intentional contact. Even more specific, manipulation is the ability to perceive and intentionally make contact. This is mission critical. When you're manipulating, you're making contact. What matters is the contact, okay? And so given the importance of contact, I feel like the community is somewhat ignoring it, and so let's not throw contact reasoning out, okay? And so I don't have Wally at the moment, but I do have Nebula. This is Nebula. Nebula has access to vision from the view that you see, has access to tactile feedback, similar to the ones that Wenjin showed. Nebula is grasping an object and wants to perform some useful skill. So in my research group, what we focus on is contact perception, multimodal contact-aware representation learning. Here, multimodality refers to vision, touch, proprioception, even language. And what we're interested in doing is planning through contact. This is kind of the mission-critical part of manipulation, okay? And so these represent the 3 pillars of our research group. And today, I want to talk about tactile-driven behavior generation. And so first, I want to talk a little bit about the importance of touch. Fortunately, I had Wenjin go before me, so I can keep this super short. And then talk to you about the different sort of methodologies available to you to produce this behavior and some of the issues or some of the successes that I've had. And the ethos for today is much more around what are we solving rather than how. I don't want to give you a recipe. I want to inform you about what it is that we're solving when we're doing manipulation. Okay? So to get us started, the importance of touch. This is the creation of Adam by Michelangelo. And as with any great art, you will look at this and you'll take away whatever you want to take away. For me, what's interesting here is the centrality of touch. This is kind of inspired by Abrahamic religions in the sense that many of them believe that the soul is imparted to the human through the sense of touch. If you're a biology nerd, you'll know that your tactile or your sense of touch was much more primitive to your motor cortex than your vision is. It was developed much earlier in our evolution than vision was. And if you're a roboticist, you'll say, okay, cool, I can use it for slip detection, I can do grasp force modulation, I can do shear estimation, I can do object localization, I can do palpitation. It has many, many great uses. It's a very useful modality. Now, when we think of tactile-driven behavior generation, what do we mean? Here's an example of a tactile sensor. Again, I don't have to go into too much detail. Wenjin did a great job of talking about it. Here, this is called a Toyota soft bubbles. And the idea here is this is an inflated membrane. There's a camera inside, and we're transducing a deformation into a visual modality. So here, the sense of touch is imparted to the robot through this deformation in the membrane, and we perceive it through a camera. Therefore, it's called a vision-based tactile sensor. What we're interested in is going from this, in addition to vision and proprioception, into behavior. So here's an example of the robot kind of stirring some food. We're not allowed to have food in the lab, so pretend those blocks are food. Okay? But to get here, what are we trying to solve? What are the challenges? What is interesting about manipulation? If you're new to the field, this will sound really weird, but manipulation is exponential in the action space and the number of objects in the scene. Now, let me illustrate what this kind of concept means. Here's an example of a cup. Pretend this is a cup. And what I'm interested in doing is moving this cup from here to this goal configuration, so something like this, okay? We're going to reset the scene and we can say, okay, if I give you one finger, how can you interact with this scene? Well, you can put your finger here. You can instead put your finger here. You can put your finger here, or you can put your finger here, right? You had 4 choices. You not only have 4 choices, you have to make this temporally. So you have t to the power 4 different choices across time, right? This is what I mean by exponentiality. This problem very quickly blows up. We have very, very hybrid systems of manipulation, which is uniquely what makes them very difficult. You can make this even more elaborate by introducing 2 cups. Now if I have 2 cups, suddenly I have 8 discrete decisions, in addition to the interaction between the 2 cups. And so now I have 9 discrete decisions across time, and we are sad. Manipulation is very difficult, and it's exponential in nature. Now that you understand what it means to be exponential in action space and the number of objects, it is always partially observed. There is no version of this problem that is not partially observed, so this is super important. If you're doing anything interesting that's dexterous, it's always partially observed. We have access to vision, touch, and proprioception. I think as a community we agree that these are reasonable modalities. Some people have been exploring audio and vibration. Super cool. It is always non-differentiable. Don't be fooled. Physics in contact is non-differentiable. We make approximations to make it differentiable, but it's fundamentally a non-differentiable system. And these are all physical issues, right? Manipulation is in addition hard because of a notion of creativity. This is not so much physics as it's a little bit living between physics and semantics. So what do I mean by creativity? Here's a nail, and if you want to hammer this nail home, you could use a hammer, of course. You could use a wrench or a dumbbell. My wife really likes dumbbells. I don't know why. You can also go into your kitchen, grab a water bottle, you can grab a skillet. You can also go grab a rock from your garden. These will all give you the same affordance to like tapping this nail in. And what's interesting is that when it comes to creativity, our own internal semantics will determine which choices we make. So if I'm particularly attached to my skillet, I'm much less likely to use it than the rock. Okay, so our reasoning goes far beyond physics when it comes to manipulation. Cool. So now that you have an understanding of what makes manipulation interesting and difficult, how do we think about behavior generation? Well, there's really 3 big paradigms. There's model predictive control, there's reinforcement learning, and imitation learning. And I'll kind of walk you through some of these like, big 3 ideas in relation to the challenges that we've seen. So when it comes to model predictive control, this is generally what a problem setup looks like. You have a robot, it's trying to do something interesting with a spatula. You have some initial state of the world. There's a world model. We used to call this dynamics, now we call them world models, super cool. And you input some actions, A1, A2, and A3. It will predict a sequence of states, S1, S2, and S3. You will compute some loss between the sequence of states you predict and the sequence of states you want. You calculate the loss, you go back, you modify A1, A2, and A3 until you're happy. You execute the first action and you go again. This is the crux of any MPC kind of a control you can see. What my lab does a lot is do this with visio-tactile feedback. So we want to do this in the vision and tactile domain. And so some example of the work that we've been doing, here's a robot. It is grasping a, this video is finicky. Sorry. Play. Good. And so the objective here is to align the spatula with the green cylinder. And it's going to do, this is all MPC, fully autonomous. You just set a goal configuration. The robot will pivot by adjusting its grasp and using the environment. You can get really fancy with this. So here the task is to grab a box and insert it into this cavity between these 2 boxes. What's interesting here is that there's not enough room, so the robot actually has to create space by using contact and pushing these objects apart. It's a very force-rich and interesting interaction. You can get even more fancy. Here's an example where the robot is tasked to balance an object in the environment using a grasped object. What makes this uniquely difficult is that there's the frictional interaction between the grasped object and the gripper, the object and the environment object, and then the environment object with the environment. This requires a lot of precision. It's very, very difficult to do, and it requires very careful reasoning. You can do other things, such as, for example, here, the task of rotating in the plane. You can do fun things like rolling pins. And you can even do in-hand rotation. This is, again, all MPC. We can do this with learned models, with physics models. MPC is incredible, okay? And so going back to the context of the challenges that we talked about, so the nature, exponential nature, multimodality, and so on, what is MPC trying to do? MPC is trying to address all of these challenges with compute at runtime. Okay, so you get a compute budget. That's your budget. That's all the time you get. You have to figure out how to address all of these challenges in that short budget. And so the trick with MPC is always to find efficiently searchable action spaces. That's the key trick in MPC. Everything you saw prior to this slide was basically us figuring out clever tricks for making searchable action spaces. But this is also sort of the Achilles heel of MPC, where it starts to break down when you have a clutter. As soon as you introduce many objects, many contacts, you begin to have this exponential cursive dimensionality come at you very quickly. Okay, so this is a pretty well-known issue, but as long as you can kind of create these spaces, life is good. Now let's turn our attention to imitation learning. Here's an example of a nut and bolt assembly through kinesthetic teaching. So here William is trying to get the robot to learn how to do a nut and bolt assembly. We have access to proprioception, we have access to tactile feedback, and it's sort of just demonstrating the skill to the robot. I think assembly is particularly useful for behavior cloning in the sense that it is a relatively constrained task. When you're doing assembly, there's not some wild action space, there's not some random person's kitchen somewhere wherever in California. It's like a pretty constrained task, okay? And assemblies are pretty hard to program. This is why most of them are not automated at the moment. And so we came at this problem and thought, okay, can we kind of address this issue? And so we took our tactile feedback, we took proprioception, we took shear fields, and we tried to basically apply behavior cloning and realized that, as is, it's very difficult to make these things work. Again, contact imparts specific constraints that you absolutely have to meet. These are zero-level sets that a distribution just does not capture. In order for you to be able to capture those, you have to have contact-aware projection techniques. In this case, we have this contact-aware projection technique that discovers manifolds that are compatible with the manipulation task and the contact constraints in order to make sure that you're stable and precise. If you're able to learn these manifolds, then these are some of the capabilities that you enable. You can do tight insertion, nut threading, and even assembly. This is like a snap fit of a remote controller onto the back of a remote. And that's something that we kind of discovered here is that the role of shear is extremely important. The reason why shear is important goes back to, again, contact. It's a direct measurement of the forceful interaction between the gripper, the nut, and the bolt. It's very difficult to infer this notion of force from just the visual feedback of the tactile sensors, but you can compute it, and really using shear is what makes this thing actually tick, what makes it work. Again, having direct access and knowledge to contact will enable you to do lots of interesting and dexterous things. Okay? And so thinking about imitation learning, and again in the context of the challenges that we've been talking about, what are you doing? You're always relying on offline human data, right? That's kind of the trick. And this means that you're relying on human labor and ingenuity to address the challenges on the left-hand side, right? So, for example, take the example of creativity, right? If I want to hammer a nail, then do I have to demonstrate every single iteration of a grasped object hammering a nail? That kind of seems like what I have to do. You're really relying on the human's labor to address many of these problems, including the exponentiality of the problem, clutter, multimodality, partial observability. It seems very difficult. In the context of manipulation in particular, we also have unique challenges of haptic feedback. Currently there are devices, but they're pretty limited. And there's massive embodiment gaps often between our hands and the platforms that we're using. Okay? And then turning our attention to reinforcement learning, I think tactile-driven reinforcement learning is about to have a renaissance. Here is Isaac. I think Yash is in the crowd. This is taken from Tactile. This is photorealistic rendering, and it's just beautiful. You look at this and you're like, wow, we're almost there, right? And what makes this interesting is simulation is rapidly advancing. It's very easy to parallelize. And many of our atomic dexter skills have relatively short horizons, which make them uniquely amenable to reinforcement learning if you can get the recipes right. And so again, to illustrate the idea of parallelization, here's a task where I'm trying to insert a block into an environment, and I can parallelize this across many GPUs. What's really interesting regarding tactile-driven reinforcement learning is now we can render touch. Again, this is thanks to Tactile from Nvidia, where we've tuned the model to be able to replicate the tactile sensors that we have access to in our group. And these are extremely close to what you would actually measure on a real tactile sensor. In addition to just the raw RGB feedback, you can also compute shear. This is like shear estimation from the same signatures that you saw in the previous slide. They're not like exact, but they're pretty good. And what you can do is basically take your model, you can train in simulation, and with just a little bit of data in the real world. So on the left-hand side is a proof of concept that you can do vision proprioception for insertion. what's uniquely interesting is those are the gel sites on the right-hand side. And we just trained this think policy in simulation with about like 10-15 minutes of fine-tuning in the real world. You can basically do insertion skills with reinforcement learning. This is like we're about to have a renaissance moment, I think, with simulation and tactile. And so going to the idea of reinforcement learning, again, within the context of the challenges that we've talked about, well, what you're doing in reinforcement learning is you're often caching sample-based search. And so you're basically doing clever engineering to mitigate the domain gap in the domain that you've trained your reinforcement learning, or trying to mitigate sample inefficiency when it comes to deployment on your particular system. Now, I kind of drew this in this particular circle because during my career, we've actually traversed this circle. When I started my PhD, MPC was the thing to do. It was super cool. And then we transformed our attention to reinforcement learning, and now we're in the imitation learning land, and I think we're going to go back. This circle is going to continue, right? And I think the reason why is that we need to really understand that manipulation is a contact problem. It's a physics problem. And the language of manipulation is geometry and forces. It is not pixels. It is not necessarily language, whilst those things are helpful. The true language of manipulation I want to emphasize is geometry and force. If we accept this and that we build methods that truly address geometry and force, I think we're going to make a lot more progress than we are currently. And the TLDR of this talk, I will let SpongeBob explain. Gently. Without contact reasoning. And with contact reasoning.
How's this, Squidward?
Thank you.
Great. Thank you so much for the amazing talk. I think we have some questions lining up.
Uh-oh.
Oh, the mic is not on. Okay, now it's good.
Great presentation, Emma. Thank you. We talked about this yesterday a little bit, but I wanted to ask you again that one thing that stops people from exploring tactile is that the hardware breaks, and it's right there where you touch the objects and hit places. And that's been a big demotivating factor for a lot of people to integrate tactile in their stack. What do you think? Is hardware way behind? Do you think we need to wait for the hardware to catch up, or do you think a hardware solution exists that can work day over day, every hour, and without breaking?
I think my spicy take is hardware, this tactile sensing hardware is not an academic problem. I think that it needs significant industry sort of effort behind it, and I think that with a little bit of effort, it can be done. So for the example is like what material you use for your tactile sensor substrate is something that material scientists will know a lot about, but we don't have that many material scientists in this room, for example, right? The people who are using the sensors are not the people who are, does not intersect with the people who can make them really well. So I think if there's economic value in using tactile sensing and we can demonstrate that as a community, then I think that very quickly companies like Panasonic and Samsung and co, who are very good at making these things extremely reliable, will pick up. I think it's our job as the community to show that tactile sensing is useful. And I think it's often, as you're describing, it's an uphill battle, right? Like you have to show like, hey, this is good, but then the issue is like it doesn't last long and then they lose faith and then it's just like a cycle. What's going to break it is like our big aha moment of deploying at scale on something reasonable to show economic value. I think like improving even like 10% on some capability deployed in industry is like really like is going to be foundational. So a lot of these research projects were funded by Ford, by Boeing. There's definitely interest. It's just survivability, I think. And you're right. I think it just needs company work. It's not an academic problem.
Thank you. Any more questions from the audience? Oh, there's one more. Yeah.
Hi, Nima. Great talk. Really enjoyed it. So you showed 3 different paradigms for tactile-driven behavior generation and cycling through them. What about combining them all together?
Yeah, I think that would be super awesome. I don't know how to do it, but I think probably we're going to see these like big foundation models be the backbone. So if I'm doing MPC, what is hard about MPC? If I can initialize it well, then it actually converges pretty fast. It's the initialization that's like super hard to get right? So if I can use a pre-trained model that will give me a decent generalization and I'm willing to write down an MPC problem, that's like a very nice way to combine them. But they're currently incompatible in the sense that a VLA will consume vision, language, and proprioception and spit out an action, whereas like MPC prefers to live in state space, and so there has to be that conversion that will be the glue between the two. Right now we're just like predicting actions out of them, and so there needs to be like an inference step or a state estimation step in the middle, but I think we can make that work. MPC and RL are basically the same thing. The compute is done at different times, right? RL is computed basically offline effectively, and you cache all of your solutions in your policy network, and MPC, you're doing it all online. My guess is most of the time we're going to do MPC, and sometimes we're going to do RL. But, that's just speculation. Thank you.
Great. Thank you for the questions. And let's thank the speaker one more time. Okay, now I'm going to introduce our last speaker in this session. So that will be Laro Pinto. So Laro is a assistant professor at NYU. His work is spanning everywhere, like computer vision, machine learning, robotics. You can find him in all the conferences and also making big impacts in all this field. And recently, he has been focusing on large-scale robot learning, both in terms of how to collect data and also how to learn from those data. And today, he's going to tell us why robot data is not enough data. Welcome.
All right. Thank you. Thank you for the really nice introduction. I'm really honored to be here at the CORL. So maybe to just get things started, everyone is showing their favorite human video, so I'll show you mine. So I've been always amazed by hands, and this is the video I always show to sort of emphasize how amazing our hands are. So it's a task that most of us can do quite easily, right? Opening a Coke bottle. But if you think about the intricacies involved over here, you have to first acquire the object, put your index finger right under the tab, apply just the right amount of pressure to open the tab without spilling the drink all over you, right? So clearly really amazing, and all of us are able to do it in a quite instinctive way. Now what I think is even more amazing about hands is just the variety of things you can do with them, right? It's not just you're able to do that one impressive task. You can do so many things in wide environments. So really a lot of my research career has been trying to chase this level of human dexterity with a robot. Okay, so maybe just to summarize what my research goal is, it's to make robots as general as possible. That is, we want them to work anywhere for anything. Okay, now as since this is an early career talk, I want to talk to you a little bit about how I started my career in robot learning and give you a perspective of why I think about certain problems in a certain way. Okay, so when I started, it was in 2015. The problem I was looking at is how to pick up objects. Okay, so to set the scene over here, imagine you have a table in front of the robot. We use the Baxter robot over there. And the goal is to pick objects up that you haven't seen before. Okay, so I know this is 2015, but you'll see a bunch of demos now even struggling to get it. So it's still a hard problem. But we were trying to solve this problem in 2015. And really the predominant approach over here was using a lot of these modular analytic approaches. So the way you would go about trying to solve these problems is you would try to build 3D models of these objects, fit these 3D models on the objects, and use physics-based approaches to figure out how to grasp that object. Okay? And the problem we have seen with modular approaches is that if you have errors in any of these modules, these errors sort of compound with each other, and the overall performance of the system becomes quite limited. So it was clear that, okay, we need to do something about this. We cannot just go about just trying to improve individual modules over here. And around this time, learning was very ripe for these types of problems. Okay? And I think there are 3 main reasons why learning was ripe over here, and I want to sort of go over this. The first one was that we really saw that deep learning was starting to work. So if you look at vision and language problems, which were also modular maybe 5 years prior, in 2015 we were seeing these end-to-end deep networks sort of revolutionizing that. So that's one. We have seen a proof point of it actually working. Second, flops are becoming more accessible. The cost of these GPUs were going down, and so academic labs like ourselves were able to use these GPUs in-house and train robot models on it. And third, which is really important for academic labs, is that the cost of robots were now going down. And so, if you break your robot now, your advisor is like little less unhappy with you. Okay. So now with all of this available with us at this time, there is one key missing piece, right? And most of you are probably aware of it. It is data. For vision language models, you have plenty of data on the internet. For robot, especially for a manipulation-like task, there is no data. And so even with all these enabling features, we needed some way to get this data. Now, our choice over here was to get robots to self-learn, robots to, in a self-supervised way, collect their own data and learn from it. So here is our Baxter robot all the way in 2015, trying to figure out how to pick up objects. So the way it does it is tries out random grasps on objects on the table, and then from success or failure, it senses it using a sensor in its finger. It figures out if it was a successful grasp or not. And using this, you can keep improving the system and keep increasing the success rate of grasping. Okay, so this was sort of the wow moment for me in terms of robot learning, where we then took this system where you saw previously it was clearly very random, not really succeeding too much, and we put a set of objects the robot has never seen before in front of the robot, and the robot just like fairly robustly picks up these objects and drops it over in a bin near it. Okay, so this aspect of like zero shot, being shown a new object and being able to work on it was really something that I think kicked off a lot of my interest in robot learning. Okay, so since then, we have been expanding these ideas of data-driven learning to several other aspects. We looked at flying drones, and it's not just us, there were other groups as well looking at other tasks like trying to push objects on the table, and even scaling to many, many robots. For example, the amazing work from the Arm Farm team at Google. Okay, so this is like a lot of work being done, all the way up to like 2017, 2018. And so are we there yet? Do we have general robots? Clearly not, we are all still over here. So why? Why don't we have robots even though we can get robots to sort of collect data and train on it? So I think the reason we don't have it is because the data scale is still limited, and the data scale is primarily limited by robots. Okay, what do I mean by this? So the upper bound of how much data you can collect with robots is really the number of robots out there, right? And so if I just like, from scouring the internet, figure out how many robot arms have been sold so far, it's around like 5 million. Okay, so the amount of data is sort of like limited to this. But if you think about vision and language, the hardware to create this data is things like phones, things like laptops. This scale is like multiple orders of magnitude larger than robot data. Okay, so if I'm trying to make a comparison over here, that small dot is total number of robot arms, and just for iPhones, which is one type of phone, it's 3 billion of them out there. Okay, so we need a new way to collect data if you're thinking of bridging a data gap. And so our main question over here is, how do we get a robot in everyone's hand, right? How can we get this robot data without actually making a robot? So what we built is sort of these handheld tools. The way it looks like is sort of a reacher grabber like this over here. So it has soft fingers at the tip. You can sort of open and close it using a trigger, and you sort of strap an iPhone on it. So the overall cost of this system is fairly low if you already have an iPhone with you. Now, once you train a model on this type of reacher grabber type data, well, you can just stick this on different robot end effectors. So this is one on the Hello Stretch or Hello Robot Stretch, and you can put it on other robots like the XM over here. Okay, now since this is quite scalable, we took this to a bunch of homes all around New York City, trained models for things like, opening drawers, closing drawers, simple like pick and place like stuff. Okay, now although I sort of say it as, it's done and solved, this has been a long-term research effort for like more than 5 years. We have like iterated over like gripper designs, types of cameras, and it's not just our group, right? So even groups like Sharan's group has made really amazing advances, like the Yumi tool, to sort of scale this up. Okay, so where are we right now? We are in a place right now where we can collect enough of data that models trained on this data can give you zero-shot performance. So we can take some of these models, go to random Airbnbs in New Jersey, and show that a robot can like open a microwave door, do some very simple pick-and-place tasks over there. And even at the last CORL, we took this robot. There we bought an IKEA cabinet, surprisingly different IKEA cabinet to the ones we had seen in the US. And it works quite well. It works quite well even if you have like a transparent door on it. Okay, so are we there yet, right? Again, clearly not. We're still here. So what is left in scaling? Why are we not able to scale even more? So I think even though we're able to use all of these like phones and all of these other devices to get the data, I think the main limitation now is the data collectors. It's the people who are involved in the process of this data collection. So if you think about it, right now, every piece of data that is being collected for robot learning is collected only for the goal of robot learning, right? And so this just makes it too expensive. It makes it too expensive, well, unless you have like, I don't know, billions of dollars of VC funding to burn over here. But like if you're trying to do this in like a more efficient way, we need a different way of going about it. Okay, so the way that I'm sort of super excited about is by looking at other sort of emerging consumer devices. So for instance, a stat which I found out recently is that the Ray-Bans, these Meta smart glasses, they've already sold a couple million of this already and close to 10 million this year, which is already larger than the number of robot arms sold, okay? And so what we have been looking at is ways in which we can train models using these types of smart glasses. Okay, so this is the Aria glasses over here. If you're not familiar with the Aria glasses, there's a Meta booth over there where they have a new version of it, so please feel free to try it out. All the pixels you're seeing over here are actually pixels recorded on these glasses. So the goal here is we can actually collect data by humans interacting with the world just wearing these smart glasses, and then without any robot data, in a zero-shot way, train robots to now do similar tasks. Okay, so let me just let this video play out. Okay, so we're looking at sort of two aspects or two axes of zero shot over here, right? So there's one axis where we want to go from human pixels, human action space, to the robot action space. And the second aspect is we want to also get zero shot in terms of the environment, in terms of the objects. We want these models to really work in new scenarios that they have never seen before. And so we're able to see this using emerging architectures that our group is building and also groups over here at CORL. All right, a sort of assumption I've made so far in most of the works I've shown is that we are going to use, or we use only visual inputs, right? And you know, if you are convinced by the previous two talks prior to me, this is clearly not enough. We cannot do it with only visual inputs. And so to sort of just emphasize this, here is a task we ran in a lab, which is to pick up an egg and place it inside that bowl, and this is trained only with visual inputs. Okay. So clearly it's not going to work, right? Because it has no idea of how much force to apply on this egg in order to pick it up. If it applies too little force, it's going to slip. If it applies too much, it's going to crack. So here is a tactile sensor which our lab has built. It's called AnySkin. It's based on a magnetic-based sensing principle. So that sort of skin you see over there is basically an elastomer with magnets embedded inside it. So when you apply pressure on it, you can sense the magnetic fields around it, which gives you the sense of touch. Okay, so if you have used GelSight before and are not happy, come speak to us. Okay, so with this sensor now, we can in a very cheap way train models and policies to pick up sensitive objects like this egg fairly robustly. And yeah, like I've shown this video before and they were like, is this egg a raw egg or a boiled egg? And yeah, you have to trust me, it's a raw egg here. Okay. Okay, so right before I end, I want to talk to you about what are the problems that we are working on right now, and maybe some initial results or initial sort of directions that I think is going to be really important for the next 5 to 10 years. So I think the first one is going more towards multi-fingered hands, right? And sure, you know, there are like reasons to do multi-fingered hands if you care about high levels of dexterity on them. But I think an even more important reason to use them is because our hands are multi-fingered. And so if you're trying to learn from human data with multi-fingered hands, you really need to get this form factor as close as possible. The second thing is sort of combining this like touch information and the vision information. Again, it might be sounding like a broken record with the previous two talks, but I think this is really going to be critical if you want to get the levels of efficiency that, you know, if you do not want to go and try to collect huge amounts of data like the VLMs, I think you need to get this to become more efficient. Now, throughout this talk, you would have noticed that I did not talk much about algorithms. I didn't talk much about architectures. And that's because I think that most of the architectures and algorithms we are building right now are not the right way to build it. There's no way we can sort of go towards the level of creativity and reasoning that even animals are able to do. So here is Patrick the orangutan being able to tie knots. Clearly did not have access to VLA models, but is able to do it. And so really, how do we build architectures and models that can get this level of creativity and reasoning? That's something which, again, I'm really excited to be solving. So this is my last slide. Since this is an early career talk, none of this work would have been possible without my amazing lab, amazing group of friends and mentors. So yeah, big shout out to them, and I'll end over here. Thank you.
Great. We already have questions lining up. Please take it away.
Right. Thank you so much for your talk. It seems to me that the industry is moving towards a direction where we're trying to create a single policy that can cut cucumbers and fix car engines both at the same time. But maybe the way is to just create specialist policies, one policy that does something really, really well. And in that case, what is it that prevents us from scaling such specialist policies? I don't think it's data, really. Maybe we can have a specialist policy with a few amount of data. What is blocking us there in scaling those?
Yeah, I think a few thoughts over here. So I think from an academic standpoint, right, you'll very rarely see papers over here which are like, oh, we get like 99.9 rate of success, right? Everyone's trying to go for like 60% rate of success, and once you hit that, you sort of stop. So I think if you're really trying to create specialist policies that get high rates of success, we have to change the sort of academic mindset where like 60% is like a good enough thing, right? Now, of course, I'm not saying that's the right thing for everyone to do, but if you care about putting your models in deployment, you really have to think about what the success rates needed are going to be over there.
Thanks for the great talk. So the previous talk, Nima made the point that we need contact reasoning, and he promised that if we achieve contact reasoning, then our robots can be like Michelangelo, right? And you made the point that we're data hungry, and we need better data, and you're talking about data that may have some information about contact, like touch. So do you think just going more, getting better data that have some contact information will solve and have this contact reasoning ability?
Yeah, this is, again, a great question, right? It often seems that sometimes data-driven learning is at odds with like contact-rich reasoning, and I don't think that's the case. I think there are ways to sort of mix them together. I do think that fundamentally a more analytic approach is not going to scale, because you'll have to then get these laws of physics for every single operation out there. So I think even a lot of Nima's work has been looking at how you get these very like intuitive learned models. And I think that's really one of the right ways to go, where with the same data, you can train these world models, as they are called now, and sort of optimize on them. So I think that's probably going to be the way to go, where you're combining this data-driven learning along with the principles of forward search with them. Yeah. Thanks.
Great. Any more questions from the audience? Oh, there's one more, yeah.
Hello, thanks for your great talk. I have a question about the data collection. You mentioned that maybe in the future we can use egocentric glasses. Do you think in the future privacy could be an issue for data collection, like beyond robot data? And my second question is, you also mentioned that tactile is very important, but I feel like today, tactile sensor might be less scalable than robot arms itself. How do you collect more and more tactile data?
Yeah, great question. So I think on the data privacy side, I feel like as a society, we are getting okay with our data being shared, right? Like if you go out there, you see so many people with their phones out, taking videos, uploading it to Instagram. So I think these problems are just going away from a society point of view. I think there's a separate question if you're trying to collect data inside people's homes and their private life. Now that I'm not sure about, and maybe I think we probably do not want to look at that as the first problem. The second question you asked about was about the tactile data, how you scale that up. I think scaling up the tactile data requires tactile sensors to themselves be really robust. This is why I personally do not like any of the sort of like a gel side or optical way of doing things, just because of the lack of robustness and transferability in them. So I think we really need a new form of tactile sensing that can be scaled in a way that has not been seen yet, right? And once you scale that up, think about all of these devices now having natural tactile sensing in them. So I think that's probably the right way to go over there. Yeah.
Thank you.
Okay, one last question.
Okay, thank you. Quick question. So we were talking about the scaling of the robot data, and there's like a vision data. You can be scaled with like egocentric glasses, all that. Do you think the scaling of the vision data and tactile data needs to be happening at the same time, or can they be happening like separately? Then you merge them together.
Great question. So I don't think we have to try to solve all the problems at once, right? I think what we are seeing is that vision is really good for just fundamentally knowing where things are in the world. And tactile is really good for once you acquire objects, what do you do with those objects, right? So I do think there's a way to sort of like, just intuitively modularize it through these models. So you can think of maybe a large model taking in visual information, language information to get close and acquiring the objects, and then really, not thinking about language or vision and just focusing on this tactile information for the precise movements you need to do. So again, I think this is a lot of greenfield research that I invite all of you to like work on, and if you have thoughts about it, would love to speak more. Yeah, thanks.
Great. Thank you so much, everyone. And this is the end of this session. Let's thank all the speakers one more time. And then next is lunch. Hope you enjoy.
Omron Cynic X quickly captures signs of change in the world and the social issues that arise from them, designs the near future, and aims to create innovative technologies necessary for solving those issues. In particular, we are focusing on research into the evolution of AI agents with physical bodies and 5 senses. We aim to create a society where these AI agents enhance human autonomy and independence, enabling people to enjoy creative activities.
presenting. Speed, rolling.
Can you believe it's been 20 years of robots?
People.
Innovation.
Collaboration.
Challenges.
Leading. Growing.
Conversation.
Expanding.
Serving. Mission. Research.
Participation.
Recognition.
Pioneering.
In the race to build truly intelligent and general-purpose robots for all applications, one element stands above all. It's data. Max Insights delivers large-scale, high-quality and cross-embodiment datasets for embodied intelligence and general-purpose robots. Using precision motion capture, we capture human data and retarget it across different robot embodiments. Our high-quality data is collected from real-world environments, including not only bedrooms, living rooms, kitchens, garages, and laundry rooms, but also warehouses, restaurants, and other everyday settings. We offer data collected using the same robotic arm across different scenes, as well as data collected using different robotic arms in the same scene. If you're building robots and want better models through better data, it starts here. Embodied intelligence starts with Max Insights.
There's a robot in my bathroom. What do you do here? Wait, come here, come here, come here, come here, come here, come here.
What are we hitting? Chest, legs, back?
I think I'm doing back today.
I spent the last decade of my life working on building humanoid robots like Neo.
So far.
Oh, here it comes.
That's so great.
Oh my gosh.
I can't even go.
I'm gonna take some robots into the jungle.
Vinny, what do you have to say?
I'm tired. New problem.
Oh my god, he's squatting.
Redwood. Oh my god. Okay. So I'm not a rapper. I'm a magician.
No way, really? That's great. Yeah. Not good enough.
Yeah, that's a moment like I feel like, hey, we can do it.
Fan, what are we doing?
We're about to go to TED.
Where are we in Vancouver?
It's about creating a future where we actually have time to focus on what matters to us as humans.
腾讯 Robotics X 和福田实验室基于过往多年在机器人领域积累的技术能力，广泛结合产业端需求，发布了规划大模型、多模态感知模型、感知行动联合大模型。各个模型之间通过多模态感知、规划、记忆等模块的协同工作，转化为机器人的具体行动。规划大模型作为机器人的大脑，具备自我认知能力，通过与人类自由沟通、拆解任务、调用工具、查询知识库和在执行中的自我反思，最终完成长程复杂任务，并可为特定领域提供角色问答服务。
欢迎参观腾讯机器人实验室。
来，我们握个手吧。
当然，很高兴认识你。
多模态感知模型可实时整合环境感知数据，构建语义丰富、空间关系精确的3维层级地图。
你们俩去站在前面2个几何雕塑中间，我给你们拍个合影。
支持自然语言输入输出，实现多场景下的高效信息检索，助力机器人精准完成任务规划与环境交互。感知行动联合大模型结合快慢系统思考与时空物理感知，有效赋能灵巧手、夹爪等多种末端执行器在复杂场景下对多样物体的操作能力。同时，针对人形机器人训练得到的模型，可实时感知机器人本体信息、环境地形信息，并做出及时响应，控制各关节协调运动，进而控制机器人灵活移动、灵敏运动。目前 Hyros 已经适配过双足、轮式人形、4足、机械臂等多构型本体，操作支持夹爪、灵巧手等多种末端执行器，与多家机器人企业在工业、汽车、家电等多行业进行场景落地实践。未来期待与更多机器人企业联手，共同推动机器人行业发展，共建人机共存、共创共赢的未来。
Omron Cynic X quickly captures signs of change in the world and the social issues that arise from them, designs the near future, and aims to create innovative technologies necessary for solving those issues. In particular, we are focusing on research into the evolution of AI agents with physical bodies and 5 senses. We aim to create a society where these AI agents enhance human autonomy and independence, enabling people to enjoy creative activities.
Can you believe it's been 20 years of robots?
People.
Innovation.
Collaboration.
Challenges.
Leading. Growing.
Conversation.
Expanding.
Survey. Vision.
Research.
Participation.
Recognition.
Pioneering.
In the race to build truly intelligent and general-purpose robots for all applications, one element stands above all. It's data. Max Insights delivers large-scale, high-quality and cross-embodiment datasets for embodied intelligence and general-purpose robots. Using precision motion capture, we capture human data and retarget it across different robot embodiments. Our high-quality data is collected from real-world environments, including not only bedrooms, living rooms, kitchens, garages, and laundry rooms, but also warehouses, restaurants, and other everyday settings. We offer data collected using the same robotic arm across different scenes, as well as data collected using different robotic arms in the same scene. If you're building robots and want better models through better data, it starts here. Embodied intelligence starts with Max Insights.
USB-C or HDMI to also. They all work fine. So just allow and should I? Because I want to see my nose then. I should probably just do extended.
Maybe extended display and
okay. I'll just see. Oh,
okay, great.
Yeah, I see. Okay.
It is working.
Okay, thank you so much.
This is MS-TV drawing.
Hangzhou, sure.
Is that guy?
Alrighty, welcome to the second part of Diamond Sponsored Talk series. So my name is Jonghyun Choi. I'm one of the co-sponsorship chair.
Hi everyone, I'm Aditya. I'm from Nvidia. I'm also a sponsorship chair.
Today's first talk is given by Heng Zhao from Galaxia, and also he's an assistant professor at Tsinghua University. And he's going to talk about recent attempt or discoveries by Galaxias on the robotics regime. So please give a big hands and welcome Heng Zhao.
Hi everyone, I'm Heng Zhao. I'm a co-founder of Galaxy and the diamond sponsor of this CORL conference. And I'm also an assistant professor at Tsinghua University. Today I would like to share our journey at the intersection of robots, data, and the foundation models. At Galaxy, our goal is to shape the robotic ecosystem with three pillars: hardware, models, and tools. On the supply side, we cover everything from motors to teleoperation systems to data and models. And our products combine three elements: robots as the physical embodiment, and our pre-trained foundation model as the brain, and post-training tools for evaluation, fine-tuning, and deployment. On the market side, we work with both enterprise clients and the developers, building what we call robotic application ecosystem, empowering others to accelerate the embodied AI industry. To support this vision, we have already built R1 series of robots. On the left-hand side is our R1 Pro robot, our next-generation humanoid platform, designed for navigation, manipulation, and complex embodied tasks. And on the right-hand side is R1 Lite, a mobile manipulator that shares the same software stack, but comes in a more compact and a scalable form. You are welcome to take a look at our robots in our booth in the exhibition. Of course, the robots only matter when people actually use them. That is why we have worked very closely with universities, research labs on developing applications on our robots. Here are some examples of research papers from these universities and research labs. And we have also a lot of industry partners. Here are some demonstrations of industrial tasks and autonomous workflows. And here are some featured partners. At Stanford, people are exploring household tasks with our robots. They developed a model called Whole-Body VIMA with a teleoperation system called Joylo, and they have also released a behavior dataset. And the Beijing Academy of AI has recently released a VOA model called RoboBrain X, which demonstrates the zero-shot generalization and lightweight fine-tuning capabilities for solving complex tasks. And physical intelligence also developed their PI5 model with open world generalization on our platform. And up to now, our Galaxy robotics community has over 100 customers globally. Now, let me turn into our own efforts in intelligence. 2 months ago, that we open source Galaxy open world dataset and G0 dual system VOA model. The Galaxy open world dataset is the world's first dataset that is open source that's collected in the open world environments: apartments, hotels, offices, and warehouses. And with this dataset, we train our G0 VOA with the dataset, and the model generalizes well in downstream tasks with few-shot capability, including challenging whole body manipulation tasks like making the bed. Here are some tasks that are trained with only 20 episodes or trajectories. Okay, and since we released the Galaxy Open World dataset, it has been downloaded more than 120,000 times, ranking #1 globally on Hugging Face and the ModelScope. This shows the community's demand for authentic embodied data. And more details about our VOA model. Our G0 dual system VOA model has a slow-thinking VOM that handles language understanding and task planning, and also has a fast execution system that does real-time motion planning and closed-loop control. Together, they allow a reasoning at 2 Hz and planning and control at 20 Hz, just like humans think slowly but act quickly. To train the model well, we designed a 3-stage training pipeline. The first stage is cross-embodiment pre-training with cross-embodiment robot data. This stage is trained in an autoregressive way, and we find that action tokenization is actually the key ingredient in this process. And the second stage, pre-training stage, is single embodiment pre-training, where we use our Galaxy open world dataset to pre-train the model. And finally, the post-training stage only requires 20 to 100 task trajectories. Finally, I would like to share some lessons that we have learned during this process. The first lesson that we learned is about the data. That the robot data, we are actually suffering from a new domain gap that is called real-to-real gap in data collection. In order to scale data collection, many companies today, they are trying to build in-house robot data collection site so that they can collect data more efficiently. However, the real homes are messy and unpredictable compared to the robot data collection site. If the robots are going to succeed in real life, our data must reflect their reality. This is why we also emphasize open world, messy, and long horizon data collection. This echoes Professor Jitendra's Airbnb challenge, that if you want to succeed, if you really succeed in an Airbnb home, and then your robot really generalizes. Another important lesson is about evaluation. The evaluation must be standardized, and it is so important to benchmark the progress of our models. However, robotics is a very complex system. Tiny differences in the hardware or environment can lead to huge differences in the results. So this is a system engineering instead of model engineering. So we took 3 best practices. First, every time that we are going to start the evaluation, we will perform log replay on the robot. And we find it to be a very good sanity check on the environment settings, and also the robot postures and the positions. Second, in order to ensure a high success rate in the closed loop evaluation, the first thing that we need to do is actually high performance open loop evaluation. If we get a good number in open loop evaluation, then it is more likely it will succeed in the real world. And third, parallel evaluation across models is also very important. Every time you do the evaluation, don't just do evaluation on one model, but on multiple models. Because each experiment, between the different experiments, there are tiny, tiny differences. In order to make sure that they are close enough, do all the experiments, evaluations at the same time so that you get the rankings of the models correctly. Looking ahead, we are at very, very early stage of this journey, and we are expanding our open source roadmaps. Next month, October 2025, we'll have more open source plans. Here's a preview. First, we're going to open source another 500 hours of R1 Pro data, in total reaching 1,000 hours of data with more comprehensive annotations. And in terms of models, we'll release new models, G0 models with different model sizes. And we will also release G0 Plus with zero-shot pick-and-place generalization capability. Finally, we'll also open source more tools, such as cross-robot calibration and high-performance inference code, so that our developers can use the robots more easily. The goal is to lower the barrier for the whole community so that everyone can build on top of Galaxia's robot. That's everything that I have for today. If you are interested in us, in our company, please follow us on X. Thank you.
I guess next up we'll have Yuka from Nvidia. Yeah. Hey, I'll just briefly introduce Yuka. Fellow colleague from Nvidia, Yuka is a director of the Gear Lab. He's also a professor at UT Austin.
Oh, good. Cool. All right. Good afternoon, everybody, and thanks for the introduction. So it's a great pleasure to be here and to share some of our recent updates on humanoid initiative at Nvidia. So to start today's talk, I would say that I want to do a time travel back to 2023, and we heard 3 amazing early career keynote talk in the morning. In CORL 2023, I was honored to be one of the early career keynote speakers. And during that conference, where I got to share some of my views for building models for generalist robot. And I argue that to succeed, we need a trinity of 3 key elements, like the algorithm that scale with data and compute, and data flywheel that generate immense amount of training data, and finally, robots share human-like physics, right? Because their hardware embodiment determines their capability envelope. So back then, in 2023, I think humanoid robotics is still a relatively small niche research area. In fact, when I first became a professor at UT Austin, I have to build a custom humanoid robots there and to carry out this research because simply there's nowhere to buy one. Well, when I give that talk, I have absolutely no idea that a few months later that I would be given the opportunity to start and co-lead a new team at Nvidia to build robot foundation model specifically for humanoid robots. So you might have seen this picture on social media, right? So a bunch of humanoids standing on the stage of Nvidia GTC 2024 conference in San Jose, California, that our CEO Jensen is the only biological one. And he announced a humanoid initiative at Nvidia. Just like many other technology, I think like the growth of humanoids in the past 2-3 years is truly remarkable. It really follows a nonlinear trajectory. It happens gradually and then all suddenly, right? And so to accelerate the development of humanoid robotics, and we started as a group at Nvidia, it's an open humanoid development platform. So that really encapsulates the 4 pillars of effort, right? So one is an open robot foundation model, the simulation frameworks that's powered by Nvidia Omniverse and Cosmos, and the synthetic data generation and processing pipelines, and finally a robot supercomputer that's running on the robot, running the entire robot stack on board. Particularly, I want to highlight Thor, and this is our new chip coming out of Nvidia recently that delivers 7.5 times more AI compute than the previous generation Jetson Orin. It has a 3.5 times more energy efficient, 10 times more throughput. And we actually have a Thor demo running in our booth with our GROOT foundation models, and you should definitely check it out. During the conference, it's a very incredible and impressive piece of hardware. So my team specifically focused on building the foundation model. So the GROOT N1 foundation model is a 2-layer dual system architecture that integrates a System 2 vision language backbone and System 1 diffusion transformer. So it's a by far pretty standard model architecture that maps the visual observation of the robot and the language commands to some high-frequency motor control signal. So the pre-trained model already have very strong generalization capability. It can follow language commands, and so it can perform tasks across different robots and different goals. It generalizes across a variety of embodiment. And then the model can be further post-trained on a small number of demonstrations to perform more complex, like this industry one, that involve 2 robots running 2 post-trained GROOT model side by side to perform this complex task in industry settings. Okay, so when it comes to foundation model, we definitely need continued innovations on the model architecture. But I would say that what's equally important and arguably more important is the data strategy. You probably already hear this again and again throughout this conference. And I anticipate that without any architecture change, simply by having higher quality and more diverse and data sources, our GROOT model can continue to expand its capability for another 6 months to a year without changing any architecture, right? So at Nvidia, we really seek to leverage a diverse range of training data, which I organize by size into a pyramid. So the top of the pyramid is a real robot data. So these are the things that that are coming from the hardware you collected usually through human teleoperation with hardware in the loop. So they are highest quality data because they come from real-world sensor, real-world motors. But the catch is one robot can at most contribute 24 hours of data per day, right? And the middle layer is a simulation and synthetic data. These are the things coming from the graphics renderers and physics engine, now neural models, right? So these are, in principle, you might argue that as long as I throw enough compute, I can generate infinite amount of data. But the challenge is how do we generate realistic, high-quality data that's useful for model training? And the bottom of the pyramid is the human video and web data. So these are the things that are sitting around from the internet that we can harness, particularly for humanoid robots, the human-centered data source can be quite useful. And there's just an immense amount of training data available. The human society collectively generates exabytes of data per day on the internet. Exabytes is an astronomical number. It's millions of terabytes, right? So, but the catch is like that they are usually unstructured multi-model, so we need to be a bit smart on how to use that. So a lot of our research examines, right? So given all these data sources, and we don't want to pick favorites, like how do we kind of leverage all of these data sources across the data pyramid? Today, I want to particularly focus on the middle layer of the pyramid, which is a simulation and synthetic data. And here at Nvidia, we see that synthetic data generation is a viable way to complement the limited amount of real data one can feasibly collect. And using simulation, we can turn the robot data collection problem into a computation problem, right? So that the question is like, how can we effectively use simulation and generate them in high quality and high quantity? So let me share two key ideas we have been exploring recently. So the first strategy is called group mimic, where we generate simulated trajectory using a physical simulator in the loop, like Isaac Lab. So given a handful of human demonstration, you can collect it through teleoperation. We can transform those trajectories within a physical simulator to new object initialization and replay that in simulation. As you can imagine, some such trajectory will be successful, some will fail, and we can keep the successful one as augmented data set for model training. So by leverage computation and simulation, we can increase the amount of training data by orders of magnitude, right? And we published this work called DexMimigen earlier this year, so you are welcome to check more technical detail. After that, we have been continuing to extend this line of work and to expand the capability of our data generation system to different robotic problems that includes long horizon tasks, the multi-stage tasks with task and motion planning. And now it can handle soft and deformable objects in Isaac Lab. And of course, humanoids, local manipulation, is particularly in factory settings. And today, I want to also share some updates on the physical simulation framework that we are building at Nvidia, Isaac Lab, and Newton. Newton is a collaborative open source effort to create an extensible framework for GPU accelerated physics. And this is a joint effort between Nvidia and Disney Research and also Google DeepMind. So now the beta version is available on GitHub. Like you should definitely check it out and try it out yourself. We also released an experimental version of Isaac Lab now with Newton support for you to play with. And there's an upcoming version of Isaac Lab 2.3, also a lot of the nice features that support humanoid robotic development. So please do try it out yourself. And then additionally, finally, we have a long overdue Isaac Lab white paper that's now available online. If you search the title, you're able to find it from the Nvidia website, and the paper will be posted on archive in the next couple of days as well. So I talked about the first strategy using physical simulation. The second strategy is called Groot Dreams, where we use this emerging from a family of a visual world model to generate neural trajectories. So we use models like Cosmos Predict to generate realistic videos like from image and language instruction, then use Cosmos Reason, a vision language model, to just sift through and filter out the bad examples. So using this approach, we can automatically generate hundreds of hours of dreams on our compute cluster within hours of wall clock time. So in contrast to the previous form of synthetic data, right? So the simulation data from Groot Mimic, the generated video do not have action labels. So we need to train another AI model to annotate the robot actions between adjacent frames. So the detailed approach is described by our DreamGen work, which we present at this conference. Okay, so now we have these three data sources. Let's put them together, right? So we have the real robot data, simulated data, and then neural trajectories. The real robot data are small in size, they are costly to collect, but they got collected in the hardware in the loop, so they are most realistic data we have access to. And then the simulated trajectories, and they come from physics engine like Isaac Lab. They usually have some rendering gaps, like you can still tell apart as a simulated rendering versus like real images, but the actions are grounded because they are derived from physics first principles. And then the third form data, which is neural trajectory from good dreams, come from visual world model, like Cosmos, right? So they look as realistic as real robot data, and sometimes they can simulate a very complex physical phenomena that traditional simulators struggle to do, like think about fire and water. But the actions here can be noisy because they are predicted by another model. Right? So given the kind of a complementary strengths of such three different data sources, we come up with a simple and effective strategy to learn from this kind of mixed data sources. And you might hear the co-training word. So in a couple of talks in the morning, right, I think this is kind of becoming a quite common strategy people use to leverage heterogeneous data source. The high-level idea is simple, that we just sample batches of data from different data sources with some load balancing during training. But to get co-training to work, I would say that really devils in the details. So the same man wheel needs to roughly match for it to transfer knowledge across domains. So if you're interested in the technical detail, you're welcome to check out the paper that we published in RSS earlier to describe all the nuts and bolts and to get co-training to work. Really, I think $1 million question here is, we have so many data sources, like, are they actually helpful for model training? And I see this as $1 million question literally, because it requires a lot of GPU compute to do ablation on pre-training. And luckily, at Nvidia, we are GPU rich. So we have done this ablation study with our GR1 humanoid robots. The results are very fresh, and we have never showed this to any public audience yet, but I think it's quite encouraging. They show that like both the simulated trajectory and neural trajectory helps positively, and if we combine both, and it leads to the highest task success rate. So our GR00T models is publicly available on GitHub. You can search as a GR00T to find the link. We have seen the research community and our industry partners adopt our model and deploy on a variety of robot platforms. The latest version currently is called a GR00T N1.5, where we focus on humanoid upper body by manual manipulation. So moving forward, we want to unlock the entire kinematic range of the humanoid. So that's why it makes sense to be a bipedal humanoid. So our N1.6 will come up soon, so let me just use a video to give you a quick look of what's coming next. So I hope the sound works. Okay. Okay, you can hear the sound stepping, right? So here we're training a whole body controller with reinforcement learning to generate human-like motion. This is one controller generates all kinds of human-like behavior. Model is trained in ASIC lab and transfer zero-shot to the real world. The models can understand natural language commands, and the person is typing, "Get me the healthiest snack." And then it navigates to the target location in a complex 3D environment. This is actually the Nvidia headquarters. You see people are working in the background. So the robot is navigating using its egocentric onboard perception. So it's approaching the desk with a bunch of food there. As it's approaching, it's running a Cosmos reason model, which is a VOA model, to reason about what the robot is seeing. Remember, the task is to get the healthiest snack. So there's a potato chip, there's a cookie, there's apple. What did you choose? Of course, apple. So the reason model decides to grasp the apple, and then you see, like, so we have some visualization of map here, right? So it's localizing itself using vision-based localization running on board. The navigation capability is training completely with synthetic data generated from ASIC simulations. So I want to remind you that, like, so this video is 1x fully autonomous. You know that Nvidia, our marketing team is very talented, right? So they made a beautifully edited Hollywood version, but I'm kind of adamant to show you this uncut version to keep everything real. As the robot reorients itself, it's tossing.
Thank you.
Yeah. All right, so that's the simple behavior, again, done by our GR00T model. So tossing seems trivial, but you know how much engineering we put into it to reduce the latencies and to get this whole system to work and in order to toss, right? So when it comes to building humanoid robotics, it's not just about chasing after flashy research ideas. It's also about getting the engineering right to squeeze every bit of the performance out of the system. So I want to conclude here saying that many of our NVIDIA robotics team members are here presenting at this conference, so you should come talk to us and visit our booth to learn more about what we are doing. Thank you.
Thank you very much, and that concludes the Diamond sponsored talk session. And thank you for all for coming here. And that is followed up by the oral session 4.
Thank you. So, hi everyone. My name is Georgia Halvadzaki. I will be now leading the discussion of the oral session 4 on planning, safety, and robustness. Please, the speakers, line up. And a bit of housekeeping as before. I think you know already when the one speaker finishes, the second one sets up so that we can be fast with the transitions. So, our first oral is real-time out-of-distribution failure prevention via multimodal reasoning. Please set up, and when you're ready, we can go.
Slideshow? Allow, and then extend it. Do you have any sound? No. Oh, okay. Oh. Maybe. Oh, try to present. Play from start. Okay. Yeah.
You can start if you're...
Okay. Hi, I'm Milan Ganai. I'm a PhD student at Stanford, and I'll be talking about our work on real-time out-of-distribution failure prevention via multimodal reasoning. So autonomous systems have been expanding their deployment regions from localized structured environments to more open world settings. And in the process, they may encounter out-of-distribution situations inevitably. And these can be different from the training data as well as the design assumptions. This increases the risk of out-of-distribution failures that go beyond just collision avoidance or collision hazards. And these can cause damage to the hardware, endanger human users, as well as cause environmental hazards. So there's a lot of work on runtime monitoring, detecting OD situations, but once we detect it, we need a response. And so these responses to prevent the OD failures require identifying appropriate fallback strategies, adaptively detecting where exactly in physical space is there an unsafe region, and then rapidly generating fallback plans that are safe. So we're building a lot of prior work on foundation models for fallback responses. These foundation models have been shown to have these common sense capabilities to understand OD situations, and they've been used to debug the edge cases and do high-level reasoning about appropriate responses and choosing those appropriate responses. But off the shelf, these foundation models are not dynamics aware. And so this limits approaches to localized repairs, hard coding the fallbacks, as well as human interventions. And those are all impractical for large-scale open-world settings. Also, querying these foundation models can incur significant latency, which is not practical for safety-critical scenarios and agile robots. So we propose our method, Fortress, which is a slow, fast hierarchical method. At a low frequency, during the nominal operations, we're preparing ourselves with reasoning about semantic safety cost functions as well as fallback strategy goals. Then once a runtime monitor has triggered the need for a fallback response, we can synthesize from the cost functions as well as the goal coordinates a fallback plan very rapidly at the safety critical moment. So one of the important things is being able to concretize a fallback strategy. You know, humans or LLMs can identify these high level and do common sense reasoning about high level semantic descriptions of fallbacks. So land on a building rooftop or an empty park. And so we can take them and query a vision language model such as Mulmo to identify 2D pixel key points in an image, and then use depth sensing or camera intrinsics to convert those into 3D goal coordinates. We also need to consider safety in these plans. These are obviously OD failure situations. And so our approach involves anticipating them. So we will have a scene and we'll have the agent query a vision language model reasoner about what are some high-level terse descriptions of failure modes. And so this can look like worker injury or sharp objects. We can extract from the reasoning traces these failure modes and store them. Additionally, autonomous systems are generally previously deployed and have collected a lot of safe data. These include a lot of mundane objects like people and cars and trees and so on. So we won't have a lot of failure data per se, but we'll have a lot of the safe data. So we want to make use of it. We can convert those images into actual text semantics data. And then ultimately we want to be able to find relationships between failure modes, this textual data, as well as new scenes coming in. And so we're going to embed these using text, or you can use multimodal embedding models to embed these and get these embedding vectors. So we have our failure embedding. We also have our safe embedding vector database. Eventually, what we're building is a cost function, and this cost function essentially looks like taking a new scene and seeing, is that new scene or new region in space, if that description is conceptually abnormally close to the failure mode as opposed to all the safe data. And so the way we concretely do this is using conformal prediction on the embedding similarity to failure. This involves some sort of quantile thresholding on the safe data. So there's going to be some trade-off between FPR and false positive rate and true positive rate, but we get a threshold saying that beyond this threshold, we're probably we're going to probably experience this sort of failure. And we can take this threshold and construct what we call a semantic safety embedding cost function. And what it really is a cost function that detects regions in physical space that have descriptions that are semantically similar to the failure mode. So here's a concrete example. We have a cost function like worker injury that we have calibrated with conformal prediction and so on, and it's meant for the animal quadruped robot in a room under construction. And it sees, oh, there's a ladder, and so that's not going to cause a worker injury, but a person on a ladder is going to, if the animal robot is too close to it, can destabilize the person and cause a worker injury. And so we're able to detect this sort of nuance. So we took these embedding cost functions that we generated and calibrated and went around a room under construction with the animal robot. And we saw, for instance, there was a cable. We detected the cable, and we detected that that could potentially cause an entanglement failure if the animal robot were to be right there. Or even if it were to cross a caution tape, it would cause an unauthorized access failure. But individually, a person or a ladder is safe because the animal robot can just stop in front of it using a normal safety filter like a CBF, but a person on a ladder together would be considered conceptually unsafe for the animal robot because, again, it can destabilize the person. So now that we have the semantic safety cost functions, we have our goal coordinates, we need to finally now create a fallback plan at the safety critical moment. So we've prepared ourselves for this moment. So at this moment, we have this optimization that we formulate as a reach avoid problem. And so part of the constraints is reaching and remaining inside the vision language model identified goal. And our optimization consists of trying to avoid any failures, so minimizing the worst case failure along the trajectory. So it comes in the form of a mini maxi-max, but not very hard to solve. You can plug in any planner or tracking algorithm like RRT, MPC, LQR, and so on. So the TLDR for this is you can slide in our embedding cost functions into any motion planner you want and make your plan semantically safe. So here's an example of how we deploy our algorithm end-to-end on the quadrotor drone. It identifies that there's a building under construction, there's a building on fire, and there is a rooftop parking lot, and so it avoids these conceptual failures. But is able to understand, okay, there's a rooftop garden and that's a good place to land. So it chooses to land at that point. So here are some takeaways. So we propose a method called Fortress for OD failure prevention, and it's a slow, fast hierarchical method. It's able to process human describable fallback strategies into goal coordinates and anticipate and avoid conceptual failures. And we do all this preparation in advance, so then at the safety critical moment, we have an optimization problem that we can rapidly solve, and we generate a safe fallback plan, and this optimization is agnostic to any control planning algorithm you can plug in place. So feel free to visit us at our poster, poster number 72, that's 6 times 12, so remember that, and that's in the afternoon session. You can contact me at this email, and check out this QR code for our website paper and code.
Okay.
Thank you.
We are over time. We need time for at least a couple of questions. We have 1 minute. So if anyone has a question, there are several microphones in the room. In the meantime, I have a question. So you rely a lot on the safe set that you collect. How do you collect it, and what happens if you encounter instances that were not inside your safe set and it's been classified as a failure, for example? How would this affect the overall planning process?
So our approach performs best when you collect a lot of diverse, safe examples. So as long as you can get as close as possible to what's considered unsafe, that's really great. But there's always going to be scenarios that are quote unquote like alien scenarios that you won't be able to actually understand and ever detect. So so the TLDR is that you should have a lot of diverse, safe data to improve the quality of these semantic safety.
Who will collect the safe data?
Sorry?
How would we collect?
So a lot of these
safe
autonomous
data?
systems have already been deployed in the past. So like for instance, when self-driving cars are driving around cities and collecting all these sort of data, there's not a lot of failure data, there's not a lot of crashes, but there's a lot of mundane safe things. And so we're able to leverage those and convert them into logs.
Okay, thank you very much. Yeah. Let's move to thank the speaker. Let's thank you. And move to the next. The next oral is Fabrica Dual Arm Assembly of General Multi-Part Objects via Integrated Planning and Learning.
All right. Hi, everyone. I'm Yun Sheng. I'm presenting Fabrica today. So the motivation of this project is that our whole world is built on assemblies, like most of objects around us. And the industry today has two ways of producing them. So either it's assembly line robots or it's human labor. On one hand, the robots are highly efficient at producing one type of product, but it cannot adapt to variations. On the other hand, human is flexible, but labor shortage is a serious global issue. And for robots, setup is painful because you need months and huge budget for infra, and you need engineers to do all the pre-programming. For human, the runtime is painful because people easily get fatigue, mental health, and safety issues. So how do we build human-like robots for efficient and flexible assembly? Assembly is easiest one of the hardest problems in robotics due to the numerous challenges, including like long horizon, bimanual operations, rich contact, stability, and precision requirements, and generalization to diverse part geometries, and most importantly, lack of data. So for existing works, domain-specific systems require priors and hard-coded sequences. RL is great at insertion, but mostly for two parts and top-down grasps. Imitation learning can work with multiple parts, but require a lot of human data and is hard to generalize. Finally, planning methods are general, but cannot handle real-world errors without closed-loop control. So, how to develop a flexible system for general multi-part assemblies in the real world? So we combine the strengths of planning and learning to enable assembly with strong generalization. Starting from minimal inputs like part meshes and hardware configs, our planner gives global sequences and motions, and then we learn policies that perform local context-rich skills. Finally, they are combined to deliver long horizon assembly on real robots. So the first question for planning is, what are the feasible part sequences? We use our prior work for precise motion planning of every parts, and given this beam assembly as an example, we essentially just peel off parts tier by tier with this method, then build a precedence graph by checking blocking relationship between the tiers, which give us all feasible assembly sequences. To find a feasible grasp to execute them, we start by sampling grasps for each part using any grasp planner, and then checking feasibility for assembling and holding without collision. And finally, we filter jointly feasible grasp pairs, which can be efficiently parallelized. However, getting a kinematic feasible solution is not good enough. We need to optimize the part and grasp sequence for stability to achieve max success in the real world. So we formulate this as a graph search problem where each grasp is represented as a node. including the part is grasping, and edges connect jointly feasible pairs of grasp. The graph extends in temporal domain, and we find the optimal path that leads to the highest objective using dynamic programming. But pickup and assembly may require different grasp. So shall we use an extra arm for regrasp, or we do in-hand reorientation? Right? They all sound non-trivial for a dual-arm robot with parallel grippers. So instead, we procedurally generate pickup fixtures to avoid regrasping by placing parts at the beginning in a way that the top-down grasp for pickup is the same as a planned grasp for assembly. So the top row is the benchmark assemblies that we designed, and the bottom row is fixtures generated by our packing algorithm. This also helps separating the picking problems from the assembly problems that we want to focus on. Finally, we combine some standard motion planners like RT for transit motions in between, and our system generates optimal plans for arbitrary dual-arm robots on diverse assemblies. You see the two arms coordinate really nicely in each step to ensure stable assembly over long horizon. Thanks to the global plan that handles all the free space motions, we can just learn a local generalist policy to insert anything with any grasp. This is done through large-scale RL over diverse geometries and diverse grasp with domain randomization. So we can come up with a minimal RL formulation based on the object-centric representations, where the observation is the pose of the part to assemble, action is a desired part movement, and reward is just simply a negative L2 without any engineering. This formulation enables scalable learning, easier sim-to-real, and cross-embodiment compatibility. To further improve generalization and convergence, we leverage spatial equivariance that transform all assembly directions to top-down insertion for observations and actions and also impedance gains. Additionally, we only learn residual actions on top of the planned actions, which is easier and only requires a small MLP as a policy network. As a result, we show complete multiple-step real-world assembly on diverse objects. We can use just one network that works on all assemblies with an average of 80% successful steps over long horizons. The policy works across varying grasp and assembly directions with an embodiment agnostic design. So to see more detailed results, we find both specialist and generalist policy can achieve a decent performance. So either training directly on the test assembly or on all other assemblies except for this one, so which is actually out of distribution. Our ablation studies show that degraded performance without part sequence optimization or grasp optimization or both optimization during planning, and also or without equivariant transformation in policy learning. Finally, the open loop baseline performs the worst. In addition, we also evaluate cumulative success rate over the entire multiple steps, so a single step failure is critical. We evaluate with 0, 1, or 2 interventions along the entire sequence. And this shows that it's still very, very challenging to achieve end-to-end success due to the nature of multi-step chaining. But our method success can be boosted just with some little help from human. I'd like to discuss the typical failure modes. So first, grasp slippage can happen, which just breaks our assumption during planning and learning. Second, there's usually cumulative drift over multiple steps of assembly. Our plan does not really track it. Third, there's some sim-to-real modeling gap is possible. And finally, the assembly can be unstable when partially assembled. So like the green bolt can just move out of place when assembling other parts. To address them, I'd like to talk about 4 directions for future work. So first, we can do some naive error recovery by memorizing human guidance. For example, the policy here fails because initially there's a large misalignment. Then I push the arm to a better initial pose, and after that, the policy will work fine for all the following runs. So it's actually pretty simple, but effective, but still it doesn't really guarantee success all the time. So a better way is to actively learn from human guidance instead of simply just memorizing it. And another way is to leverage vision feedback from VLMs for better initial alignment. So by watching this failed attempt, VLM can suggest directions to adjust the end effector for successful insertions. And also, we find it's necessary to use active perception, since camera views can be easily blocked by parts or arms. And sometimes the camera needs to find a precise angle to look into the connection between parts. There are some great works happening in this CORL that explore this direction. Alternatively, human can do flexible reorientation of assembly to align that with our sight. But it's really, really challenging to consider stability, visibility, and regrasp with a robotic setup. Of course, a better hardware always makes your life easier. We simply just printed a standard panda panda finger, and instead we broke many of them. It's always recommended to use fingers that have better stability or dexterity or sleep detection through some tactile feedback. So finally, data-driven learning is extremely effective in handling failures and learning adaptation. But I will argue that we are never going to collect enough real-world data, considering all different assembly tasks and all different scales of objects and all different failure modes. If you disagree, let's debate at the poster session. Thank you.
Questions? Yes, please.
Thanks for the presentation. I'm just curious if you are trying to assemble something that can be assembled in different ways. I mean, a little bit large scale, but say an IKEA drawer set. As a human, if you don't really follow the instruction, you probably go 90% the wrong way until you get to the end and realize you didn't really do it right. Which is because it could be assembled in different ways until some point, probably. How does the method deal with that? But even at a small scale, you can also like come up with things that can end up in different shapes if they were to get assembled in different ways.
Yeah, that's a good question. The question is about like, what if during your assembly process you get blocked and this is actually a not good sequence for continuing the assembly? So our method doesn't have this problem because we actually plan from disassembly. So we first plan the disassembly process and then we reverse the whole process to obtain the assembly sequence. So this is, I didn't mention in the talk, but this is the like so-called very popular assembly by disassembly principle. The only restriction is that it only works with rigid objects, so we don't do any deformable object at the moment.
Okay, thank you. Then we can proceed. The rest of the discussion can happen on the poster. So let's thank again the speaker and welcome the next speaker on geometric red teaming for robotic manipulation.
Hello everyone, I'm Devim Goyal from Carnegie Mellon University. Today I will be presenting our paper GRT, Geometric Red Teaming for Robotic Manipulation. The ultimate goal for robotics is to enable reliable behavior in messy real-world settings. But we still lack tools to audit performance beyond the test set. Static benchmarks fall short in uncovering real-world failures. We instead need proactive methods that discover and address fragilities before deployment. Given a robot policy, one way to achieve this is red teaming, which is a proactive search for credible failures. A red teaming agent carefully observes policy rollouts and then proposes plausible tests that could break it. These insights can then be used to improve the policy. This idea is gaining traction. Recent works use red teaming to probe sensitivity to language instructions, and other methods test perception robustness by predicting counterfactual scenarios. Another axis for red teaming is object geometry, what the robot perceives and interacts with. This is where GRT comes in. Consider the case of using contact GraphNet to pick up this bottle from the YCB dataset. Our red teaming agent observes many such rollouts in simulation and discovers small deformations of the object shape that cause contact GraphNet to completely fail at this task. So how does this work? We begin with a fixed policy and a nominal object on which it succeeds. Given task constraints, we query a vision language model that proposes where to edit the object. We then use a deformation model to modify the geometry of the object and run many simulation rollouts to search for deformations that break the policy. In the end, we find crash shapes that degrade the policy. Let's now unpack each component. First, how can we deform the object while still keeping it task relevant? We define anchor points, which govern parts of the mesh that stay fixed. We also define handle points, which mark mesh locations that we may move to steer the deformation. Their displacements determine the extent of the deformations. We then define a Jacobian field over the mesh and use a Poisson solver to generate the final deformations. The model delivers a constraint-compliant deformed mesh in the end. Manually annotating the meshes can be limiting at scale, which brings us to the next step, VLM guidance. We first sample canonical views annotated with key points selected via a heuristic sampler. A geometric reasoning prompt selects key point subsets on these candidate handles and then selects these regions which are then suitable for realistic deformations. The VLM then reasons about the task relevance of all these candidates and chooses the final handle points for the deformation. By using a VLM to select the handle points automatically, such a method can be easily scaled to arbitrary objects. With VLM guidance and the Jacobian field-based deformation model in place, we are ready for a simulator-in-the-loop optimization to probe the policy's geometric sensitivity. Given the nominal mesh and VLM-guided handles, we optimize handle displacements to create crash shapes that minimize policy performance. Towards this end, we sample an initial set of random displacement vectors. These vectors, along with their handle points, are passed into the deformation model, which outputs candidate geometries with plausible deformations. We simulate the policy on each deformed object and measure how well the policy performs. Subsequently, the top K failure-inducing shapes are selected, and then we mutate a subset of their displacement vectors to seed the next iteration. This optimization loop gradually hones in on policy-sensitive geometry, as visualized here in the GIF, and uncovers failure cases. Across grasping, insertion, and articulated drawer manipulation, task-consistent edits flip outcomes of the pre-trained policies from reliable success to consistent failure. The blue bars in this plot are the nominal runs normalized to 100, while red bars are the same policies on our crash shapes. With only geometry edited under task constraints, success drops by over 70 points across all tasks. The policy and control mechanisms remained exactly the same, so this is a clean measure of geometric sensitivity. We further test the efficacy of GRT while restricting the deformation space by capping handle motion and enforcing a smoothness score constraint. Even under this constraint, GRT is able to discover meaningful failure modes, and the edits stay small with low distortion. To assess each design choice, we ran an ablation. This figure charts failure severity, search efficiency, and plausibility for each variant. First, without optimization, the VLM alone gives more plausible edits, but lower severity and efficiency. Without the VLM, the optimization finds stronger failures, yet the plausibility of the objects drops. Finally, our full method gives the best overall trade-off with the highest search efficiency, the strongest failures, and the competitive plausibility. Let's now look at our real-world experimental setup. For grasping, we use a tabletop Franca arm with an Azure Connect camera and contact GraspNet as our grasping policy. For insertion, we use an XARM6 with an assembly platform fixture. We use the industrial framework to train RL policies for this task. As shown here, contact GraspNet succeeds on the nominal objects, but then fails on the discovered crash shapes. Across 20 trials per object, performance drops sharply on these confounding geometries. Here, the insertion policy inserts the nominal plug with tight tolerances, while crash shapes cause misalignments, leading to catastrophic failure. Across 40 trials, policy performance on crash shapes is substantially lowered. We now ask a simple question: can crash shapes be used to improve the policy? Our proposal is a single step: fine-tune the policy on the discovered crash shapes. We call this step blue teaming. We blue team the insertion policy by fine-tuning on crash shapes with PPO. The fine-tuned policy is now fixed and shows no degradation on the nominal shape. This holds across 40 real-world trials, validating GRT's ability to generate actionable signals. To recap, GRT searches for task-constrained shape edits that break a policy. VLM-guided parametrization and Jacobian field deformations ensure plausible task-relevant changes. A gradient-free simulator-in-the-loop search then uncovers hidden geometric failure modes. We also show GRT enables targeted policy improvement. The QR code on the top corner can take you to our website, and I'm happy to take any questions now.
Thank you. Questions? Okay, if there is no question, like how expensive is this optimization, and why do you keep this notion, as I suppose they are like some notion of affordance of these points that you select? Why couldn't I just randomly, uniformly sample and basically do something in sorts of sim to real? Why do I really need to query a VLM for that?
Yeah, so for your first question as to how expensive this process is, So we've scaled this across multiple GPU nodes on the cluster. So I think each geometric red teaming run runs for about 10 iterations with 10 samples each, and this is what the results look like. And this process takes about an hour and a half in total.
Okay.
As to your second question, why do we need to query with the VLMs? So we have baselines without the VLM, which are essentially just random points being picked out at different parts of the object. And I guess there are some results in terms of like reducing the performance, but in terms of more critical objects where the grasping policy actually did a really good job at grasping it, just randomly selecting points is no longer enough to really challenge the learned priors of the grasping policy. Okay. So the VLM really helps us pinpoint those affordances, which challenge even like shapes which the policy might eventually perform really well on.
Okay. Yeah. Thank you. Makes sense. Thank you to the speaker, and then we move on. We can clap. Then we have Stack It Up, 3D stable structure generation from 2D hand-drawn sketch.
Okay, hi. My name is Yi Qing. I'm from National University of Singapore. Today I'll present this work, Stack It Up, 3D stable structure generation from 2D hand-drawn sketch. So let's imagine a kid draws this sketch of an Eiffel Tower and asks a robot to bring this to real life. But the robot doesn't understand this kind of a hand-drawn sketch. Instead, what it requires is a preset code specification, the exact poses for the blocks, and hidden support for stability. This is where Stack It Up comes in. It transforms a rough 2D sketch into a 3D stable arrangement of building blocks, make it understandable and executable by a robot. And with Stack It Up, hidden support and exact object poses are automatically predicted, enabling a robot to understand and build exactly what the user has imagined. But turning a 2D sketch into a 3D stable structure isn't straightforward. So what are the challenges? So firstly, a 2D sketch is inaccurate. A hand-drawn sketch are rough and not drawn to scale, so the proportions do not match the reality. If we place the object exactly as drawn, the structure can be unstable or not even physically feasible. And secondly, a 2D sketch is incomplete. The sketch only shows the front view, so it means that we don't see the internal support or the hidden object, which is essential for stability. So our insight is that instead of directly predicting the 3D poses, let's predict these abstract relation graphs as an intermediate step. The node of these abstract graphs are the object, and edges are the symbolic relations among the object. So why do we use this graph? On one side, it distills the geometric cues from the sketch and abstract away the inaccurate details, which help us to resolve the inaccuracy. And on the other side, it is compact. It is a compact abstraction. So it's very effective for us to reason and sample about the missing and hidden object, which help us to handle the incompleteness. And another reason why we use this graph is because instead of directly predicting the 3D object poses, which require a huge generative model, we have to generate a lot of data to cover all structures. Using this graph, we can break down the problem into smaller pieces. So instead of training a huge model, we can now train smaller diffusion models for each individual relation type individually. And because each this geometric relations has a clear geometric meaning, we can generate synthetic data and train these models independently. And then we will have a new graph corresponding a new sketch. We can compose these pre-trained diffusion models on the fly. This allowed us to ground any sketch into the 3D structure and generalize the wide range of structures. Okay, now we have this graph and this small compositional diffusion models. We can effectively generate structures that resemble the sketch. But there's still one big question. How about stability? So there are actually two parts to this question. One in the discrete space, when do we add the hidden object? And another in the continuous space, how do we ensure the 3D object poses predicted are stable? So can we try using a single diffusion model? Well, stability alone has many solutions, including many useless ones, like flat scattered on the table, which is not going to be very useful for complex structure prediction. And generating lots of training data to cover all stable structures this is impractical. So if we train a single diffusion model for stability only based on a small set of data, it tends to collapse to common stability patterns and fail to compose when we combine that with other geometric relations. And more importantly, this generative model in the continuous space isn't going to help us with the hidden object prediction. So what we need is really a representation that is flexible to represent any stable structure, easy to train with synthetic data, composable with the other geometric relations, and able to guide the hidden object prediction. And then we turn to architecture 101. Every skyscraper is built from a few basic local stability patterns. So let's model these patterns directly. What is good about these patterns is that they are naturally linked to the relation graph. Each stability pattern corresponds to a simple subgraph or set of subgraphs that we can define clear rules with. And by combining these local stability patterns, we can construct tall and complex and global stable structures. And finally, these patterns aren't fixed. They can evolve by adding new objects or tweaking the existing relations. We can define these evolution rules manually, and these rules guide the prediction of the hidden object, ensuring stability while preserving the resemblance to the sketch. Now let's see how Stack It Up work all together. A user starts by drawing this simple rough front view sketch of their desired structure. Stack It Up then identify all the visible blocks. Using the relative poses of these blocks, Stack It Up construct the abstract relation graph. This graph captures the qualitative geometric relations, such as left off and horizontally aligned, and also the stability patterns like two-pillar bridge, abstracting with the exact metrics while maintaining the structure integrity. Then Stack It Up grounds these abstract graphs by composing multiple diffusion models, jointly predicting the precise 3D poses for each blocks, and these predictions are tested for stability in a simulator. If the structure isn't stable, Stack It Up then updates the graph by predicting the additional hidden support guided by the library of stability patterns and integrate them into the existing graph. This updated graph is then regrounded into the precise object poses again and retested. This iterative loop continues until the structure is fully stable. In summary, Stack It Up takes a simple user sketch and iteratively refine them into a stable, detailed 3D structure. The result is a ready-to-build arrangement that the robot can understand and execute. Stack It Up consistently generates stable and visually accurate 2D structures that closely resemble the original sketch compared to the baseline approaches, and we can create stable arrangement for a variety of sketches, ranging from iconic landmarks to modern house designs. And even if sometimes we give the same sketch, Stack It Up can also adapt the arrangement to the shapes, to the blocks you give it. So in the upper example, the blocks are thin, so the system automatically add additional pillar behind the visible pillar to support the roof. And on the lower example, we use sprinkle cans, which has a wide support, a wide base, so the hidden support isn't needed. This means that with the same sketch, Stack It Up can automatically generate a different but stable structure adapted to the shapes and size of the available blocks. So with Stack It Up, anyone can easily communicate the ideas of a 3D structure to robot via a simple 2D sketch, effortlessly turning creative ideas to a real-world construction. Thank you. Ready to take questions?
Questions? So I have a question. So here you don't take into account the execution of the robot, right? Like failures that may come from the robot or the whole, let's say, 3D space where the robot is operated together, like with the cans and like the volumetric space that they...
Right, yes. Currently, this project focuses on the goal specification, and we rely on off-the-shelf motion planner to do it. But then, given the support graph, we can do a BFS on the sequencing of assembly, just as the previous the presenters has mentioned assembly by disassembly. I think in this we use the same principle to reverse the ways we stack it up to disassemble way to stack it up.
Okay, and one clarification: the initial abstraction that you extract, the semantic relations, how are they being labeled these days?
Oh, we designed a rule-based system based on the relative process of the visible blocks. Thank you.
Thank you. Thank you very much. Thank you to the speaker, and then the next speaker can prepare. The next speaker will talk about planning from point clouds over continuous actions for multi-object rearrangement. When you are ready, we can start.
Hi, I'm Amber. I'm from Carnegie Mellon, and I'm presenting our work on planning from point clouds. This work was co-led with my co-authors, Kalol and Angela, and also made possible by these co-authors. So we're at a robot learning conference. I'm sure we're very familiar with policy learning. And policy learning approaches have advanced greatly on robot manipulation tasks. But what about long horizon robot manipulation tasks? For example, a robot trying to organize this really messy room with some shelves. This challenging task requires the robot to reason about a 3D physical scene and also about the effects of a sequence of actions that it may take. Planning becomes essential in orchestrating such long horizon operations. Symbolic planning is a classical family of methods for solving long horizon manipulation tasks. However, these approaches require a symbolic scene description, which may be challenging to acquire for real-world scenes. Another approach is planning in the space of natural language, but large language models may have trouble grounding language in the 3D physical world. So we propose to do visual planning, or planning directly from partially observed point clouds. Our method reasons over a sequence of continuous valued actions without needing to discretize the action or state space. But searching over high-dimensional and long horizon state action transitions is difficult, so how do we deal with this challenge? Our key idea is to learn to propose object transformations. Then we're able to search over different point cloud object rearrangements, and our method is called SPOT. So this becomes our formulation for solving multi-object rearrangement problems, such as this table busing task, where the goal is to organize all the dishes into one neat stack. By leveraging our key insight, we're able to learn to propose task-relevant object transformations, and then generate a tree of point cloud rearrangements on which we can then use A* search to plan to a goal-satisfying configuration. Now for an overview of our method. We operate directly from an RGBD image of the scene and semantic object labels. This gives us a segmented point cloud. We also specify a goal function over the segmented point cloud. For example, for the table busing task, we might check whether the centers of the point clouds are all within a certain distance threshold from each other. These are the inputs to A* search. In the search, at each node expansion, we generate child nodes by first deciding an object to move, and second, deciding where to move it. To guide our A* search, we have 3 learned modules: the object suggester, placement suggester, and a model deviation estimator. Upon finding a goal, the search will output a plan, which is a sequence of objects and their transformations. The robot can then directly execute this using motion planning. Now I'll get more into the details about our learned models. First is the object suggester. Our point cloud demonstration dataset is not task-specific, so the model learns which objects in the current scene can feasibly be moved. We get a probability distribution over each of the objects in the scene, which we can use to guide search. Now that we've picked an object to move, we now need to decide where to place it. This is where the placement suggester comes in. We implement this using a conditional VAE, which maps an input point cloud into a latent distribution, from which we sample points that get decoded into transformations. We iteratively rescore the latent distribution around the previously sampled point in order to generate diverse transformations. So the placement suggester learns a distribution of possible transformations of the object throughout the task. Sometimes the actual dynamics of the environment may not match the suggested action and what our models think. For example, our models might predict this transformation where we take out the middle block from the stack and put it on the table, but of course in reality what happens is the stack will actually topple over. So we learned the model deviation estimator, or MDE, which predicts how much the expectation differs from reality. The inputs are the point cloud observation as well as the proposed action, and then it outputs a real number, which is the predicted deviation. We also use this to guide search towards actions that are more likely to be executed successfully by the robot. Now that we have the 3 learned modules, these get incorporated into the A* value function, which is made up of a cost function and a heuristic function. The cost function has these different terms in it that are largely derived from the outputs of the learned models that I just talked about. And then the heuristic function is task-specific and specified over the segmented point cloud. For example, our heuristic for table busing involves summing the distances from the point cloud centroids to the center of the plate, serving as an approximate measure of distance to the goal. We evaluate our method on tasks in both simulation and the real world. So we have block stacking and table busing, which involves unstacking and restacking objects into a desired configuration. In constrained packing, the robot needs to put items into a confined space without stacking them on top of each other. And then we define task complexity by the length of the ground truth optimal plan. We also compare our method with some ablations and baselines. In random rollouts, at each step we choose a child node uniformly at random from a set of candidates and continue search until we exceed a node expansion budget. We also test an ablation that removes the guidance from the object suggester, and Spot outperforms both of these, showing the importance of guided search. We also run a beam search baseline, where at each step the policy chooses the child node with the best heuristic value from all the candidates that Spot would generate. So this ablates the search component while keeping guidance from the heuristic. We compare with 3D diffusion policy, or DP3, and end-to-end imitation learning policy. Here are some example runs where the goal is to stack the red block on the green block on the blue block. And we see that DP3 is unable to complete tasks requiring more than 2 steps, while Spot is able to. Finally, we compare to prior works that, like us, also plan from partially observed point clouds, but in contrast, they require defining a set of relational abstractions in order to get a symbolic description of the scene. So we do not require this, but achieve a similarly high success rate. Here are some qualitative results of our method. To conclude, we propose an approach that combines learning and search-based planning while operating directly from raw 3D point clouds. Our learned suggesters enable search by proposing object transformations. So you'll find us at poster 62 if you have more questions, and I'm happy to take any questions now.
Okay, thank you. Any questions? Yes, up there.
Hello, extraordinary work. In my experience in extremely crowded environments, you often have erroneous point clouds due to, say, failed segmentations or erroneous object to point cloud associations. So I'm curious about how your method handles such cluttered environments. Do you see any failures associated with wrong point cloud generations?
You're asking about wrong segmentations of the objects in the scene?
So wrong objects, as in you have incomplete point clouds or point clouds are mapped to the wrong object?
Right. So occlusion is a big problem, right? So in some of our table busing initial states, maybe there's already like a bowl on top of the plate, which means that the plate is very incomplete. It's more like a sliver rather than a plate. So our method is able to, I guess, like learn from our demonstrations and adapt to these sorts of challenges.
I see. That's wonderful. Thank you.
We go now here.
Great presentation and great animations in the slides, but I'm curious about how your method compares to end-to-end learning methods, say PIO5 or Gemini Robotics 1.5, for example, where it can do the planning out of like just emergent capabilities that it got from similar demonstrations, but also from like pre-trained models?
Yeah, that's a really good question. I think we did a bit of testing on OpenVLA, but without any fine-tuning. That basically wasn't able to achieve any success, but probably with some fine-tuning, it would do better, although I believe that for these types of like longer horizon task, planning is essential.
Great, thank you.
Thank you.
We have time for one more question, so yeah.
Hi. I wonder, how do you find the grasp model for each object? Or how do you find the grasp pose of your end effector?
Yeah, in the real world, we use contact grasp net, and in simulation, we had some grasping heuristics.
Okay, thanks to the speaker. And finally, we have belief conditioned one-step diffusion, real-time trajectory planning with just enough sensing.
Hi everyone, good afternoon. I'm Gokul. I'm a PhD student at the University of Illinois at Urbana-Champaign, and today I'll be presenting our work on belief-conditioned one-step diffusion. So some motivation, if you think of a robot, in this case a marine robot, it is incomplete without any of these sensors, right? And there are a lot of these heterogeneous sensors, and each of them give information about different modalities. And the main goal of these sensors in a navigation setting is to figure out a way to use it for localization. And if you think about it, generally the whole point of this navigation setting, once again, is that there's some annoyed human who gives the robot some task, and you have an environment with some obstacles, uncertainty, and so on, and somehow the robot needs to figure out a way to generate a trajectory to the goal and follow the trajectory in real time using all the sensors. So when it's using all the sensors, it uses sensor fusion, active perception, etc. So taking a closer look at the path that the robot just followed, at this particular point, the robot is near obstacles, and it needs to be fairly certain about its positional uncertainty, because if its localization error were high, there's a very good chance that it might crash into obstacles and fail the task. On the other hand, somewhere here, when the robot is in open waters, it can afford to be less certain about its position, because it is in the open water and there is much less chance of collision happening. So our observation here is that sensors value is highly task specific and local environment specific. That is, we argue that you can solve the same task that was given in the previous slide by not using all the sensors at all times. So we ask a very precise question. Given a goal, can a robot generate a short next horizon motion towards the goal, and in real time decide the smallest set of sensors that must stay on so that its localization uncertainty is reduced just enough to reach the goal, something that we call real-time trajectory planning with just enough sensing. So while people have tried solving each half separately, planning is usually cached as POM-DPs and solved using different approaches. But their catch is that all of them assume that these sensors, all these sensors are turned on while training, have expensive covariance rollouts, and are super slow. And on the other hand, the just enough sensing is usually cast as a sensor scheduling problem, and people solve it using optimization approaches. Once again, the catch is they're heuristic, expensive because of tree growth, and of course very slow. Well, I heard someone in the audience say, just use RL. I hear you guys, as someone whose bread and butter is RL, I hate to admit that it has its own problems in this particular setting. It has a lot of heuristics, it is data hungry, there's a lot of reward shaping that you'll need to do, and a lot of hand engineered shields. Right? At the end of the day, you might be able to solve it with RL, but I would argue that it would most likely not scale, might not be an elegant solution, will have issues with data, and will not generalize well. And I'll quote Professor Pedro Domingos here. And the claim that we're making is sometimes all you need is context. And sometimes this context comes from some of the strangest places. I studied a little economics at some point, and I held on to some facts from that course. Apparently, if you track lipstick sales, you can tell a lot about if a country is going into recession. Similarly, if you count the number of pizzas that is being delivered to Pentagon, it gives you a good estimate about the military activity. These are actual facts. I'm not making it up. You can look it up. These are what people call alternative data. That is creative ways of creating statistically significant proxies. Basically, if you cannot measure the target, find a way to measure its shadow, and it will eventually lead you to the target. So the TLDR of our paper is that belief condition diffusion can produce short horizon paths towards the goal and serve as a sensing oracle, or in this case, provide the alternative information required for sensing. The obvious question is, why even use diffusion? So if you think about it, diffusion planners produce a full distribution of trajectories that are usually just gone to waste and end up choosing one of it, and the rest of them is usually discarded, right? But the good thing is, because it's a distribution, if the robot were choosing the wrong set of sensors, intuitively the distribution should widen. And similarly, if it were using the right set of sensors, the distribution would contract, right? So what we are hinting at is, maybe diffusion might already be encoding how much sensing is too much sensing. So our paper drives this intuition to practice using belief conditioned one-step diffusion. So let's assume we have the same robot with all these different sensors, and generally neural planners need a fixed tensor for belief maps. We feed the planner where the robot likely is, which way it points, and how concentrated the belief is without the runtime blowing up. At every time step, we create a representation of belief of the robot, and it is in these, encoded in these 5 chosen channels. Our paper ablates a few more channels and show that these 5 are actually enough. And the way we get to this belief representation is not set in stone, but any approach that creates these belief maps in real time works. And from there, we train a DDPM on belief rasters, semantic goals, and sensor maps, and distill it into a single-step student. And the good thing is, in one pass, it outputs a local trajectory and also a calibrated waypoints for the log variances. And we show in our paper that the CVAR value of this particular calibrated log variance acts as a validated tail risk proxy for sensing that is, in some sense, an alternative information. And finally, we show that this one single proxy is enough to drive an online RL algorithm, and we instantiate this using SAC and show that in real time, under 10 milliseconds, we can repurpose diffusion to simultaneously produce short horizon paths towards the goal and also serve as a sensing oracle for a small sensor selection policy. So here are some quick results. The setting is very simple. You have a robot operating in a challenging marine environment with a lot of different sensors, and the goal is to navigate with just enough sensing without crashing. Here's a quick example of a daytime lab. I'll keep quiet for like a few seconds. You guys can read through what's happening. On the top right, you see which sensors are being selected. On the right, you see our intuition on why this is happening. And the robot completes the task without ever crashing into any of these fountains or obstacles, and is also able to do so with just enough sensing. So here's a quick analysis. If you look at t equal to 68 in the GPS denied zone, you see how our approach BCOD immediately turns off GPS the second it enters a GPS denied zone. Similarly, because it's context aware, when it is near all these obstacles or perimeters, it just turns on all high power sensors, not caring too much about frugal sensing and making sure the robot is safe. And you'll see a similar path in high quality sensor modality area as well. And our key results are that BCOD plus SAC delivers close to perfect task completion at less than half the sensing cost of an always-on baseline. And we also show that this variance is a very calibrated context-aware predictor of the localization error. And you can scale the lake or the environment to how much or large you want, and we show that we're still able to plan in under 10 milliseconds, or 10 plus minus 1 milliseconds, and outscales any of these analytic belief planners. And finally, we failed a sensor mid-run and show that BCOD is able to adapt online, reallocating modalities to recover from faults. We have open sourced all our data. This is the first of its kind, fully belief annotated navigation snippets with all synchronized multimodal sensor logs. And beyond marine navigation, we also show in a 3D setting how we are able to navigate this drone. Everything is running on board, real time, real world, under 10 millisecond. So the keywords across the paper were just enough sensing, task-specific uncertainty, diffusion models as an alternative data, and the TLDR of our approach is that diffusion already does encode clues about how much sensing is enough, and we show with B-code how to instantiate this. We've also have a live demo. Feel free to go on to the website and play around with the model, break the model, and please come talk to us at Poster 87 in case you come up with some cool stuff on the demo. Thank you.
Thank you. We have time for one question. Yes.
Thank you for the great talk. I have a question about the motivation and the use case of this project. So why do we, in the first place, want to not use all of the sensory data? What are the burdens of coming from using all the sensory data?
Yes, this is a great question. So first thing is, one good motivation could be a stealth-based environment. Let's say you're operating in a stealth-specific environment where every time you pull from the GPS, your stealth reduces, or every time you use some other sensor, your stealth reduces. So you'd like to complete the task by being as frugal about sensing as possible. And secondly, as I showed in my results, sensors actually consume power. If we are able to save this power, maybe this can be used towards computing other stuff that are more relevant towards task completion.
Yeah, thank you.
All right, thank you to the speaker, and yeah, we can go now for a break. Thank you very much.
This is MS TV drawing.
Hello everyone. We have 10 minutes before spotlight session, and then if there are any speaker for spotlight session, then please move to the front left over there. We are now looking for many speakers because now it is missing. So let's prepare. Yeah, as you know, we have 5 minutes left. So the speakers, if you are here, then please go to the front left, and especially the presentation number 16 and 26. Please go there as soon as possible because you have something problem in your video. Wow, I stopped the music. I don't intend to do that. Hello everyone. It's time to start spotlight session. I think that some of us is absent, so sometimes you will see some emergent case, but please enjoy that. So let's welcome the first speaker. Let's enjoy it together.
This is our work on improving motion planning efficiency with message passing Monte Carlo. So the choice of sampling distribution ends up being critical for planners, especially in high dimensions. So we aim to generate well-spread point sets that improve motion planning efficiency. To do so, we propose MPMC, which is a neural point set generator that is based on graph neural networks and that minimizes a geometric loss known as discrepancy. And a closed-loop formula for that loss allows us to train in high dimensions. For example, in dimension 10, we achieve an order of magnitude better discrepancy than uniform sampling. We can also show that lower discrepancy leads to a tighter gap on closeness to path optimality for probabilistic roadmaps. And then we can benchmark against a series of different sampling distributions on experiments up to dimension 10, and show that we consistently outperform these other sampling techniques. So please come see us at Poster 19 and we can talk more about this. Thank you.
Hi everyone, I'm Satish and I'm excited to present our collage. We want to train specialist policies without having to collect lots of new data. Data retrieval methods enable this by starting with a small-scale target data set and then retrieving from large-scale data sets data similar to it. Then the training is performed by mixing the target demonstrations with the retrieved data. However, current data retrieval approaches rely on a single feature modality for retrieval, such as visual, 3D, or motion similarity. Relying on a single modality can be limiting, as different tasks benefit from different types of cues. In collage, instead of committing to one feature modality, we retrieve data using several different feature modalities and predict and estimate the weight of each retrieved subset based on its relevance to the target task. In our real-world experiments, we retrieve data from the large-scale droid data set. I know there's a lot in the slide that I didn't get to cover. Come find me at poster 41 and I'll explain everything in detail. Thanks.
Hi everyone, I'm glad to introduce our work about robotic chemical experimentation, RoboChemist. We propose a dual loop framework that integrates VLMs and VLAs. The VLM acts as the planner, decomposing high-level tasks into subtasks, then generates prompted images through visual prompting to the VLAs. VLM also functions as the planner, assessing the completion status of the subtasks. Results show RoboChemist outperforms baselines in both primitive tasks and complete tasks. This is an illustration of the acid-based neutralization reaction experiment. It automatically decomposes actions and monitors the whole process until the solution is clear, meeting the request. We selected 7 general primitive tasks for retraining, and RoboChemist can do complete tasks leveraging VLM and the VLA's ability. RoboChemist shows adaptability, successfully performing both primitive and complete tasks. Thanks.
Hello everyone, we would like to introduce our work, Uncertainty-Aware Accurate Elevation Modeling for Off-Road Navigation via Neural Processes. Off-road navigation tasks involve traversing unstructured and complex environments such as hills, valleys, or cliffs. However, as shown in the images, negative obstacles are often invisible in sensor readings. This invisible nature makes the problem very challenging, as underestimating them can lead to a vehicle rollover. Thus, accurately estimating them and identifying uncertainty are essential. For tackling this task, neural network-based approaches have been proposed, but they often underestimate the terrain or demonstrate degraded accuracy when trained to predict uncertainty. Addressing such concerns, we introduce semantic conditioned neural processes that leverage the strong learning capabilities of neural nets and predict uncertainty from Bayesian estimation. Our method demonstrates stronger performance on off-road environments, captured from various testing sites.
Hello everyone, I'm Kaizhe Hu. So can your robot swim by itself? I'm glad to introduce you Robot Trains Robot, a holistic system for real-world humanoid learning. With RTR, our robot can learn to fine-tune a sim-to-real working policy and double its speed, or learn from scratch a challenging swing-up policy within 20 minutes. So for humanoid robots, it is way too dangerous to let it learn in the wild. And domain randomization cannot fully close the systematic sim-to-real gap. Inspired by human parents when they guide their children by hand, we propose to use a robot arm with force torque sensing to guide the robot and an adaptive treadmill to keep it in range. Our robot arm can move horizontally to give it a sufficient exploration and adjust vertically to give it a learning curriculum. It can also reset the humanoid when it falls. We also propose an efficient latent fine-tuning algorithm to boost the sample efficiency. Please come to poster 2 for more information. Thank you.
Hello everyone, I'm Luca Gallotti and I'm happy to introduce our work on robots that autonomously discover their abilities. So we present URSA, an algorithm to discover diverse and high-performing skills directly without simulation. Here's how it works. Over 5 hours, the robot collects data and trains directly in the real world, continuously switching between different skills as it discovers them. As you can see, the robot starts with random movements, but quickly learns diverse locomotion behaviors to move forward. These repertoires can be used for rapid adaptation to damages with no additional training. In addition, URSA can learn from handcrafted skill definitions like forward and angular velocities. In that case, the result is an interpretable skill repertoire that can be used to control the robot velocity. Thank you for your attention, and feel free to visit us at our poster number 75.
Hi, I'm Eric from GM by way of Cruise, and I'm excited to talk to you about VLM 80. So end-to-end driving models can suffer poor performance in complex and long-tail scenarios, possibly due to a lack of reasoning. And directly using a foundation model like VLM at inference is costly. So how can we leverage VLMs to enhance the reasoning of these models without incurring an inference time, without incurring extra inference time compute? So we're going to use VLMs as teachers to generate reasoning-based annotations, and we're going to use an auxiliary supervision head to distill this knowledge into the end-to-end driving model without any training time overhead. And so we see significant gains both on open loop and closed loop evaluation. We do this across a number of state-of-the-art end-to-end driving models and show improvements. And so we're excited as this gives a practical way to kind of bring in some VLM knowledge into end-to-end driving. So see you at the poster, VLM 80. Thank you.
Hi everyone, I'm Jim. Very excited to present DRP, Deep Reactive Policy. In this project, we aim to fix 2 major limitations of traditional motion planners, that they're slow and hard to deploy. So we use them to collect data and distill their knowledge into a neural policy. The pre-trained model is then fine-tuned with a locally reactive controller through student-teacher distillation. Finally, we combine the fine-tuned policy with an adaptive module to further enhance reactivity. The final DRP system can perform adaptive motion planning in unseen, clutter, and dynamic environments. It's also adaptive to block goals and will approach as close as possible without colliding. Although the policy was trained entirely in simulation, it can be deployed zero-shot to arbitrary, unstructured, in-the-wild scenes. The network runs at 300 Hz, enabling it to react quickly to environmental changes and dynamic obstacles. And it will remain reactive even after reaching the goal. Come and find us at poster 8. Thank you.
In this work, we introduce ROLA, a framework that transforms any in-the-wild image into an interactive, physics-enabled robotics environment for scalable data generation policy learning. ROLA consists of 3 stages. Stage 1, recovering the physical scene from a single image. Stage 2, scalable robotic data generation in simulation. And Stage 3, robot learning and deployments. Using the collected demonstrations from a single image, we train imitation policies and directly deploy them in the real world. Additionally, our pipeline enables scalable data creation to train visual language action models. As a result, we're able to train a vision-based manipulation model using only internet images. The model first predicts a grasp and, from a single image and then executes the task via motion planning. If you have any questions, please come to our poster later. Thank you very much.
We present SDS, a fully automated framework for high-fidelity imitation of quadrupedal locomotion skills directly from a single demonstration video. SDS eliminates the need for handcrafted reward functions by introducing visual and chain-of-thought prompting to improve the semantic understanding of the skill, and a closed-loop evaluation and evolution pipeline which involves reward functions through self-supervising signals. We demonstrate zero-shot transfer of 4 gates to the Unitary Go1 robot and show that SDS can work on different platforms. Each skill trains within less than a day on a single Nvidia RTX 4090. We select 4 visual similar skills with increasing dynamic complexity to assess SDS fidelity. We also showcase results on real-world hardware tracking base height to assess locomotion stability. We also train SDS on a quadruped with a different morphology featuring inverted rear joints, distinct from those of the demonstrated agents.
Hey everyone, I'm Tongxian. I'm glad to introduce O3 afford one-shot 3D object-to-object affordance grounding for robotic manipulation. Affordance represents the functionality that indicate how objects can interact. And specifically, we investigate the problem of object-to-object affordance grounding, as many real-world tasks require interactions between pairs of objects. And O3 afford achieve robust generalization across classes, categories, and occlusions. Our pipeline consists of 3 parts. First, semantic point cloud construction and a transformer decoder, and last, an affordance-based manipulation. Without the need of demonstration, our pipeline can complete tasks that require accurate spatial understanding with the help of our affordance representation and common sense knowledge from LLM. And the results on 5 real-world manipulation tasks demonstrate our method's potential for LLM-based robotic manipulation. And check more details on our website and poster number 61. Thank you.
Hello, I'm Bo from UCSD. In this work, we study embodiment scaling laws. Embodiment variations are pervasive in the real world, and we want to understand how to learn from and generalize across diverse physical embodiments. Our hypothesis in embodiment scaling laws that training policies on more diverse embodiments lead to better generalization on unseen ones. We seek to quantify this relationship using robot locomotion as a testbed and generate 1,000 robots by verifying topology, geometry, as well as joint-level kinematic constraints. We then train a single model capable of handling diverse observation and action spaces on random subsets, and observed positive scaling patterns in terms of generalization performance on unseen embodiments. In particular, we noticed that scaling embodiments is much more effective than scaling data alone for embodiment level generalization. Our policy can be deployed directly on GoTo robots with modified joint limits, as well as humanoid H1 robot in the real world, demonstrating both sim-to-real and cross-embodiment transfer. We hope this results in locomotion, inspires progress in other task domains, and represents a step towards general cross-embodiment intelligence. Thank you.
Good afternoon, I'm Yu Haolin. Our work is Tactile. Tactile is a new teleoperation system based on a library of textual manipulation types. This library provides a wide range of robust and volatile types. For new user, we built a retrieval module with a multimodal large language model to help user quickly obtain the most suitable types. User can switch between types through foot pedals, voice, or keyboard. This system fully leverages the robot's unique dexterity and its capability. The data collected by the system shows superior performance in replay and imitation learning. We invite you to see our demo at poster 57. Thank you.
Hello everyone. I'm happy to present our work Constraint Style Learning from Imperfect Demonstration under Task Optimality. It's very common that we use learning from demonstration for style regularization, and it can often happen that the task we want to achieve and the demonstration we have has a misalignment. So our motivation is to achieve the balance of these two different objectives. So we propose a ImMimic that we formulate the whole optimization problem as a constraint MDP, and we optimize our style reward only when our task reward has been within some optimality. Our results show that our method can preserve the task optimality and still learn some meaningful styles from the imperfect demonstrations, and we validate our method on the humanoid locomotion task and the quadruped hardware. It seems stuck here. So if you are interested, please come to the poster 69. Thank you.
Hello. Today I'm going to introduce our work on bipedal balance control with whole body muscular standing, falling, and simulations. Human balance is actually surprisingly difficult, and studying human bipedal balance in real life is also challenging. So to first tackle the control difficulty of human bipedal balance, we introduced a high-dimensional control framework called HBC. It's bi-level using model predictive control as the high-level planner and PD control plus inverse dynamics as the low-level controller. It is able to achieve natural behavior on very high-dimensional human models. It's near real-time and training-free, and it's based on very intuitive cost-function design. So now we can do large-scale human motion data collection that won't be very accessible in real life. And the collected data includes fine-grained muscle-level measurements that will be invisible in the real world. And thank you, and please come to poster number 9 for more results. Thank you.
We introduce UniTact2 Pose, a unified approach learned in simulation for category-level visuotactile in-hand pose estimation. The core of UniTact2 Pose is an energy-based diffusion model that unifies tactile pose estimation, tracking, and uncertainty, conditioned on multiple contact and generalizable to unseen intercategory CADs. The energy net is trained on pure simulation data synthesized by ZenSim. An estimated pose is generated by a denoising process led by the energy net. By starting the denoising process from different priors, the framework switches between pose estimation and pose tracking. On instance-level tactile pose estimation, our method surpasses conventional regression, matching, and registration-based baselines. When trained on multiple instances within one category, our method can also generalize as well to novel instance with comparable performance. Finally, we demonstrate our tactile pose estimation approach can be effectively integrated into a precise pick-and-place system in the real world. Thanks for watching.
So hi everyone, I'm Ethan presenting TRIP6. So one key challenge for robot learning is how to generalize from a single demonstration. And TRIP6 handles this by first inferring a latent influence point purely from the geometry of the trajectory, and then using a VHDL language model to ground this into a semantically transferable frame. And then in a new scene, we identify the same semantic feature and transfer the scale to this new frame, which enables robust generalization. And this is not limited to just door opening task. As you can see, the same principle can be applied to other tasks like surface wiping and insertions, allowing adaptations to different object poses, orientation, and sizes. So in short, TRIP6 infers test frames from a single demonstration without human label or pre-training. And if you're interested in our poster, please welcome to visit our poster at poster number 58. Thank you.
Hello everyone. We present GraphVLA, a graphene foundation model pre-trained on billion-scale synthetic action data. Existing VLAs heavily rely on costly real-world collected data. In contrast, synthetic data is cost-effective and scalable, but it is yet underexplored. In this work, we first built a scalable synthetic data generation pipeline and generated ThinGrasp1B, a synthetic grasping dataset consisting of 1 billion frames. Based on this large-scale synthetic dataset, we built GraphVLA, which effectively utilizes both synthetic action data and web grounding data. GraphVLA achieves strong zero-shot sim-to-real generalization, working well in dynamic disruption, unseen background, complex lighting, dark lighting, and adapts to specialized scenarios with 100 examples. Welcome to poster 29 for details. Thank you.
Hi everyone, we present Robot R1. Reinforcement learning from verified rewards has emerged as an effective strategy to teach LLMs to reason. And more recently it's been applied to robotics and embodied AI settings where robot datasets are converted to static multiple choice formats such that verified rewards can easily be extracted. But this begs one question. Why train agents on such static data instead of letting them learn from direct interaction with their environments? To that end, we propose an embodied AI agent that not only reasons about the current state of an autonomous car, but it can also make alterations to its driving behavior. And during training, these LLM decisions are not compared against static data, but they're actually rolled out in a simulator to extract verifiable rewards from these direct interactions. And we show that this approach allows 3 billion parameter models that can run locally on a Jetson to outperform models like GPT-4o. Come talk to us during post session 2, and actually there's a typo, it's poster number 40, not 325. Thanks.
Good afternoon everyone, and I'm Po Hao, and welcome to our paper Control VLA. So in summary, Control VLA fine-tunes task and environment specific skills with just only 10 to 20 demonstrations and achieve a high success rate, making robot deployment practical with fewer demonstration requirements. So our method bridges the pre-trained VLA models with downstream tasks of centric representations using the control net style fine-tuning techniques. And across 8 diverse real-world tasks involving multiple embodiments, Control VLA outperforming the baselines with fewer demos. And we also evaluate our method with long horizon tasks, which are challenging on the limited demonstration setting. And thank you for your attention. Wait for your insightful discussion on our poster number 44. Thank you.
Hi everyone, so we're interested in learning predictive models of robot skill effects, particularly in multi-object scenarios. However, when we deploy these, we'll inevitably reach out-of-distribution scenarios where the robot will fail. So here we show a few different examples where the robot's predictions don't match what happens once it's acting. And so we'd like to learn from these failures to mitigate them in the future and also recover from the failure here. So here's a specific example where the robot wants to put this box in the recycling bin, but has a very bad idea of where it should go. And so we use an information theoretic objective to solve a probabilistic inference problem to get a diverse set of simulation scenarios matching this failure, where the robot can fine-tune on as few as 20 examples and then be able to redeploy its policy, recover from this plan, and then also generalize to similar scenarios successfully. As everyone else says, come to the poster. Happy to talk about all the details.
Hi everyone, we're presenting ACLOC, an active visual localization system for a mobile robot. So we have a pretty simple motivation. When you're doing visual localization at a specific place, looking at different viewing directions give you very different localization performance. This is because the information you can get from that field of view can vary a lot when you're changing the directions. So this error distribution can actually let the robot to actively choose a viewpoint to get better localization results. So we call this distribution log map, and we design our system with a learning-based module to predict it. So our system, in the end, can predict individual single viewpoint selections within 0.1 seconds. It can also be seamlessly integrated into path planning while incorporating with other motion constraints. So as a result, Eclog can work as a simple plugin system that helps the robot to do localization on the move, while also with the flexibility to handle different multi-objective in the navigation. So come to our poster at number 89 for a lab demo and some discussions. Thank you.
All right, VLM can be used to generate low-level trajectory executable by a robot. So this can help bypass large-scale and task-specific data collection. But which VLM is the right choice? So we propose ManipBench, a benchmark which consists of multiple choice questions where VLM reason about the gripper trajectory in robot manipulation tasks. So this evaluates their low-level reasoning and planning abilities. The benchmark has over 12,000 questions built upon diverse data sets from the real world and in a simulation. And we test 33 VLM from 10 different VLM families. So to evaluate our benchmark, we also performed real-world experiments on separate tasks, and we found a correlation between a model's performance on the benchmark and on the task. So happy to chat more in the posters. Thank you.
Hello everyone, I'm Lu Zhesun from TTIC. Today I'm going to introduce our paper, Flashback, Consistent Model Accelerated Shared Autonomy. First of all, what is shared autonomy? It means the user shares control with the assistant agent to complete some difficult task. In our case, the goal is never explicitly given to the agent, so the robot has to infer the user's intention. We first train a diffusion model on expert data. We do not require any reward, goal, dynamics, nor user feedback to train our model. Then we assume the user intention action can be seen as an expert action plus some noise. Using the diffusion model, we recover the corresponding expert action, but in this work, we speed up the process by using a consistent model to get a one-step prediction. We evaluate our method in both simulation and real-world experiments. Please come and visit our poster at number 23. Thank you.
I'm Jaden, and I'm going to be talking about our paper on action-free reasoning for policy generalization. So human video data offers a promising route to scaling robot data, but it doesn't contain actions. We posit that despite this, it still contains rich information just beyond hand tracking that can enable better robot policy learning. So to this end, we present RAD, reasoning through action-free data. RAD goes beyond existing works that track points, plans, or sketches from human video data to extract reasonings, including high-level plans, subtask decomposition, movement primitives, or key scene details. With RAD, we can learn how to reason from the human videos and learn how to map reasonings to actions from robot data. RAD improves performance by 15% on tasks unseen in human or robot data, and it also improves performance by an additional 15% when we tap into in-the-wild data from the something something data set. Please see our poster for further details.
Hello everyone, we present Search TTA, a multimodal test and adaptation framework for visual search. AVS is similar to object goal navigation that uses VLMs, but we do it in outdoor settings. Challenges include a lack of datasets with unseen targets, and a lack of online correction methods when VLMs hallucinate. Search TTA accepts inputs of various modalities, generates a probability score map that acts as priors to guide the search planner, and performs online adaptation via gradient updates. To train and evaluate Search TTA, we curate AVS Bench, an internet-scale ecological dataset. It contains up to 380,000 satellite images, along with taxonomies, represented by different modalities. We successfully validate Search TTA on a drone, with perception simulated in a Yosemite Valley simulation, the task to find bears. We'd like to highlight that TTA improves search performance most significantly for out-of-domain taxonomies and when training data is limited. Happy to chat more at poster 70, the green one. Thanks.
Hello, I'm very happy to present our work, MimicFunc, imitating tool manipulation from a single human video via functional correspondence. So in this work, we studied the problem of function level generalization, meaning that given a single human video of tool manipulation as input, we want a robot to imitate from this video and generalize to different tools with the same function. Here, the core problem is how to overcome intra-function variations to achieve function level generalization. To answer this question, we propose MimicFunc, a method for imitating tool manipulation skills from a single human video via functional correspondence. For example, given a single human video of pouring with a mug, the robot can imitate from this video and generalize the skills to different tools with the same function of pouring, for example, a teapot, a watering can, or a saucepan. In addition to pouring, MimicFunc also supports diverse tool manipulation tasks. So if you're interested in our work, please start our poster session 2, number 39. Thank you very much.
Hey, I'm Moritz, and I'm excited to present our work on Flower for compact and efficient VLAs that anyone can train from scratch. So here at CORL, we have seen many exciting work on VLAs that typically combine pre-trained VLMs with large-scale diffusion transformer. However, this training recipe does not work for small VLAs below 1 billion parameters that we need for larger efficiency. Because we still need to preserve the large-scale diffusion transformer, but then don't have enough capacity to have a large enough VLM. In order to solve this dilemma, we systematically applied key design decisions for small VLM and proposed several architecture innovations like intermediate fusion and global RLN that enable us to train a competitive VLA in just 200 GPU hours. That matches the performance of way larger VLAs like Pi 0.5 on benchmarks like Libero and Kelvin. If you want to find out, come to our poster 50. Thank you.
Hi, my name is Pierce Howell, and I'm a PhD student at Georgia Tech. Consider a scenario where fire departments gather heterogeneous firefighting robots to suppress a wildfire. Robots must assume roles in real time based off robot capabilities and the environment, adjusting to team changes and damages. Existing neural network architectures for multi-robot systems typically use one of two types of policies, either shared parameter or individual parameter policies. These approaches are often viewed as a dichotomy, forcing a trade-off between efficiency, generalization, and diversity. Instead, we view these approaches as two ends of a spectrum and introduce a middle ground approach, cache, that leverages hypernetworks to enable a single set of learnable parameters to dynamically adapt robots' behavior based on robot capabilities and the environment. We showed that cache can generalize better to unseen robots and teams while offering learning efficiency and parameter efficiency. Additionally, we demonstrated cache on physical robot hardware and showed that it can adapt well to online changes and capabilities. Thank you. We look forward to seeing you at our poster 20.
Hi, my name is Pirik, and we demonstrate a few-shot neurosymbolic imitation learning for long horizon planning. We do so by abstracting symbols for task planning and learning continuous controls. Our approach can also perform zero or few-shot adaptation to more complex tasks. So here is the kind of demonstration we give to our agents. So it's only skills demonstrations and not transitions. And we actually never show our agent how to solve the complex tasks. Nevertheless, as you can see, our agent is able to solve complex and long horizon tasks, like the towers of Hanoi, in different settings. And we also evaluate our agent in different domains, like donut assembly, kitchen cooking, and forklift pallets management. So we showcase that our approach is domain agnostic and can do more than pick and place. Thank you so much, and my poster is number 43. Thank you.
Good afternoon. My name is Mark Vandermerve. I'll be presenting my work on in-context learning for dynamic manipulation. So when performing a dynamic manipulation task, such as rolling a ball to a target location, we may not succeed at the first attempt due to the complexity of the interaction. However, we can utilize information from previous interactions with related dynamical systems to try to improve our result iteratively. So we propose a method that takes a given policy and execution result along with a small policy improvement data set over similar task instantiations to predict a new policy. And to fit the policy iterator, we use in-context learning with a pre-trained LLM to predict the policy adjustment. And we show over a variety of dynamic manipulation tasks that we can exploit in-context reasoning to iteratively improve policies over varying physical properties and goal locations. Thanks.
Hi, I'm Zhi Su, a fourth-year undergrad from Tsinghua University, and today I'm here to present our learning framework to achieve cooperative and competitive robot soccer games. So our framework can achieve the 2 versus 1 robot soccer game in the real world, where the 2 robots learn to cooperate by passing and shooting. And thanks to our decentralized design, we can replace the robot with a human player, achieving a human and a robot interaction. On the defensive side, the red robot can learn to block the passing and then counterattack. And here we demonstrate the 1 versus 1 setting, where the blue robot learns to use the wall to block, shoot, yeah, and also by self-play, the red robot can learn to anticipatory move and block. Yeah, thank you.
We present Retrieval, a method to add in-context adaptability to VLAs. Here, Pi0 struggles to adapt to the grasp and motion required for this new object, an idly plate. It also faces the issue of language grounding when distracted objects are in the scene. Can we add ICL to VLAs so they can adapt to new tasks without training? Yes, we propose Retrieval, or retraining for in-context learning. We created Retrieval Pi0, a VLA that can adapt to new tasks just with retrieval and in-context learning and without any additional training on that task. Here's Retrieval Pi0 completing the tasks with the new unique object, the idly plate. Further, if you fine-tune like we pre-trained Retrieval, you get really reliable and robust policies. Thank you. Please visit our website.
Hi, my name is Viraj and I'll be presenting our work on diffusion-guided multi-arm motion planning. Existing learning-based approaches have shown impressive performance, as you can see here. However, they rely on massive data sets, often involving complex multi-arm interaction behaviors, including up to 4 arms. Even though these approaches have shown to be scalable, if you train those approaches with only single or dual arm data, that scalability falters, often leading to collisions. Our approach, which we call DGMAP, starts with a single arm and uses its observation to train a single arm diffusion model whose job is to predict single arm trajectories. In a multi-arm setting, conflicts are identified in a pairwise manner, which are then deconflicted using an ego agent that utilizes this dual agent observations to train a dual arm diffusion model whose job is to predict efficient collision resolution strategies. Now, these 2 models are then composed using MapIF-like techniques to compute delta joint action sequences, which when combined with closed loop feedback results in the following behaviors, enabling us to not only scale to 4 arms, but even up to 8 arms. For more details, find me at poster number 18. Thank you.
Hello, I'm Zhao Dong. I'm here to present OnPose, model-free post estimation framework. So P for novel objects is hard because many methods still rely on CAD models. Thus, many model-free method uses diffusion priors to solve this problem. But that will introduce unobserved areas, which introduces uncertainty. The question is how to quantify it and use it for future observations. We introduce OnPose, a novel object framework that uncertainty has. So from single frame, we get priors with pixel level uncertainty, and then we leverage it to 3D diffusion Gaussian splatting and refines it as new frames arrive. A post graph is used to fuse the priors and diffusion. On standard benchmarks, pose improves pose accuracy and reconstruction quality. Please visit poster number 84 for more details. Thank you.
Hi everyone, excited to share PriorTouch, a framework for translating high-level contact preferences into low-level robot control. Given a reference trajectory involving multiple contacts and sparse feedback about some kind of discomfort, PriorTouch uses a learning-to-rank contextual bandit with simulation in the loop to safely adapt to contact preferences. In practice, upon receiving feedback, our robot first moves to a safe configuration to avoid further discomfort. This is followed by spawning a digital twin, which is then used for exploration via LinUCB rank, our novel learning to rank algorithm. Upon convergence, we return to the real world to successfully adapt to the user's preferences. In our real world user study, participants highly favor PriorTouch over the baseline approach. PriorTouch reliably extends to complex trajectories involving multiple contacts, demonstrating its scalability. Please drop by at poster 21 to chat more. Thank you.
Hi everyone. Our paper introduces decoupled forward-backward model-based policy optimization, or DMO. DMO combines APG and MBRL, achieving very high sample efficiency. In APG, the forward pass uses the high-fidelity simulator, and the gradient of the objective is obtained by backpropagating through the differentiable simulator. In MBRL, the next state is predicted by a learned dynamics model, and the gradient is obtained by backpropagating through the learned model. DMO combines both approaches. It unrolls trajectories with the simulator like APG, but computes gradients via backpropagation through the learned model. DMO avoids compounding model rollout errors and yields far better sample efficiency than PPO and SAC. Thank you for listening.
Hello everyone, my name is Lichuan Wang from Georgia Tech, and today I'm going to present my TopoCut. So TopoCut is trying to solve the multi-step cutting problem that's cut the object into some target shape, such as slice, stick, and dice. So we solved this problem by building a framework that's consistent of a benchmark with a MLS and PM particle system and a topological discovery algorithm, and also a post-invariant spectral reward function. We also train our policy with our self-collected data. So the hard thing in a simulation environment is the topological information tracking. So we solve this by the damaged particle tracking and also the fragment ID maintenance. So here are just demos showing how we are doing this. And for the policy learning, we were training a policy that's based on discrete diffusion policy, since cutting is literally just bisect the particles. So for more demo, please come to the poster 16. Thanks.
Hello everyone, I'm very happy to present our work, Local Touch, Learning Dynamic Quadrupedal Transport with Tactile Sensing. In this work, we want to enable quadrupedal robots to perform dynamic interaction with objects. Therefore, we build a tactile sensor and we mount the sensor on the back of the robot. Then we train the robot to transport objects in simulation. After that, the policy can achieve zero-shoot transfer to real robots. We can see the robot carefully adjusts its motion to balance the object. If you are interested in more details, you can come to our poster to learn how we build a tactile simulation and how we train the symmetry gates. Thank you.
Hello everyone. Today we are presenting our paper, Learning Smooth State-Dependent Traversability from Dense Point Clouds. As shown in this clip, robots nowadays are capable of building detailed point cloud maps in real time. However, leveraging this rich environment representation for traversability analysis is challenging. Consider the highlighted obstacle as an example. Most existing methods take elevation maps as input, which can lose important geometric information. Moreover, the state dependency of traversability is crucial but mostly overlooked. When only a few training instances are available, the mapping from state to traversal risk can be extremely challenging to learn. To this end, we present Sparta, a method leveraging Fourier basis functions that is capable of performing challenging tasks and generalizes seamlessly to hardware, and can be easily extended to handle other problem settings. We look forward to seeing you at the poster session.
Oops. Hello, I'm Alice, and this is Coop Motion. We learn dynamical systems from demonstrations, so given trajectories denoting desired robot poses in time, we use Koopman theory and flow divergence losses to learn a dynamical system or flow map such that the flows match the trajectories in space and time, is recovered during disturbances, and converges to goals. Evaluations show stability, interpretability, and sample efficiency. We evaluate on robots operating in a fluid flow tank, and here we emphasize the smoothness of the trajectories from our learnt flow field and the lack of local minima. Would love to chat at poster number 12 and check out our website for more awesome videos. Thank you.
Hi everyone. Given only an egocentric camera view, do you think you could take a look at it and instantly say, this spot looks safe to move towards? Probably yes. Humans don't need precise depth sensors for navigation. We intuitively judge based on what we see and pick obstacle-free regions from visual cues. However, current end-to-end offline visual navigation policies don't directly optimize for obstacle avoidance and instead imitate the expert demonstrations, which only implicitly captures these skills. Alternatively, robots can use LiDAR, but these are expensive, bulky, and not scalable. To address these gaps, we present HALO, Human Preference Aligned Offline Reward Learning for Visual Navigation, where we quantify human navigation intuition into a reward model. We then use the Plackett-Luce model, a generalization of the Bradley-Terry model, to rank actions. This model can then be used to train a human preference aligned policy. Happy to chat more at poster 14. Thank you.
Hi, I'm Katie, and I'll be presenting sequence modeling for time-optimal quadro-trajectory optimization with sampling-based robustness analysis. Here, we explore sequence-to-sequence imitation learning to learn time-optimal quadro-trajectories with constraints on the full dynamics, given a predefined geometric path. We leverage differential flatness to learn only two variables, the minimum required to recover the full trajectory. In addition, we quantify feasibility by assessing the trackability of trajectory predictions within planned time windows and measure their robustness to small perturbations of the model inputs. We demonstrate the feasibility of our planner on hardware, showing comparable performance to optimization-based methods for only a fraction of the compute time. Our model, trained on rest-to-rest trajectories, is also able to generalize to non-rest endpoints, allowing us to stitch together longer horizon trajectories without a loss in performance. For more information, please check out our poster at number 11. Thank you.
Okay, hi everyone. This is Ziwen from Tsinghua University, and here is introducing Embrace Contact. So contact sequences are crucial for legged robots, especially in this control context-rich task. But traditional methods also always cost too much computation and makes it really hard to deploy in the wild. And previous humanoid works consider only fixed contact in the ground. We successfully tested that using a simplified collision shapes and the pure sim-to-real RL pipeline can achieve this context-rich task in the real world without any real-world fine-tuning. We curated a set of extreme actions and trained them together using multi-critic technique. We also show that using multiple frames of the future reference, it significantly increases the performance, even if the motion is not so feasible for this type of robot. And please check out our paper at poster number 1. Thank you.
Hi everyone, I'm Xue Yi. This is the Reason Plan, a novel MLM fine-tuning framework for closed-loop driving, which comprises the self-supervised nesting prediction task and the decision chain-of-thought process. In case 1, it anticipates hazard from a warning zone. Upon detecting the obstacle in the current lane, the eco vehicle decelerates and prepares for lane change. Once the safe gap is confirmed, the Reason Plan performs the lane change before returning to the original path. In case 2, it recognizes the traffic lights and strictly follows the rules, stopping at red and moving only at green. When the green light switches back to red, the Reason Plan stops. Our post number is 33. Welcome to our booth for more discussion.
Hi, I'm Harry, and we've been working on dexterous tactile in-hand manipulation with LLM-designed reward functions. And anyone who works with reinforcement learning will tell you that reward function design is really, really difficult and there's a lot of guesswork. And LLMs are just really happy to keep guessing. And what we found is by being quite picky about what context we give the LLM, we can get really good code back with much better performance and much less code complexity, which speeds up training as well. We validated this in simulation and in the real world and found that in the real world, across various LLMs, we get much more rotations per episode and much more increased episode length. So we've got all of the code, we've got a website, everything online. Please come and visit us at the end, poster number 60. Thank you.
Hello, my name is Eckhart and this is Dennis, and today we introduce meta optimization and program search using large language models for task and motion planning. We want to answer the question, how can we leverage VLMs for physical reasoning? We introduce a 3-stage optimization problem where each layer informs the previous one. In the first layer, our language model generates policy code and constraints that define a motion plan. It also decides parameters to be optimized by the later stages.
These parameters are then optimized by zero BBO method. We used CMAS. Right. The first stage then applies trajectory optimization to roll it out in the physics simulator. So here you see the results. Our approach outperforms the baselines, and here you see the results as images. Thank you for listening. We see each other in the posters. Our poster booth is number 71. I repeat, number 71. Thank you.
Please give big hand for the last presenter because they waiting for 1 hour. It's time to enjoy post session on the first floor, and then I will just give very short message. We will have Becky today night, right? And then we also prepare unlimited alcohols. So let's make them empty together. And then I will give you very secret. I will give you two secret for today's banquet. Today's K-pop performance will be not unusual, not usual. So it is very special. So please check what is special. And then please remember that we have a small number of seats, more than 1,000, but some people who are very late, you need to be at the overflow room on the first floor, so don't miss, be at the venue. Thank you very much.
마이크 부탁드릴게요.
네, 확인했습니다.